second day of our Astrobiology conference. I'm Zainab. I hope you enjoyed yesterday's talks. I'm sure you will enjoy more today. Our first speaker is Dr. Dimitra Atri. He is a research scientist at New York University and New York University Abu Dhabi, and also a researcher at Blue Marble Space. He is an astrobiologist and planetary scientist leading a Mars group. His work involves analyzing data from various space missions to determine the habitability of Mars and other planets in our solar system and beyond. Today, he will be with us with a topic Mars, Dead or Alive. Hi, Dr. Atri, how are you?
Hi, I'm good. How are you?
I'm fine, welcome. I'm really happy to have you here.
Yeah, it is great to be here, and thanks to you and all the organizers for organizing this.
Thank you. You can start to share your screen.
Yeah, let me try this. Hmm, hold on.
You will click the present and then share screen and then entire screen. And if you have an audio in your presentation, you can allow the audio. And that's it.
I've done this keynote. Are you able to see it?
No, maybe it's because of the permission. Sometimes Chrome needs permission to share.
Oh, okay, let me try another way.
Okay.
This is screen. Are you able to see my screen too?
No,
Still
I
nothing.
cannot see. I think our audience cannot see also. Yeah,
Can you see?
now. Yeah, now we can see. Yeah.
All right.
Okay.
Okay, great. Okay, great.
Yeah.
I'm glad it worked.
Okay,
So
stage
I'm
is yours. I'm going. You can start your.
all right. So hello everyone again. I'm going to talk about Mars, dead or alive. I'm Dimitra Atri from New York University in Abu Dhabi. So in case you were wondering, New York and Abu Dhabi, NYU now has a global presence in addition to its campus in New York. It has a campus in Abu Dhabi and also in Shanghai in China. All right. And the most interesting coincidence is the three campuses where NYU's campuses are based at. All three had missions going to Mars recently. UAE's HOPE mission, NASA's Mars 2020 Perseverance rover, and also China's Tianwen-1. So let me start by giving you a quick introduction to Mars, although I'm sure most of you know these things, but it is just good to get some perspective. So the size of Mars is almost half that of the Earth. You can see the Earth's moon is quarter of that size. On the right, you can see the land area of Earth, which is similar to the whole area of Mars. Its mass is about 1/10. Okay, so it's a very, very light planet compared to the Earth. Its volume, it would take more than 6 Mars to fill the volume of the Earth. So from this, you can imagine how small the planet is. Its structure, although we don't understand a lot about the inner structure of Mars, but we
I'm
still.
sorry to disturb you, but we can see just a screen with purple hills, not a presentation if you are moving on it.
Oh, I am. Oh, I'm sorry.
Okay.
I have no idea why that is happening. Uh, Let me remove this. Are you able to see my slides?
No, it's still just a background picture.
Oh no. Let me share this again. I'm sorry about this. This is the first time I'm
It's
using
okay.
this platform. Um,
Maybe you can
okay.
upload your slide here. So I
Yeah, yeah.
think
Are
I
you able
can.
to
Yeah,
see it
yeah,
now?
yeah. Now we can see everything. Yeah, yeah.
Yeah. Is this clear now?
Uh, I'm waiting to see because it didn't change now. No,
Oh, the slides are not changing.
no.
Oh, why? I don't know why
It's
that is.
freezing. I don't know why. Maybe we can do like this. You can press the present and slides. You can click the slides and your computer. From your computer, you can upload here and we can show. We can try this one. Did
Oh,
you
okay, okay.
find?
Sounds good. Sounds good.
Yeah,
Let me do that.
present and slides and then your computer. Or if you have Google Slide, you can choose that also.
Yeah, let me do that.
Okay.
Oh, okay, I need to export it to PDF. It's a keynote.
Okay.
Yeah, let me just export to PDF. I just
Okay.
had, I think, one or two um, animations, but this is fine. I can just, uh, should be okay. Okay, now I should be able to. So present
Yeah.
slides,
Slides and your
your
computer.
computer,
Yeah.
upload file,
I- If you
and
upload, also I can add here, so we can figure out the issue.
yeah. Yeah, I've uploaded it now.
Okay, I'm checking. I didn't see.
Yeah, it is saying processing.
Oh, okay. When I'm able to see, I will click and yeah.
Yeah,
Okay. Okay, now we are.
yeah,
Yeah.
I'm so
Yeah.
sorry about
It's
this.
okay. It's okay. No problem. I'm going. You can start. See you.
Okay, so now you will control the slides, right?
Yeah, but you can also.
Okay, yeah. Let me just do that. So,
Okay. If you cannot, I will do. Yeah, you can.
okay,
Okay.
now you're able to see this, right?
Yeah, yeah, yeah. It's moving.
Yeah.
Okay. Okay.
Yeah. So these are the three campuses which I was showing you in Abu Dhabi, New York, and Shanghai. And these are the three missions: Hope, Perseverance, and Tianwen-1 from China. The size of Mars is about half that of the Earth. Its surface area is pretty similar. The mass of the planet is much lower. It is about a tenth that of the Earth. The volume is about a sixth. So six Mars can fit inside the Earth. So this is just to give you an idea of how small Mars is. Its structure is not very well understood. So this was supposed to be an animation showing you the internal structure of the Earth and Mars. So we know that just like the Earth, Mars is also formed with a core. It has a mantle and a crust. Um, on Earth, the core is a solid, but on Mars, we don't know. It is most likely a mixture of a solid or a liquid, and we are still trying to figure it out. Gravity on Mars is a little bit smaller than the Earth, about two-thirds the gravity on the Earth. And so, if you are on Mars, you'll be able to jump, much further distance. The atmosphere of Mars is extremely thin. It is about 1% that of the Earth, very thin atmosphere. On Earth, as you know, we are made mostly of nitrogen and oxygen and 1% of other gases. In case of Mars, it is mostly carbon dioxide. So 90% of Martian atmosphere is CO2, with a little bit of argon, nitrogen, and many other trace gases. Now, because the atmosphere is extremely thin, it is extremely cold. So, as you can see, the temperature on Mars can go down to minus 140 degrees Celsius. The average temperature is close to minus 60. And the maximum which you can see in certain areas in summer months is 30 degrees Celsius. So it is an extremely cold planet. The year on Mars is roughly twice as long as Earth here. So, for example, this Hope mission has been orbiting Mars for 2 years, 2 Earth years, which means that 1 year on Mars. All right. So let me give you a quick introduction to the history of Martian exploration using space probes. So the first attempt was made in October of 1960. This is the Mars 1M probe by USSR. It was designed to be a flyby mission, so it would go not landing on Mars, not orbiting around Mars, but just go fly past it, take some measurements, take some photographs, and send it back to the Earth. It had an instrument to detect UV light. Spectrometer is a device which can break light into different components, just like what a prism does. And by studying those different components, you can study a lot of things about what is going on Mars. It also had a radiation detector, a cosmic ray detector, but it was a failed mission. It even failed to orbit the Earth. And then there were many failed attempts by the Soviets. US also tried, and there were several failed attempts. And this is what you see throughout Mars exploration history. Most of the missions in the 20th century failed. So, after a bunch of failures by both agencies, the first success was in 1965. This is the Mariner 4 probe by NASA. It did a flyby in July 14th and 15th, 1965. It sent images of the surface of Mars. So on the left, you can see a photograph which shows craters. It looks very much like the moon. And this was the clearest view of Mars at that time. We didn't know how Mars looked like. On the lower right is a painting based on data from this mission. So in the 1960s, it was not a time for any kind of digital technology that we are familiar with now. So when the data came in, based on that information, because everyone was so keen to look like, to find out what Mars looks like, based on that data, the scientists and engineers who were a part of that mission started to make drawings using different colors. And this was the first image on the lower right, which they came up. Obviously, when more data became available and they were able to process it, they were able to show you the image on the left. Uh, then moving on, 6 years later, 1971 was a very important year for Mars exploration. You had many launches scheduled. Um, so on May 9th, you had Mariner 8, May 10th, Cosmos 419 by the Soviets. And you can see the full list here: two missions by the US, three missions by the Soviet. And it was also a time of Cold War. It was very intense competition, space race between the two countries. And Mariner 9 by NASA became the first orbiter around Mars. So it reached Martian orbit on November 14th, 1971. And if you go to NASA JPL's website, it still says that in 1971, the Mariner 9 spacecraft beat the Soviet Mars 2. So it was not just about doing science, exploring planets. It was also a big political statement. The Mars 2 orbiter by the Soviets entered just a few days later on November 27th. On December 2nd, 1971, the Mars 3 orbiter entered the orbit, and it also landed successfully on the surface of Mars. And this is the first probe designed by humans which made a successful soft landing on the surface of Mars. However, just after landing, it stopped communicating, so there was no science output. You can see the lower picture how this small rover looked like. We have different looking rovers now. And since then, NASA has successfully launched a number of probes in orbit around Mars and also on the surface, which I will talk about later on. So this was all happening in the 20th century. The world changed. So in the 21st century, in 2003, European Space Agency's Mars Express launched, and it entered the Martian orbit on Christmas Day in 2003. They also had a lander named Beagle 2, but it failed. It crash landed on the surface of Mars. So this was the story at that time, that it crash landed. But later investigation found that it was successfully able to land on Mars, but there was an issue with opening of its solar panels, and those panels were not fully deployed. Its antenna was not able to come back up, so it was not able to communicate back, which was really unfortunate. Then in 2014, Indian ISRO had a Mars orbiter mission called Mangalyaan. It entered orbit in September 2014, and this is the history of Mars exploration. That in the 20th century, only two countries. Then the first 2 decades of the 20th century, European Space Agency and India, and then now in the 2020s, you see a new country, UAE, sending a mission to Mars. And I work very closely with this mission. It was launched in July 2020 when we were all under lockdown. It reached the orbit of Mars on February 9th, 2021. And 2021, just a few days later, China also became another country to reach Mars. They had an orbiter, a lander, and also a rover, a great achievement in space exploration history. This is just a summary of all the failed missions to Mars. You can see how difficult it is to go to Mars. So let me now go to what have we learned from Mars. So as you saw earlier, that Mars is full of impact craters, just like the moon, because the atmosphere is thin. It undergoes impacts, which you can see now. So this is a figure of all the impact craters on Mars, more than 60 kilometers in diameter. So these are really huge impact craters, and you can clearly see that it is not uniformly distributed. There are some places on Mars where you see a large number of craters. Some places you don't see any impacts. Some places you see less impact craters. So this is a mystery. Why is this happening? And the reason is just if you use common sense, if you expose a surface for a very, very long time, there are more chances that it is going to have more impacts. And if it is a new area, then the probability of impacts is less. So you will see less or no impacts. And this is what people use to determine the age of the surface. So this is the distribution of, on the vertical axis, you can see the density of craters. So you take an area and you count the number of craters. So on the vertical axis, you see the number of craters per kilometer square. And on the horizontal axis, you see the size of the crater, the diameter of the crater. So in this plot, if you see the top part, in the top part, uh, this is the oldest region. In the oldest region, you are going to see the highest density, which you can see on the top part. You can also see the highest diameter craters there. And as you move inwards, the plot becomes younger and younger. And in this way, just by counting crater density on Mars, you can figure out the age of that place on Mars. And on this plot, the age of different surfaces, you can figure out from as young as just 10,000 years ago all the way to 4 billion years ago. So this is a very straightforward technique which is used to determine the relative age of different surfaces on planets. In this case, it is for Mars. This is how it looks like. So if you count these craters, you can come up with broadly three types of geological units on Mars. And these are given by three different colors. And you can see how they are distributed. So the southern part is this whitish part, which is Noachian. Then the rest of Mars is a combination of Amazonian and Hesperian units. So three distinct type of geological units on Mars. And what is the most interesting thing about this is you can clearly see a north south difference. So here you can see, right, the southern part is white. It's a completely different geological unit compared to the north. So if we look at the altitude distribution of Mars, so in this plot, this is taken by NASA's MOLA instrument. It's a laser instrument which can give you a precise measurement of elevation of different parts of Mars. So the blue part is lower, the red part is higher. On the left, you can see these are four huge mountains. These are volcanoes on the surface of Mars. Uh, the tallest one, Olympus Mons, is more than 20 kilometers tall. Compare this to Mount Everest on Earth, which is 8.8 kilometers. So, really tall mountains. On the lower right, you can see a dark blue spot, which means it is a significant depression. It's a huge impact crater. Um, so there is a dichotomy, a clear cut dichotomy, which you see here. The northern part of Mars is all blue, which is much, much lower. On an average, the northern part of Mars is about 4 to 5 kilometers lower than the southern part of Mars. And the hypothesis is that the northern part was filled with ocean, just like oceans on Earth. There was an ocean on Mars a long time ago. And this, so a lot more work goes into this. So basically, this is a geological history of Mars. So just like on Earth, we have different geological eras. People have figured out different geological eras on Mars. So this goes back to 4.5 billion years ago. So the oldest period on Mars is the Noachian period, which, as you can see, it is the southern part. So the southern part is the oldest part of Mars, which was in the Noachian era. It is highly cratered. Then the part after that was the Hesperian era, and right now we are in the Amazonian era. There is a good chance that life existed on Mars during the Noachian period. There was liquid water. Now we have ample evidence to say that there was liquid water on the surface of Mars. And in addition to an ocean, it had liquid water producing river valley networks, it had large lakes. The Hesperian period was a transition period. So the planet became from an Earth like planet with oceans, with abundant water, to becoming drier and drier. And in Amazonian, as you can see, Mars now is completely dry. It's a desert, and this is how the planet changed. Now, as I mentioned, there are tons of evidence that there was water on Mars. So you can see signs of flowing water. So this is taken by the Mars Reconnaissance Orbiter, by the HiRISE camera. You can see clearly the signs of flowing water and also impact events. You can see tons and tons of these on Mars. I'm just showing you one example. And the advantage of living here in Abu Dhabi, living here in the UAE, and exploring Mars is that this area looks exactly like Mars. And it looks the same way because it has the similar process of how these things evolved. So you can see on the, so these are, pair of images. On the left you can see a photograph taken on Mars. On the right you see a photograph taken here in the UAE, mostly in Abu Dhabi. And there are so many features taken by different rovers, Curiosity and our Perseverance rovers. by orbiters. You can see so many features which you also see here. So here we can go to those sites, we can take photographs, we can take samples, we can investigate them. We then bring those samples to our lab using analytical instruments. We study them in great detail. And by studying how these samples were formed, how this area, which was rich in water, became dry, what is the chance of life surviving here, how can we detect life in such environments, we then connect it to Mars to do the same thing about Mars. Mars also has polar ice caps, just like on Earth we have polar ice caps. Mars also has polar ice caps. And this was a beautiful animation to show that during summer months, ice caps shrink, and then during winter months, ice caps grow, which you also observe here on Earth. So we also see those things on Mars. And on Mars you see two types of ice. So on Earth you see ice made of H2O. On Mars you see H2O ice, plus you also to CO2 ice, because Mars is extremely cold. So two types of ice on Mars. All right. So Mars overall is a perfect planet for my research because in the past, so on the left hand side, you see NASA's illustration of how Mars could have looked like about 4 billion years ago, with abundant liquid water on the surface. We know what happened on the Earth, how life originated, although we don't really understand the origin of life. But once it originated, we understand how it evolved and we know the full story. We don't know what happened on Mars. And so this is the biggest question, that, whether life existed on Mars or not. And so the two main goals of my research group here at NYU in Abu Dhabi are: number one, how did Mars lose most of its atmosphere and water? So Mars had abundant liquid water on the surface, which means that it also had a thick atmosphere to maintain some kind of a greenhouse effect, so maintain that warmth. So what happened? How did it become from having a significant atmosphere to such a thin atmosphere, just 1% that of the Earth? How did it lose most of its water? And did life ever originate on Mars? And can we find signs of extinct or extant life on Mars? So maybe there is life now on Mars, maybe below the surface. Can we find signs of it? Maybe life at some point originated on Mars, it existed for some time and then it became extinct. We don't know. And so, can we find that? So, these are the two main goals of my group here. And so the biggest breakthrough was just a few years ago in the question of how Mars lost most of its atmosphere. And this was revealed by NASA's MAVEN mission. MAVEN is an orbiter around Mars. And what it figured out was that there is this radiation coming from the sun. It is called solar wind. So this is hot charged particles, hot plasma coming from the sun, and it also impacts the Earth. But on Earth, we have a very thick atmosphere, we have a significant magnetic field. So we are not really concerned about this solar wind. But on Mars, it does not have a global magnetic field, its atmosphere is extremely thin. So what happens is the solar wind can directly interact with the atmosphere of Mars and it can slowly erode it. And the physics of this erosion is extremely complex, as you can see on this cartoon on the right. And this is also one of our major focuses here in Abu Dhabi. So I won't go into this. What I was going to show you was an animation of how this works. So Let me just explain. I was going to show you another animation. You must have seen these dandelions, how this wind interacts with them, and all the seeds are dispersed. A similar mechanism happens on Mars. So, Mars, when it had a thick atmosphere, under the influence of solar activity, the upper atmosphere of Mars slowly got eroded due to different types of electromagnetic interactions, deposition of heat in the upper atmosphere of Mars, and that process even continues now, which we can see through these different missions. So we study the different mechanisms of how solar wind interacts with Mars, and then we roll back in time to study how the atmosphere was and how it evolved as a function of time, so that we can understand how the climatic change on Mars happened, how the distribution of water on Mars changed, and so on. So this HOPE mission is also extremely important to study this, because HOPE has a very different orbit. So all the missions that I discussed here, so MAVEN, Mars Global Surveyor, Mars Reconnaissance Orbiter, Mars Express, and so on, they try and go very close to Mars, because when you're very close, you get in-depth observations of Mars. You can even scoop a sample of the upper atmosphere of Mars using these orbiters. But the downside is you cannot see the full planet at once all the time. So Hope is much, much further away from Mars. Its name in Arabic is Al Amal. So the outermost orbit is the orbit of Hope. And so the advantage of having such a big orbit is that you are able to see Mars's full disk all the time. You can see the planet rotate in front of you, and you can understand all the physical processes happening on the Mars at a global scale, which was missing till now. And so by combining data from the two orbiters, from Maven and from Hope, the plan is to form this comprehensive picture of what is happening on Mars right now, understanding its present weather and climate, and extrapolating it back in time to understand the full history of Mars. So, this is just one of the studies that we did with Hope. So, just like the Earth, Mars's axis is also tilt. It is tilted by 25 degrees. And on Earth, we have seasons because of this tilt. And on Mars, what happens is Mars's orbit is elliptical. So, in addition to having a tilt, which causes different seasons on Mars, the distance between Sun and Mars also changes. And so, when the distance between Mars and Sun is small, the temperature obviously goes up. When it is further away, temperature goes down. So, this effect, coupled with having a tilt, causes very complex seasons on Mars, which we study. A day on Mars is 24 hours and 37 minutes, so slightly longer than a day on the Earth. Um, so this is measuring the surface temperature. So this is a diagram that we made using data from the HOPE mission. We are able to measure the surface temperature of almost all regions on Mars. So this is an older study. We have much better diagram now at all local times. So you can find on any point on Mars at 9 o'clock in the morning or 11 p.m. at night. We are able to tell what the temperature is. And then what I thought, well, NASA has these two rovers, Curiosity and Perseverance, which are on the surface of Mars. They are also measuring temperature. So why shouldn't we compare the two? And that's what we did. So we made a comparison of how the temperature changes on at the location of Curiosity rover, which is at Gale crater, of Perseverance rover, which is at Jezero crater on Mars, and we found the results to be consistent with Hope's mission. There were minor discrepancies which we now understand, and this has enabled us to obtain really high resolution map of surface temperature of Mars in great detail. We also study auroras on Mars. So here on Earth, we have magnetic field mostly focused on the poles. So you see auroras, which is interaction between solar wind, Earth's magnetic field, and the atmosphere. You see these in polar regions on Earth. Mars does not have a global magnetic field, but what happened is Mars used to have a magnetic field, and so the different areas of Mars are now magnetized. So that weak magnetic field is spread throughout Mars. So we see auroras on Mars throughout the planet, which have been seen with earlier missions. But with hope, we see these auroras, which are, like these sinuous rivers, thousands of kilometers long, which we don't understand. So, in the plot which we made from data from the Hope probe, as you can see on the lower middle one, you see lower left one, lower right one, you see auroras which are thousands of kilometers long. And we don't know why these auroras exist, and we are trying to figure that out. This will also give us insights into how solar radiation interacts with Mars, and we will understand better the escape mechanism. How does solar wind interact with Mars, leading to the escape of its atmosphere? So, as I mentioned earlier, one of the first things people did was to study different areas on Mars. So, on Earth, because there is so much activity going on, the downside is we do not see ancient surface anymore on Earth. So, on the top, you see surface area. So, on the extreme right, close to zero, we see areas on Earth which are formed maybe a billion years old, and as you go back in time, all everything is eroded. You can't see any of those. So on Earth, it is impossible to find an area which is 4 billion years ago. Okay, some people claim they have found areas, but those claims are highly controversial. But on Mars, right on the surface, you can see areas which are 4 billion years ago. This was the time when life originated on Earth. So it gives you an insight into not only the condition of Mars at the time when life originated on Earth, it can give you an insight into the state of the solar system because of these bombardments. And so this is a unique opportunity that you have 4 billion years old areas on Mars right now, which you can study using telescopes, using orbiters. You can go and land there. You can probe using these rovers. So it is extremely exciting. It is also a window into early Earth, and we hope that by studying these areas in great detail, we'll be able to study how life originated on Earth. All right. So so people have known these things, and the biggest mission in the 1970s to look for signs of life was the Viking mission. So it was a set of two missions, Viking 1 and Viking 2. These were identical. So two orbiters and two landers. These two landers landed on two different parts of Mars. And the main objective was to search for life on the surface of the planet. And this is a photo of Carl Sagan here with the Viking lander. You can, see the size of the lander here, pretty big lander with a bunch of instruments. And on the right, this is the actual photograph taken by the Viking 2 lander from the surface of Mars. You can see it is completely dry, it is full of rocks. And so, one of the main experiments on board the lander was the label release experiment. So, in those days, in the 1970s, there was a technique to detect contamination in food products. So let us say, a company is selling a food product. uh, so you have inspectors from the government. They would go there just to see whether something is contaminated or not. So what they would do is they would take a sample. They would put nutrients in it. And if of place which they claim is completely clean, if there are bubbles formed, if you see any sign of gas, which means there were microbes, so it would mean that they were lying, right? There is some contamination there. So they thought, so NASA at that time hasn't had a same experiment, that why don't we take these nutrients to Mars? We would scoop a sample of Mars, we would put these nutrients there. If there is no life there, nothing is going to happen. If there is some microbial life, then they would produce, they would utilize these nutrients, they would release gases, CO2. And this is what we did, what NASA did. And on the right you can see, so uh, so on the vertical axis, this is the measure of radioactivity coming from the sample. On the horizontal axis you can see time. So this nutrient was tagged with radioactive carbon, just to make sure that the gas, when it reacts with biology, when it comes out, it will come in form of radioactivity, and you can measure this. So what happened is they took a sample, they injected nutrients in it, and then after a few hours you see radioactivity going up, which means emission, which means gas is coming out of that sample. And this happened in both different experiments, and it became a huge news, which indicated signs of life. And it became a huge news that Mars is alive, there's life on the surface on Mars. But then people were able to predict the same effect here on Earth just by regular physics and chemistry experiments. So the nutrient, if you put this with Martian soil called the Martian regolith in Martian conditions, just by regular chemistry, you can produce this signal. So no sign of biological activity. In addition to this label release experiment, it had another experiment called the pyrolytic release, also had an experiment called gas exchange. I don't have enough time to talk about all of these, but there is a broad consensus that the result of all three experiments on both the landers showed that there is no biological activity on Mars. They found no signs of organics on the surface of Mars. There was a Phoenix lander, so another lander on Mars by NASA, and they found something called perchlorate salts. So the surface of Mars is filled with these perchlorate salts, which are used as explosives here on Earth. So whenever you see fireworks, those are perchlorates. And so if there are perchlorates on Mars, perchlorates would react with any kind of organic substances and would decompose them. Okay, so then it became very disappointing news for astrobiologists that there are no organics on the surface on Mars. Plus, the Martian soil is highly toxic, so you cannot have any signs of life. Now, in the 1990s, in 96, there was a Martian meteorite called Allen Hills 84001. And on the right, you can see a photograph of this meteorite taken from a microscope. And it showed some weird structures, which at that time were interpreted. It could be due to geological activity, it could be due to some kind of microbial activity. The president of the United States, Bill Clinton, at that time announced this discovery. It became a huge news. Media ran the story as, there is microbial life on Mars, which it wasn't. These structures most likely can be produced by, regular processes. So it became extremely embarrassing for NASA to claim, signs of life on Mars. So NASA then changed its strategy from finding life on the planet to looking for water or looking for habitability on Mars, studying its environment, studying its chemistry, and so on. And this was a new era. So you can see different rovers, and these humans are here just for scale. There was this Sojourner. It was a small rover. Uh, it can go, it can land on the surface of Mars, it can move around. It had a camera, it had a bunch of instruments to study the composition of the surface of Mars, of different rocks, to study its regolith, and so on. Then there were a series of two twin rovers, Spirit and Opportunity. Then NASA had this Curiosity rover, which is the size of a big SUV. And more recently, this Perseverance rover. And the data from these rovers have been transforming. We now understand so much about Mars based on the data from these rovers. So, what do we know? So, as I mentioned earlier, the Curiosity rover, which is now, it has been deployed for more than a decade on the surface of Mars. It landed in an area which is on a crater which is called the Gale crater, and it is widely believed that this Gale crater was full of water. So, on the right top diagram, you can see this is how Gale crater could have looked like. And based on the investigation from the rover, it is now very clear that this area was full of water in the past. The most interesting result was the discovery of organics. So the previous missions could not detect organics, and this was because the instruments were not sensitive enough. So the surface of Mars, especially this place in Gale crater, it is full of organics, although organics are in very limited amount, in very small concentration. There are a bunch of instruments. So, for example, this is from the SAM instrument. SAM is sample analysis at Mars. It takes a soil sample of Mars, it can analyze its chemical composition, and the signals are consistent with organic substances. So there are many theophanic, aromatic, and aliphatic compounds, benzene rings, large, benzene rings, and so on. So very interesting macromolecules found on the surface of Mars. So this people have also found, liquid water in some places on Mars. Also, there is, some controversy about it. So what happens is Martian soil is highly rich in salts. These are called brines, and any water which is high in salt concentration, it freezes at very very low temperatures, which means that even at -5 or -10 degrees Celsius, at which on Earth water freezes, on Mars it can stay in liquid form. So water can stay in liquid form despite low conditions. Especially in the subsurface, the temperature is not that extreme. So there could be pockets of water just below the surface of Mars. Now you have all these organic substances. So maybe there are organisms which can probably survive using this. Even though Martian soil is toxic, still you find these organic substances, which is a positive news. And the most interesting thing is there are some microbes, there are some extremophiles, microbes which are capable to survive in extreme conditions. They actually use these perchlorates for their metabolism. So the idea that these perchlorates are toxic to life, well, these microbes have proven to be wrong. Microbes can use these perchlorates and utilize it as their food. All right. So the latest rover on the surface of Mars is the Perseverance rover. There is an actual video footage which I was about to show you, which shows how this rover was deployed at the Perseverance rover site. It is at the place called Jezero crater, and you can see these delta deposits. So here, which you can see on Earth, you have these rivers. These rivers carry sediments for them, and these sediments become extremely heavy, and you see these delta shaped forms right here on Earth. Same thing is found on Mars. So Jezero crater is great to explore. Maybe there were ancient rivers on Mars that deposited sediments here, and so this rover has been exploring this area for a very, very long time. This is how Jezero crater looked like in the past, full of water. This is how it looks like now, and we have learned so much about this place and about past conditions on Mars using Jezero crater. Now here in our lab, we have collaborated with a chemistry lab here, and what we do is we simulate Martian conditions in the lab here. We have a replica of Martian soil because no sample has been returned from Mars so far. So by studying data from these rovers and landers, we have a simulant of Martian soil, Martian regolith. So we study organic chemistry by using different units on Mars, different types of soil on Mars, different types of organic substances, perchlorates, different minerals. We here study the surface chemistry of Mars by doing experiments right here on Earth, and then we try and understand what was going on Mars in the past, what is going on at Mars right now. So this is also really useful for us to understand the surface chemistry. I showed this to you earlier that there are so many features. On the left on Mars, you see these conglomerates, alluvial fans, paleo river channels, subcars, ripple marks on the surface of Mars. We see the same things here in the UAE. We go out in the field, we explore them. This In the middle, you see the Curiosity rover took this photograph. We have this famous fossil dunes area in Abu Dhabi, and so this place is a gold mine for Mars researchers, and we are trying to figure out whether Mars ever it hosted life, or maybe we can find signs of biological activity on Mars at the moment. But the thing is, even if you have a detection which could say probably there was life, it would be highly controversial. So the only way to explore Mars and look for sign of present day life or maybe extinct life is for humans to go there. And now different agencies around the globe are thinking very seriously about going to Mars. There are a bunch of private companies. NASA recently, earlier this month, announced an office Moon to Mars program where NASA is seriously thinking about going to Mars. UAE has a Mars 2117 program that UAE wants to establish a human presence on Mars by the year 2117. This is, you must be familiar with this movie. This is from The Martian. So our group is also involved in human exploration of Mars. Mars is bombarded by high level of radiation because it has no global magnetic field. Its atmosphere is extremely thin. So what is going to happen to the human body? What will happen to astronauts when they are in transit, going to Mars, landing there, staying on Mars, maybe even coming back? So how does radiation interact with the different organs of the human body? So we have used a tool which is used by scientists at CERN, the same collider which discovered Higgs boson. They study, charged particles, how they interact with matter at the most fundamental level. We have modified that code to work with the human body so that we can understand how this radiation at the most fundamental level interacts with the human body. Then we compare our results with different medical literature, and we will be able to figure out, whether going to Mars is safe or not, what kind of radiation levels astronauts will be exposed to, what kind of diseases they could face, how to mitigate those dangers through having more effective shields, by improving their diets or medication, and so on. And we recently published a paper on this study. This is going on. We have several students from Blue Marble Spaces, young scientist program. We are basically studying habitability in space. Um, we have a radiation map of the whole surface of Mars. We use data from this instrument called RAD, Radiation Assessment Detector, which is on the surface of Mars, operating for more than a decade. And when we calibrate all our calculations using data from this detector. There are future missions. So on the left, you can see this ExoMars mission. It was supposed to be launched last year in 2022. It was a collaboration between the European Space Agency, ESA, and Roscosmos. But because of sanctions, the mission was cancelled. But ESA now is partnering with NASA to launch this mission in 2028. The best thing about this mission is it has a drill which is capable of drilling almost 2 meters deep. So, as I told you, the surface of Mars is high with radiation, it has perchlorates, it is extremely cold. So, life is most likely below the surface where conditions are more optimal. And subsurface area has not been explored on Mars at all. So, this mission is going to take those samples and study them. And this is our best chance of looking for signs of life. It will be launched in 28. NASA has another mission called Mars Life Explorer, which will go in the mid 2030s. It also has a drill capable of drilling 2 meters deep. NASA and ESA have a joint mission called Mars Sample Return. It will go to Mars in 2031, land there, pick up samples, and bring them back to the Earth in 2033. This is the first time we are going to have samples from Mars. We will then be able to study them with the most sophisticated instruments and study Mars in great detail. China also has announced a similar mission with the goal of bringing those samples in 2031, 2 years before the NASA and ESA's mission. So you will see. And there are crewed missions right now being planned, most likely in the end of 2030s, 2040s, who knows. So overall, it's a very exciting time. And the reason this research on Mars is most important is not only we'll be able to understand how a very similar planet to the Earth, what are its conditions, how it evolved, whether life evolved there or not, is now we have thousands and thousands of planets beyond the solar system called exoplanets. And the main question about these exoplanets is whether they have life or not. And these planets are in similar systems. So you must have heard of this TRAPPIST 1 system, which is 40 light years away. It is very, very small system consisting of a number of planets. It looks, reminds you of the solar system. And so the question is, we have so many systems now. Are any of these planets habitable? How to find them, to develop a basic understanding and an understanding at the fundamental level. Are these planets capable of hosting life? Is this life native to the planet, or was it delivered from elsewhere? What makes a planet habitable, and how to identify such planets here in the solar system and beyond in case of extrasolar planets. And on the top, we now have a fairly good understanding on how Mars, which was very Earth-like, how it evolved into a dark and dry and cold planet as we see now. What is going to happen to the Earth? So we'll be able to figure that out. Uh, this is the Mars exploration family portrait. So I would thank all these mission teams, all the space agencies for investing so much money in all these probes, which has taught us so much about Mars, which is still teaching me and all my group members every day new things about Mars. And before ending, I would just like to share this latest map of Mars. So this is a photographic map of Mars taken from data from the HOPE mission. So more than 3,000 observations from the HOPE mission were combined together to form this first. So this is the first realistic photographic atlas of Mars that you're going to see. The other atlases use false color images. These are the actual real color images of Mars. You can download this map along with others on this website marsatlas.org. And thank you all so much for organizing this. And I'm open for questions. And I'm sorry about the delay early on with the slides. You are muted.
Oh, okay. Thank you for your presentation. No problem. It can be, I mean, it's okay. So I can start with the questions. First question: is there any possibility for Earth can transform that way, like losing atmosphere and becoming desert like
Mhm.
the way Mars has done?
Yeah, really good question. And so, in the short term, the answer is no, because Earth has a significant magnetic field. It can deflect these charged particles. The only way charged particles can enter, the Earth's atmosphere now is in the polar regions. There is some escape, but Earth also has, very Earth is a very active planet. It's geologically active, and through these processes it also generates a lot of gas. It replenishes the atmosphere. So in the short term, no, Earth is going to stay. There will be, because of more CO2, there will be climate change and so on. But there is no way in the short term it can become something like Mars. But in a long term, in the future, you know, on Mars, what happened is Mars is much smaller, it is much colder, so it's dynamo which generates this magnetic field. The core cooled down, its dynamo died, and so the magnetic field died. Maybe same thing would happen to the Earth, in far, far away billion year time scales. It could happen that our dynamo shuts down, we lose our magnetic field, and so Earth also starts losing the atmosphere and maybe becomes dry like this.
Okay. A second question. General design of rovers are based on going on small hills and flat surface. Is it possible that we are missing out some of the information we could have learned with different vehicles?
Yes, yes. So the rovers are designed to last for a really long time. First of all, they are very, very expensive. These are, billions of dollars are spent in these missions. It takes, teams 10 to 15 years they have to spend on the mission, from the conception to design, going through all the reviews, funding, then getting the actual equipment design, then launch. It's 20 25 years of investment on these missions, so people want to land them in very safe places where it can operate for a long time. And there are many places. For example, I showed you, there are volcanic regions, there are hills, there are valleys. So there are huge valley called Valles Marineris on Mars. It is, several kilometers deep, and it's a very exciting place. And so there can be probes. So maybe, Turkey can send a probe. All of you are
I
young.
hope.
You should, uh, you should plan a mission going to all these, exciting places, and hopefully we'll learn many new things which have not been explored by these vehicles. Going to polar regions, we have not explored polar regions by these rovers. There now, you see this small Ingenuity small, probe which can fly on Mars on small flights. Maybe we can have similar things in future, similar probes which can fly to different destinations and explore different things, and they are going to teach us new things.
If we can go to Mars, how likely is it that we will create habitats similar to deep cave ecosystems like on Earth?
Okay, so deep cave ecosystems on Earth in some places. So, for example, there is a place in South Africa. It's a gold mine, and if you go 2.8 kilometers deep, there is a very unique ecosystem. Obviously, there is no sunlight there. It is 2.8 kilometers deep. There are traces of water there. There's hardly any oxygen, but that area is rich in radioactive rocks, uranium, thorium, potassium. So alpha, beta, and gamma radiation from those rocks interact with that, the surroundings. It interacts with, traces of water, and it produces food which can be used by microbes. So there is a bacterium which thrives in that environment. It just lives on that. If we bring it out, expose it to, maybe room temperature, it is going to die. It lives there. And so there is a good probability that there are deep cave ecosystems on Mars similar to the Earth, because Mars also has similar rocks, similar minerals. This bacterium, which I mentioned, it operates by using sulfate reduction. Sulfate reduction is also possible on Mars. It has similar chemistry. So there are many such types of deep cave ecosystem which could exist on Mars. Really good question.
Okay. How to catalyze organic activity with GCR?
Yeah, so galactic cosmic rays are, high energy charged particles which are coming from all over the galaxy. So solar wind is just coming from the sun. These particles are much, much lower in energy. Galactic cosmic rays are much higher in energy. And when they interact with organics, they destroy them, obviously, on the surface. But the idea is, and I have proposed this idea, that below the surface of Mars, these galactic cosmic rays can interact with surrounding environment. And just like you see in deep cave ecosystems, this radiation is producing food through sulfate reduction. Maybe galactic cosmic rays can also, initiate some sort of chemical reactions, which could be useful for life. So this is, one of the things. And so galactic cosmic rays are really harmful on the surface, but below the surface of Mars, they could be. useful. They will obviously degrade organics, but they can also aid in some kind of biological activities still to be tested out.
Okay. Has there been a decrease or increase in mass since the existence of our Earth?
So the overall mass of the planet is pretty much the same. The only difference is the mass of the atmosphere, which has decreased over a period of time. So Mars is, much further away from the Earth, from the Sun. So it is much colder, obviously. So in order to for it to sustain liquid water on the surface, it should have, thick atmosphere with greenhouse gases. Now you don't see it, so obviously the mass of the atmosphere have become less. But the overall mass of the planet is, the same.
How was the effect of cosmic rays on Mars? How did this effect manifest itself?
Okay, so as I answered earlier, Mars is constantly bombarded by these cosmic rays, and the surface is therefore it's a high radiation environment. On the surface, if you put organic substances by galactic cosmic rays, by high amount of solar UV radiation, organics will be degraded really quickly. Okay, but
Okay.
there is, something else going on which is preserving these organics, and which is what we are trying to understand here in the lab, that we are simulating Martian condition. We are using different types of organic substances, different types of minerals, to understand whether, some of these substances can sustain themselves even in harsh Martian conditions.
Okay. Do we can transfer ocean water from Earth to Mars and check what's happening?
Yeah, this is a good, thought experiment, that, if we just take, a large amount of water and dump it there, especially the Northern Ocean, it will be full of water. All the valley networks, it will be full of rivers and so on. So yeah, it can be done. But the thing is, do we actually want to, completely change the pristine environment of another planet? What right do we have to completely transform a planet? So from my point of view, Mars has surface which is 4 billion years old. Okay, so we should study it so well, because we don't know what was going on 4 billion years ago on Earth. So we can, study that. Maybe it will give insights into our solar system 4 billion years ago, tell us about something about life on Earth, for example. And so we need to study that. It's a pristine environment, but once we change it, then it's gone forever, right? Then we cannot, even if we find, signs of life, then it could be, human contamination. Who knows, when we actually go there and you find, some bacteria, it could be, contaminated by us.
Yeah. Okay. And next
Yeah.
question from same person. Can we
Yeah.
transfer bacteria that cellular mechanism work with sulfur to check what's happening?
Yeah, so this can be tested in, I don't think this is going to happen in the near future, but when, astronauts are actually going to Mars, then they'll be able to carry out the more and more such experiments. So one thing about these rovers is that they are extremely slow. For any kind of simple experiment, they can take days and days. Plus, their capability is highly limited. So when astronauts are going there, they can do all sorts of experiments. They can do them quickly. So one of the thing is, you can take these extremophiles and you can, expose them to Martian conditions, and you can see how they behave. So one such experiment is right now going at the International Space Station, which I think Zainab is now on the space station. You can see her. Uh,
Yeah.
just,
My
so just
background.
out, so just outside the walls, you have these microbes which were transported from the earth. And so how do these microbes behave? These microbes are still alive at such cold temperatures for months and months. They are there. So how are they reacting to it? Same thing can be done on Mars, and see what kind of mechanisms they develop. Maybe they can use some kind of sulfate reduction technique. Who knows?
Okay. Uh, One more question. Do you think we can convert carbon dioxide on Mars into oxygen, or should we create a space with oxygen in a carbon dioxide atmosphere?
Mhm. Yeah, so this so on the Perseverance rover, which is the latest NASA's rover on Mars, there is one experiment used to which the main aim is to generate oxygen there. And this can certainly be done, because especially for future missions, you need to be able to generate your own oxygen, especially in a confined space. And so certainly that can be done. It has to be done in a confined way, right? Otherwise, oxygen is all going to escape, and we are going to alter the atmosphere of Mars forever. So we don't want to do that. We want to keep Mars in as pristine condition as possible. But we should have an oxygen atmosphere inside human habitats, just like what we do in case of International Space Station.
Okay. Our last question. Some of the vehicles sent for missions to Mars cannot return to Earth. So, what happens
Mhm.
to them there?
So nothing has been returned to the Earth so far. So everything that you see from the 70s, which has gone to Mars up till now, it just stays there. So orbiters, even when they die, they are orbiting around Mars. You can see them. There are landers which they have stopped communicating. You can see them right now with there are orbiters right now. They take high resolution images. From these images, you can see they are still there. So they just stay there.
So, we have so many space trash.
Yeah. So the Mars is the only planet which is now inhabited by robots, right? These are all
Yeah.
robots. Yeah, they rule the planet.
Maybe in future, like science fiction movies, we can collect those trash and then sell.
Yeah, why not?
Okay, so thank you. We are all done with questions.
All
So
right. Thank
I'm
you
so
so
sorry
much.
to say you goodbye, but we are so thankful to have you here. It
All
was
right.
really
Thanks so
amazing.
much.
Okay, see you. Bye bye.
See ya. Bye.
We will continue with our next guest, Dr. Sheri Jensen, but we will give a small break at 2:30 p.m. We will see each other again. See you. Bye bye.
We continue the session with Dr. Sheri Jensen. She is a linguist who teaches in the linguistics at Bowling Green State University. Her research interests include linguistic components of extraterrestrial message construction, social aspects of human space colonization, disability studies, the relationship between language, embodiment and thought, and ways in which alternative sensory input could influence the evolution of scientific and advancement and cognition in potential extraterrestrial intelligence. Hi, Dr. Sheri, how are you?
Hi, I'm great. How are you all? It's very early here.
Thank you for asking. I am very excited, actually, but I hope I can handle it. I tried to introduce you, but I know it's not enough for your successful life. Do you want to add more details about yourself?
Sure. Right now, I am in Washington, D.C. I come from Bowling Green, Ohio, which is a very small town, but I'm now in the capital of the United States, Washington, D.C., and I'm working on questions about disability and spaceflight. So right now, there are a lot of rules about who can fly, who can go to space, and they're all based on, a lot of them are based on your body and what your body is like. And if you have any kind of problem, any kind of disability right now, the answer is no, you cannot fly. And that's not necessary. So we're working on what do we need to know so that we can open space flight to everyone. So that's our project. We know that right now there is one guy at the European Space Agency. His name is John McFall, and he has a one-leg prosthetic. He has had one leg amputated, and he is now in their astronaut candidate program. So he might fly. The European Space Agency does not say that he will fly. They're not promising that, but they are investigating how that's going to be possible. And that's some of the work we're doing over here as well. We don't have a disabled astronaut like Europe does yet, but we're working on it. So that is some of the work we're doing, and we're doing all kinds of research to make that possible. And one of the things that we're doing very soon is an analog mission. And in case you're not familiar with that word in English, an analog mission is where you do everything that you would do if you were on a real mission, except you stay on Earth. So we will be doing 6 days in a sealed habitat, and it will be like we're on the moon, except for the gravity, but we won't be on the moon. We'll be in the desert in Arizona. So we're going to use that mission to study some things about, I'm blind, and so we're going to be using that analog mission to study, what do you need to know if you're blind and you're part of a crew in space? How will that go? And what can we learn from testing it out? And we will have one EVA, each of us. So I'll put on a spacesuit and I'll go out and I'll walk around in the desert with the spacesuit, just like it would be on the moon, except for the gravity. And we have a lot of studies and experiments that we're going to do, and we'll just see where it goes. I'm very excited to be there.
Thank you. It was great to be with you in this session, and I can't wait to listen to you because of your interesting title. If you want, you can start your presentation.
Can you tell me how I share my screen? Because that's a thing that I'm going to need to do.
There is a present button.
A present
You need
button,
to click
okay.
on it. And after share your screen.
Okay, I'm hitting the present button. And then we get a little dialog box.
Slides. Video file 2 of 4. Horizontal 3 of 4. Share screen 4 of 4. And a list.
Uh,
Video file 2 of 4. Slides 1 of 4. List 4 items. End of complimentary. List 4. Slides. Video file 2 of 4. Horizontal 3 of 4. Share screen 4 of 4. Modal dialog. Modal dialog. Modal dialog. Modal dialog. Screen sharing text. List 3 items. Screen sharing workshop. Some screen lit. Follow these steps. Link to share video with audio. And a list. Don't tell them text again. Uncheck. Share screen. Share screen. Press share screen. Home busy.
Oh, I'm sharing my Chromes. Okay, I think. Please let me know if this is working or when this is working. If you won't have to look at my smiling, sleepy face, you can look at my exciting computer screen, which means I should probably, I'm so sorry to be doing this while.
End of complimentary. Chat tabs group. Complimentary. End of main. Link issues. Leave studio. Link.
So, did that work? Can you all see my screen?
No, I can't see right now.
Oh, that's interesting. I'll try it again. I'm so sorry.
Leave studio. Link.
No problem.
Present. Mic and camera settings. Modal dialog. In modal dialog. Close modal.
Okay, I can try to help you.
Thank
Um,
you.
Camera.
I'm Zainab, by the way.
Yes, I know.
Audio tool free.
You can press the present and then you can try to press share screen.
And list.
You can click that, and after this,
camera.
entire screen.
Okay, 1 minute.
FaceTime HD camera. Camera resolution. Standard definition. 180. Mirror my camera. Unchecked.
It's telling me things about my camera that I don't need to know.
Maybe your Chrome settings are not allowing to share. Sometimes it's happening.
Oh.
You need to give that permission I'm not sure how to do, but sometimes those settings are not allowing to share.
Oh. So I sent you the URL for my
Yeah,
presentation.
I can share.
Can you do it?
And you can say me to go further, and I can
That would
just
be
pass.
great.
Okay.
That is
Okay.
the safety mechanism.
Yeah. Okay. So wait a minute, please.
Well, I'm glad we can do this way.
Yeah, I can do that. Is there any audio on that? So I will allow the audio.
There's no audio.
Okay. Okay, so I think everyone can see now.
Okay, so the first screen there should just have my name on it, and
yeah.
Okay, perfect. So and I'll just tell you, Zainab, thank you. I'll just tell you when to hit the next button, if that's okay.
Wait a minute. I think I need to remove.
And I've just lost your audio.
Okay, I will stay on the screen because if I go back, you cannot hear me.
Yes,
I will stay here.
I think I want to hear you.
Okay. Okay, so I'm starting. We are at the first page now, communicating with ET.
Okay, good. So I will just tell you when it's time. So this is so much different than the last presentation. This is a whole universe away from the last presentation. It's so different, but it's really important that we do this work now. So one of the things that people always ask me is they say, "What? You are a crazy person. Why are we talking about communicating with aliens when we don't even know if there's life on Mars?" Right? We're talking in our solar system about the possibility of maybe a little tiny patch of green moss or something, right? Hi, puppy. We're not talking about anything big like a puppy.
Yeah, he's sick. That's why sometimes he's just barking. Aww. I'm so sorry.
No, he's okay. He's a good dog.
Yeah.
So we're not even talking about anything as sophisticated as a dog in our solar system, right? We're just talking about maybe some tiny little microbes. So why do we talk about communicating with an intelligent being? And this is the reason. It's not that we think that there are intelligent beings on Mars, right? We just don't know. We don't even know if there are any intelligent beings anywhere in the universe yet, except us. We have no idea. But part of this is that you have to get ready, right? You can't pretend like everything is fine and you need to do nothing. And then all of a sudden, boom, there is an intelligent species. And all of a sudden, you've not practiced. You have no science developed. You have no theories about what this will be like. You're just completely lost. So it would be irresponsible of us to do nothing. So even though we've got nobody out there to talk to right now, we are practicing with the ideas of how to send a message and how to decode a message. So that's kind of why. Also, by the way, we have sent many messages into space by radio already. Some of them are just silly, like there was a Doritos commercial that we sent in 2011. And some of them are more serious attempts to communicate. Messaging Extraterrestrial International has sent some serious messages, and they're all by radio signal right now. You could use lasers. We've started to think about that, but right now radio and lasers are our two choices. And one of the problems we have, of course, is that these messages move at the speed of light, which means that even if we get very, very, very, very lucky, and there are intelligent beings on Alpha Centauri, which is 4 light years away, our little message would take 4 years to get to them. So think about how sometimes you get nervous because you say hello, and the other person does not say hello. You say hello, and they go, oh, hi. And that feels really, really awkward, that pause. Imagine a pause of 8 years. So I say hello, my message goes to Alpha Centauri, they hear it, they figure out what it means, and then they say hello back. Minimum 8 years. So that's one of the problems that we have with communicating between civilizations is that if we do get a radio signal, and I'm not going to talk about how difficult it will be to find the radio signal. That's too much for one presentation. But if we do get a radio signal, the pace of our conversation will be excruciatingly slow. It will be terribly, terribly slow. But we have a worse problem than that. So our first problem is it's slow. Our second problem is that we have no context for what we're doing. When we interact with each other face to face, it's easy. We're in the same room. We have a lot of shared things. Most of us can look at each other. Most of us can hear each other. We share a language, easy peasy, no problem. If we don't share a language, that's still pretty okay. So if you speak Turkish and I speak English and we don't share any language, I can still communicate with you. I can still smile at you. If you're sad, I can still take your hand. If you need something, you can point to it. I can still get it for you. If you want to teach me how to speak Turkish, you can do that, because if I want to know what something is, if there's a dog there, you could say dog, and I could say, oh, dog, and we can share, we can learn the words, right? And the reason we can learn the words is that we're with each other, and it's relatively easy. That's how humans have done it for years. Okay, but this is not going to be like that. One of the problems that we're going to have is that the conversation is very slow, and it's going to be all done by radio. So we cannot share pictures because the rules for encoding pictures are really complicated, and we don't know that they will know how to decode our pictures. Also, the idea of a picture is not the best communication tool. So if I send you a picture of a dog, and then maybe I record a word, I write a word, you don't know what that word means. That word could mean dog. That word could mean loud. It could mean friendly. It could mean furry. It could mean cute. It could just be a sign that means hello, or it could mean danger, or it could be that you think this is a scary dog, and so you're trying to be threatening, or you think this is a friendly dog. So pictures with single words are a big problem. So other problems that we're going to have, there's so many problems. Other problems that we're going to have is we don't know what their world is like, right? We don't know what their bodies are like. We don't know if they look at things. Do they have a sense of sight? We don't know. What kind of artifacts do they have? You can't, for example, use a cup. That's an easy thing to do for human-to-human communications. Look, here's my cup. No problem. But will they have a cup? Would they recognize a cup? Do they drink? They probably do some kind of taking in of liquids, but how do they do that? Are there cups? We don't know. So the only thing we know about them, the single only thing that we're going to know about these people who receive our message, if they receive it, the only thing we're going to know about them is they have something like a radio telescope. And the reason we know that is that they received our message. So this is a huge problem, right? All we know about these people, we don't know if they have arms and legs. We don't know what their world is like. We don't know if they're peaceful. We don't know if they have 3 heads. We don't know if they fly. We don't know if they swim. All we know is they have this radio telescope. But that's a lot, honestly. That's quite a bit to know. That's a good start, because to have a radio telescope, you have to build it. I mean, there is kind of the unlikely, super unlikely, but who am I to say, possibility that they just are sentient radio telescopes, like that they somehow grow radio telescopes in their bodies. I don't know. It's a weird idea, but one of the things you have to do when you're thinking about aliens is you have to imagine everything. So anything you imagine about an alien, you're not wrong, because we have no data yet. So you could be exactly right. So all we know about them probably is that they have this radio telescope. And what we can assume is that they had to build the radio telescope, which means they've done some things. They figured out radio. That's kind of cool. It's weird to the only thing you know about another living being is that they have built radio. They understand radio. That's a weird only thing to know about somebody. You meet somebody in the parking lot, and maybe the only thing you know about them is, what kind of jacket they're wearing. Or maybe maybe they have a T-shirt that says something. That's the only thing you know about them. Or you might know, that they're alive and that they're human. But the only thing we know about these guys is they know about radio, which is weird. But to know about radio, you have to know about math. So that's kind of a good place to start. So if we know about math, we can use math to communicate. We can use math to build a language. And when I say that, I don't mean that thing that people sometimes say when they say, oh, music is a language, or oh, love is a language, or oh, other things are language, which are not language. I mean a real way that you can make sentences. Love may be a language, but that does not say, I would like a sandwich and I would like cheese on it, and I would like you to bring it to me at 3:00 this afternoon, and I will pay you for it. Like that stuff is language. Being able to communicate really specific things is a language. Music is a form of communication. It's beautiful. We all love it, but it's not a language. Right? So what we're talking about here is the ability to eventually say to each other, hi, we exist, we're alive, and we live on this planet, and here is what our science is like, and here is what our religion is like, and here is how we care for each other, and here are our problems, and here's what we worry about. That kind of thing. And then, and things like, hi, I'm going to send you another message on Thursday, like in 3 days. Is that going to be okay with you? So that's the kind of stuff that we want to communicate. So we want to take math, which is the only thing we know about that they know, and we want to use that to be able to tell them things about ourselves, what we look like, what our biology is like, anything we want, right? Anything. The idea of a language is that it's flexible and it can say anything you want it to say. Just like I can say anything in English, I can say anything in Turkish. I want to be able to say anything in math, including things like, this is dangerous, this is nice, I will send you another message next time our planets are lined up. So that's a lot to ask, and it's a building process. So what I'm going to show you today is a way to get started with a language built out of math. And so in the early 1960s, a Danish philosopher named Hans Freudenthal created a very complicated system that he called Linkos. And his idea was exactly this, that we could do math. He wasn't the first one to think of it, but he wrote 3 volumes of this math language, and it is dense, my people, and it is it's a lot. I tried to work through his language. So I thought, okay, fine, I'll start like I'm an alien. I'll start on page 1. What does it say? I got lost very quickly, and that's okay. One of the things about communication between people, even people who understand one another, is that it's really easy to get lost. You get it wrong. So as we move through this, we're going to slowly build hypotheses about what we're trying to say, and we can be wrong, right? And if you're wrong, you get to the end of the message and you have the wrong idea, or nothing makes sense. One of the things we do about that is that we have the idea that we want as many people as possible to be working on this. So if we get a signal from another planet, the protocol says that we will share that with everybody. It won't be a secret. Astronomers are not good secret keepers. They're very excited about what they learn. They will not only will they tell us because they're excited about it, but that is the agreement that we have made. That the observatories will share the signal with each other, and then once they're sure that they have something real, then they share it with everybody. Okay, and so we will work through it, and you'll like, oh, what does this mean? What does this mean? And then if you're wrong, that's fine, right? And then we might. So the idea is that we all work on it. We get to the end, and we hopefully have a message, and we think, okay, do we agree? Is that our best hypothesis? Okay, so how do we do it? One of the things we know about radio is that you can make beeps with it. You can inflect the radio signal so that you can make ones and zeros. You can go deet, deet, deet. We all know that's easy to do, and it's easy to detect. So in a second, Zainab is going to hit the next button. And
okay, I'm pressing next. Yeah, we are at the second page.
Perfect. So I don't know how you guys want this. Maybe you could throw your answers in the chat, and Zainab can be your spokesperson, or maybe she'll be like my student or something. I don't know what is best to do here. So to make this interactive, however you want to do it. So the first question is, these little dots on the screen here, they indicate beeps. Just each little dot is a beep, beep. So can you tell me what this screen, can anyone, or Zainab, I don't know how you want to do it, tell me what the screen means? Like, what do those beeps mean? What is the screen doing?
Oh, I don't know, just beep, beep, beep, and beep.
Yeah, it's just beeping, but like, what is the difference between, like, what do you think the first line means, and then the second line?
Because they're different, like codes. Like some of them have 2 or 3 dots, like 2 or 3 beeps, but some of them have lines like 2 or 3. So even some of them are, longer. Some of them are smaller.
Can you go back a screen, Zainab? The first screen should be just dots.
Dots, yeah, okay. Oh, I couldn't go back. There is just the next button.
Okay, you can go all the way around. It will go all the way around.
Okay, I figured out. Okay, so I'm at the first page. Yeah.
Now we have just a dot, and then we have. So what is this? What are these dots doing?
I don't know. Really, they are like a Morse alphabet.
Yeah, so like you've got one dot, right?
Yeah.
And then you got 2 dots.
It can be A, and then 2 dots can be B, something like that. I don't know.
And then you got 3 dots.
We give the code. Yeah, 3 dots, 4 dots,
and
5
then 4
dots.
5 dots,
yeah.
6 dots.
Yeah.
So you're counting, right?
Yeah.
So you can beep, beep, beep, beep, beep, beep, beep, beep, beep. So you've learned to count. So we've already now we have established numbers.
Okay.
So or I mean, and it could be anything, right? But we just have to make a hypothesis. So we're going to go, okay, cool. We've those look like numbers. And the classic thing is that they would send prime numbers. That would be, and I could have done that, but this is easier, I think, to understand. This 1 dot, 2 dots. So, 1 dot means 1, 2 dots means 2, 3 dots means 3. Okay, cool. So now we've established numbers. Now go to the next screen, if you would.
Okay, I am at next screen.
So now we have dots, short dots. We know those are numbers. So any combination of dots there we know is a number. And then we've got a short line and a long line. Yeah. So then what we're going to do is we're going to look at those dots and look at those lines. And by looking at the numbers, can we tell what those short line and what that long line has to be? We've got a short dash and we've got a long dash. So let's see if I can. Oh, I don't have my exact numbers here. So if you make a hypothesis, if you read the first line, I'm going to have to pull mine up here because I've got the wrong thing open. What if my computer will let me do this?
Okay.
Basic window. Jensen. University. Start again. Start again. Contact. 1. Contact. 1. Contact. Dr. Will Jensen. Start again. Link.
Okay.
Start again.
So that's I'm just showing I'm looking at my own numbers here.
2 items. Website not secure. 2.
Okay.
2. Communicating ET. 2. 2. 2. Out text. 2. 2. 2.
Shoot, it's not letting me look. Let me look at my own screen, you doggone computer. Hang on 1 second. The computer is very, very unhappy with me right now.
It's okay.
Communicating ET. 2.
So,
2.
Almost there.
2.
Seriously, what's wrong with you?
Forward. Sidebar. Private. Add page. Not secure. Wait. Reload this page. Collection. Tab overview.
Oh, I see what's happening.
Share. Reload this page. Out toolbar. Tab bar. Vertical. Windows basic.
2 seconds.
2. Contact. 2. 2. 2.
Seriously, not gonna let me look at this. Okay. So if you look at those numbers, what do you think the short dash means, and what do you think the long dash might mean? Poor Zainab, you're like on the spot here in front of everybody. I feel bad. Can people help you in the chat, or is that not easy to do?
Out text. 2.
Come on, let me look at my own screen. I'm so sorry. So if you have like a 2 and then a glurk and then a 3 and then something different and then a 5, then your question is, what does that first thing have to mean so that this whole first line makes sense? 2, 3, 5. That's the question that we're trying to ask here. It's like a logic puzzle. And again, I'm trying to look at my own numbers. I'm really sorry that I can't do that. I don't know. I don't understand why. Oh, I know what to do. Hang on.
Okay.
So I can be helpful. Instead of just tormenting you, I can help you. 1 second.
Open. Move to trash. Open the second ellipsis. Firefox. Google. Microsoft. Notes. Skype. 8. Text edit. Ellipsis.
Come on.
Text edit.
Here we go.
Text edit.
Okay. Okay. I'm in a better position to be helpful now.
Okay.
Okay. So we take each of those lines as like a sentence or a math problem, right?
Mhm.
So the first line, so separate them out. You feel like, imagine that you're making a space between lines. So the first line has dot, dot, dot. So there's 3 dots, and then something, and then 2 dots, and then something else, and then we have 5 dots. So if you can imagine what you can put between those numbers to make that line into a math problem. So one of the things I can do is I can imagine that small dash is a plus sign.
Yeah.
And then I can imagine that long dash is an equal sign.
Yeah.
Right? So I could say, oh, 2 plus 3 is 5. Haha, okay. Now I've discovered what I think it might be a plus sign and an equal sign. But I'm not totally sure because I've just seen one piece of data. So I'm going to look at the next line and just test my hypothesis. So I've got a 2 and then a dash. Maybe that's a plus. And then I'm going to count these dots. 1, 2, 3, 4, 5, 6, 7. And then, okay, so 2 plus 7. And if there's 9 dots here, 1, 2, 3, 4, 5, 6, 7, 8, 9. Ha! I win. So that's more data to show that, yeah, okay, so the small dash is a plus and the longer dash is equal sign, right? So this is not the meaning of life, right? This is not super, super exciting. But you did just discover a plus sign and an equal sign. And so now you're kind of on your way. So go ahead and click on the next one.
Okay.
And I'm able to help better now.
Okay. We are at the 3rd page.
Great. And I am getting mine open here as well. Okay, so now this is irritating to count dots, right? No one wants to keep going, ooh, dot, dot, dot, dot, dot, dot. So I went ahead and substituted numbers for the number of dots, right? So we no longer have to count dots. I'm like, okay, just assume there's 4 dots there. I'll just give you a 4 because we've already learned that. And I've substituted nonsense words for those hyphen and the long hyphen because it's just easier that way, right? Because we're going to make up a lot of words, and so it's just nicer if we don't have to count dashes. Okay, so some of these will look familiar. So the first thing we're going to do is we're going to look at the. I got all my little words here. I got sag and vleep. I just made up those words. They don't have to. The word itself doesn't have to. The sound of the word doesn't have to mean anything. So our first line here is 5 sag 2 blar 7. This is exactly what we had before, except that I've swapped in sag for the plus sign and blar for the equal sign. Okay. So we can make so our lives have gotten easier a little bit. So anytime you see sag, that's going to mean plus. Anytime you see blar, that's going to mean equals. And so we're just gonna make sure that that's true. We look at the second line. We got 9 something 4 something 13. So yeah. Sag is plus and blar is equals. Cool. Okay. And so we can keep going on. We can keep going and check our we can check our hypothesis. But now on the third line, we've got 3 plus 2 plus 4 is 9, right? So okay, we're good. We're doing good. We're still happy. And then there's another one. Just enough so you can just lots so you can just keep checking your hypothesis. That's one of the things that you would do in sending a message is that you would make it redundant. You would keep going and going and going, saying the same thing over and over so you have enough examples that that the person would understand. So in the next little group here, we've got 1 plus 1 is 2. That looks fine. And then we have 1 plus 1 something equals 19. This is one of the really important words to create. We've got blar, which is equals. It's kind of like is, right? We've kind of invented the word is or same as. And so that ick there, Zainab, I hate to keep putting you on the spot, but do you have an idea what that ick could be?
I don't know, but I just figured out C is just multiply.
Yes. Okay, good. That's right. So C is multiply. That's fantastic. So this ick is important. We got C is multiply. That's cool. Do we have any? I wish we could make more people help you.
Actually, I'm now following the YouTube chat to check. If they are giving answers. Some of them were giving answer for the first question. Those dashes saying a space between the numbers or Morse code. They were saying like that, and then. That's it. They did not add anything else. Okay. But I think they are also trying to guess.
Yeah, good. Okay.
Yeah.
So Zainab figured out what the C is. That's multiply. We have plus and we have multiply. And we have a problem with ick. We don't know what ick is yet. So if you know what that is, throw it in the chat. And we also have vleep.
They are saying blar is equal, but we already figured out blar is equal, and sag is plus.
Yes. Yeah. Good job, guys. Yes. What about vleep and ick?
Yeah, vleep is just minus.
Yes, good. Okay, yeah. Perfect. So now we have plus, and we have minus, and we have equals.
It's not even power. I don't know what is that.
Yeah, it's weird, right? It's like something completely ridiculous, isn't it? Like these
1 plus 1 something is equal to 19.
Yeah. So let me offer you this hypothesis. What if it just means not?
Okay.
Because 1 plus 1 is not equal 19. I would give you a lot more of these before you don't have very many examples here. So that's how we do. So now the most important thing about this is that you've also made words, right? So you've made the word not. You've made the word same. Blar is kind of like same. You've made the word plus, which can mean like with, or it can mean and you've made the word vleep. You've made the word minus, or you've made the word without. There isn't anything really good that like multiplication means. I don't know. Maybe that means something in English or Turkish. I don't know what that means, but it's good math, right? And it's a thing that we're able to figure out. You want to go ahead and go to the next one?
Okay, I am at 4th page.
Okay, I'm opening mine. So this one, I think we might. This one I think we might zoom through quickly. I'm not sure we'll through. I just want to look. So like if I wanted to show that ka meant divide, right, which is the question on this screen, I would just have to make up an equation. I would just have to say something like 45 ka 5 blar 9. Right? I would just make that up.
Yeah.
And then if I wanted to show the decimal point, because eventually we're going to need a decimal point, right? So I mean, divide is also a really good word to have. It means put things into equal groups. That's a really complicated word. Like that's not apple or dog. That's a really semantically complicated concept. You've just created the word for take a set of things and put them into equal groups. That's kind of freaking amazing that you can do that in just what 4 slides. Right? And then the same thing with if you wanted to create a word for the decimal point, right? You would just, this is our list of, I also put our list of things that we know down there at the bottom. If you wanted to do something like with a decimal point, I mean, people can write their own, but go ahead and go to the next one if you would, Zainab, because we have examples.
Okay, I'm going to the next one. We are at 4.5.
Yeah, you can tell that I changed my mind while I was writing these, right? Because I'm like, I'm not going to renumber these. I'm just going to call that 4.5.
Yeah, for NIM 5.
Yes. Yes. Oh my God. Okay, I am totally gonna change. I'm totally gonna change the title of that screen.
Yeah.
Now. Thank you so much. That's amazing.
You're welcome.
Every time I give this presentation, it gets better. Thank you. Okay, so here are just my examples of for NIM and so one of the things that I should have been doing that I have not done in this presentation because it's kind of complicated is really teach them symbols for digits. Because this might eventually get a little complicated with the numbers after the decimal points, and you'll see why in a minute. So if that's bothering anyone, I mean, it should bother you. But we'll be okay. We'll be okay. Let's see. So I have my examples for NIM and I have my examples for COT. Okay, so go ahead and click to the next one.
Okay.
Presentations window.
We are at for NIM 6. Yeah.
So good.
Menu. Open.
Okay. Now let you guys look at that while I get mine pulled up here. Okay. So in this one, the first thing, this is one of the improvements that one of my students made to my experiment, made to this, because I had this boom. I chose to write boom this way. So this is just more examples of NIM and Ka here on the top. Okay, so when I first made this presentation, this was an assignment for one of my linguistics classes, and this is what, and I had boom like this. This is how I had boom. I don't think so. First off, my question is, what does boom mean, and why is this a bad way of doing it? This is a bad way of encoding this. It's not super logical, and it will cause me trouble later on, and it's not the most flexible way I could have created this. So anyway, before we fix it, what does anybody think that boom means here?
Boom is square.
Yes, it is. It's square. So we have 5 boom, blar. So 5 boomed. 5 boomed is 25, and 10 boomed is 100, and 103 boomed is, you do the math, right? It's my math.
Yeah.
My math is right. I checked it. But does anyone have an argument of why it was a bad idea for me to make a word that means squared? This is totally, that doesn't have to be your question, right?
I don't think so, because normally math has also that power. I mean, as a special name square. I mean, not power 2. We are saying just square, so it's another word. So we already made up that word. Why not someone else didn't make up that?
Fair. That's fair.
Yeah.
The thing that the easier thing, not the easier thing. This is the thing to do that made sense to me when I did it too. Like, why not? Let's have it squared, and we can have one that means cubed. But then I'm gonna have to have a different one that means fourth, and a different one that means the fifth. So another way I could do this is I could make boom just mean exponent, and then I could put a number there.
Yeah.
And then I saved myself a word, right? I've just got one word that means exponent. I don't need a squared word for squared. I don't need a word for cube. But you're exactly right. And again, I think I'm going to change my presentation slightly to make this boom, to make my first example mean like to the fourth or something like that.
Okay.
Yeah. So things are getting better all the time for me in my world.
Okay,
Okay. Go ahead and go to the next one.
Okay. So 5.
Yes, with no nims. Hang on, let me find mine. Okay. So here, let's give you guys a second to give everyone a second to look at it. Okay, so now things are getting faster, right? Now we're going to make a bunch of stuff all at once, because you've already got the idea, and now we can start zooming. So we've got 9 minus 9. So what does AB have to mean? That's our first one. AB.
Yeah. So it will be 0 because 9 minus 9 equal to 0, and 9 minus 0 equal to 9.
Exactly. So one of the things that I did wrong the very first time I made this assignment is I just put the number 0 here, right? I didn't make up a word for 0. I just wrote 0. And I can't do that because the way we have to remember how we're sending the signal. The way we're sending the signal is that each number gets a beep.
Yeah, they are dots. So we are counting the dots. Actually, we are not showing them with numbers.
Yes, exactly.
So we don't have dots, so we can say 0 without having that.
Exactly. It's like a space, right? There is no 0. So that was, I did my very first time making this assignment, I put zeros in, and I'm like, wait, you can't do that. That doesn't make any sense. Which is exactly the sort of struggle that we need to go through to make this happen, right? We have to go through like, oh, that was wrong. You can't do that. So there's my 0. We've invented the 0. We're good for us. We're doing a good job.
Yeah.
And so now we have this yo thing.
Yeah.
I don't know how you want to define yo.
I not identified because 9 divided 0 equal. I mean, we cannot divide the 9 to 0.
Right. So we've got unidentified, and that's a really important mathematical concept, but it's also a really important semantic concept, right? So we've got this word that means you can't do that, or that's impossible, or that's unidentified. That's a really complicated semantic concept. So hang on to that. We're just going to put through. How are we doing on time? Does anyone?
I think we have enough time. Let me check. To our time, we are at. I'm trying to calculate for you because we have in different zones. Here in Turkey, it's 3:15 p.m. So I'm trying to calculate for you.
Well, I just wonder how much time we have left.
Okay, so let me check.
I might need to skip some things. 3:15.
Okay.
3:15. I can't do that in my head.
Okay, normally we would finish it after 30 minutes, and also including question part. If we say 10 minutes for questions, so we have 20 minutes now.
Okay.
Okay.
Okay, so I have about 10 more minutes to finish this up before there's questions. Is that right?
Yeah.
Okay, cool.
No,
okay.
With questions, we have 30 minutes. For these slides, we have 20 minutes.
Okay.
Okay?
Okay. Okay, cool. So this next thing, I've got 3 nim, and then I've got this number 1415926. I could have gone on for a while. You might recognize that number. So then what does this do after the nim here have to mean? This is kind of a complicated one.
Yeah.
So you might recognize this number. This is all about if the aliens recognize this number, which they will. Again, if they have a radio telescope, they know math, right? So this number 3.141592635, on and on, should be familiar to them. And so they should know, because they built a radio telescope, that this number goes on and on and on forever, right?
Yeah, because this is P number, so it's going on.
Yes.
Repeating, yeah.
Yes. So this do has to mean going on and on forever.
Yeah.
And so so this word toto then is going to mean, it's going to mean pi. We say pi in English, right? So,
Yeah.
So now we have a word for pi.
Yeah.
And then I don't know, like, and again, now this next line, you just have to guess right. So you've got pi something, and here is my pi times something squared. So that boom 2 is squared, right? Because we've decided that we're not going to go boom. We're going to use boom as an exponent and then put a 2 there. So pi something squared equals something else. So that just relies on you knowing that formula or intuiting what that formula is. That this formula is going to be the same all across the galaxy, right? These geometric things, we didn't just make that up on Earth. If they've built a radio telescope, they've worked with circles, right?
Yeah.
So they're going to know that pi r squared is a circle. And so we don't, so that is that's going to have to just be a jump that they're going to have to make, a logic jump that they're going to have to make.
Yeah, that's diameter.
Yeah, right. Yeah. So the pi here is going to be the radius of the blue is going to be the radius of the circle. So we have pi times the radius squared equals, and so it's reef is going to mean circle.
Yeah.
I want to make sure we have tons of time for questions. So this next one, who I'm just going to give to you. This is.
Oh yeah.
I'll just tell you this one. This number who is just giving you it's just isolating the biggest number in this sequence. Like here's a group of numbers. This one tells you which one's biggest. So who just means biggest. So we've built. Let's see where we at. Okay, we're on number 6. So we've built quite a bit of stuff here. We've got 2 more slides, 6 and 7. So now we can start saying some things. We could really actually say some things.
Yeah. It's saying echo, and then ik.
Yeah, so
we didn't learn yo-yo.
So what? So like you could say that. So if you get a signal, then if you get a signal, and this is what they say. So we have the difference between ik and we have ab and we have yo. So this ik means not, and the ab means 0 or nothing, and the yo means impossible. Like those are 3 pretty complicated semantic words that it would take you. The difference between impossible and nothing is not something that I would ever teach an intro language learning student, right? That's hard. Like it would take a long time before I would learn. If I didn't have a dictionary, it would take me a long time before I learned these words in Turkish, right? I would be like, I got to learn cup and dog and cat and run and walk and now and yesterday. I've got lots of words to learn before I get this. But weirdly, these are some of the words we get first in this language. So if they say blah blah blah to you, that could mean a couple different things, right?
Yeah.
It could mean same. It could mean yes, or is. It's sort of it might be a little bit hard to figure out what blah blah blah means. But if you say something and they say ik back, they're basically just saying no. Like no, that's not it. Ik. And if they say yo to you, if that's the thing they send back, you're getting, I don't know, impossible, absolutely not, couldn't possibly happen, or maybe dangerous, bad. I mean, we would have to experiment a bunch to know what the heck they were saying. I'm going to skip the other one. Okay, so we go to the next slide, please.
Next slide, okay, 7th.
This is the last slide I have. And I wanted to show how you could go from, let's give you a second to stare at those numbers.
Okay.
In case that helps. So what I wanted to do here, was introduce the possibility of introducing some real world objects. So I can't hand them an apple. I can't point to a dog, right? I can't do any of that stuff. So I have to think, what is it in the real world that we share? What is it that we might be able to use? What do they have and we have that they know and we know that we could communicate by looking at numbers? And so this is just going to be a wild guess. Are they going to know what this sequence is? So some of you who are chemists might, or physicists, right, might think about these numbers and go, hey, I recognize this. So I got the numbers 1 through 8. And then I've also got these numbers that are increasing a little bit, but they're not increasing super regularly, and they're not super, and they're not round numbers, right? So this is 1 through 8. And then what I've given is the atomic weights of the first 8 atoms in the periodic table. There's no way for you to know that unless you recognize those numbers. So this is a way, again, in which our whole thing could go wrong, right? If they're like, what are those numbers? Like, well, maybe no one would ever think of it. But we're hoping that because we're talking about math and science, that they would go, oh, I bet that's hydrogen. Couldn't that be hydrogen? But couldn't that fa? Couldn't that fa mo? Like, I don't know what fa and mo might mean, but maybe one of them is like the atomic number. Maybe one of those means element and one of them means ways or something like that. I mean, I don't know, right? They'd have to get lucky, or they'd have to have a lot of people working on it. But that's exactly the problem we're going to have. So now we have words for hydrogen, helium, lithium, beryllium. We've got words for everything up to oxygen, which is useful because then we could do this thing, which is my favorite part of the whole presentation. Because now then at the bottom, you've got 2 Fa, which could be hydrogen, plus another hydrogen, plus an 8, atomic number 8, which is oxygen. So hydrogen, oxygen equals, put all those together, and we have a new word, zo, which has to mean water. And so now, look, we've taken ourselves from absolutely nothing to water. And from there, build whatever you want to build, right? I mean, there are some things that are going to be really, really hard. And there's sometimes when you're going to have to make extreme guesses. And sometimes you're going to be completely wrong. And we might never manage to communicate. And they might never think of the periodic table. My guess is that somebody eventually would. And they would go, oh, it's water, hello. And then we can start talking about chemicals. Once you can make molecules, you can talk about any substance in the universe, right? And then you can build anything you want to build from there. You can do some trigonometry. You can work out angles. You can work out weights. You can use your radio signal to determine measurements of time. You can talk about anything that you want to talk about. Now that you have this, you could work out a word for star by talking about having lots and lots and lots of molecules together of hydrogen and helium. You could show how hydrogen becomes helium. You could show how helium, how you break those things apart. You can show all these things. You can talk about energy. You can talk about anything you want to talk about. It's all slow. It's all tedious. And at any point, you could go terribly wrong. But that's one way that we could go from, I can't ever understand you, to let's talk about who we are and maybe establish a basis of, if not friendship, at least nerds talking about science together. I'm going to stop there and see if there are any questions. I'm happy to answer.
Okay. So I'm closing.
Also, Zainab, you did great.
Yeah, thank you. Okay, it was really amazing. I really enjoyed. Okay, I'm taking Banu here because Banu was hosting this session actually. She will help you to read all the questions and then you can answer all those questions,
Yeah,
okay?
Just read me whatever questions you have and I'm happy to answer.
Okay, Banu, you can start.
Okay, hi again. And
Hello.
if you're ready,
Yes.
if you're ready, I will start first question.
Absolutely.
Okay, the first question is, in your presentations, you say that we can agree on mathematics. What if the maths of those complicated creatures were different from the math we invited? How do we communicate there?
Well, so I think that's an interesting question. Like, can math be different? And so there are theorists of math who might imagine that there are some kinds of different ways to do math. But if there are, that's okay because we just taught them ours, right? Everyone is going to have some kind of counting, especially if they manage to build a radio telescope, right? If everything is so different there that they never build a radio telescope, then we will never communicate with them at our present level of technology, right? So, and you are right, they may never think of math, which I think would be weird, but aliens are weird, right? So maybe. None of this is guaranteed, but this is one way that we could do it. And it's also the reason why we walk them through it slowly, like there's a 1, there's a 1, there's a 1, there's a 1. So that if their math is different than ours, we can teach them our math, just like this.
Okay, thank you. And second question is, despite the possibility of encountering complex creatures like us, is it possible to produce a spatial communications language for these creatures?
So I don't know if we'll ever get all the way to language, right? I mean, we might. I don't know. One of the things that we hope for is this. So we are a very young civilization. We've just barely invented radio. On the cosmic scale, we are babies. We are such babies. We are little tiny babies, just sort of figuring out. We've only been to the moon a half dozen times, right? We are children. So other civilizations that we meet will probably be older than us, and they might have done first contact before. Like for us, it'll be, oh my God, there's someone out there that's amazing. For them, it might be, okay, there is another new intelligence. Okay, fine, we'll try to communicate. No big deal. It's good. So they might know more about how to communicate with us than we know about how to communicate with them. So just like we don't count on babies to teach themselves language on Earth, the adults sort of help them through that. Mostly, we are hoping, or it seems logical, that the other civilizations out there who have more experience will have already met someone before or been thinking about this longer, and so they hopefully will take the lead and make it easier for us.
Okay, and another question. Hi, Sheri. I follow you with much love and respect. I think we have a lot of learn from you. I am very curious about your success story. Could you briefly describe how you came to this point?
Let's see. I don't know. So it is, I think maybe you're asking the disability question. It is not the same anywhere on the planet for people who are disabled to do the things that, to get the same opportunities that non-disabled people have. We have the same capabilities and the same potential, but we need different things. So I was very lucky early in my life to learn to read Braille. That has made a huge difference in my life as a blind person. Learning to read is important, just like everyone else learning to read, right? If you don't have the opportunity to learn to read, that can make a lot of problems for you. So all of my ability to do math and science, I could have done it without being allowed to read, but it would be hard. Also, the very early education that I got was super important. So if you've got kids, when you have children with disabilities, they have to have a chance to go to school, and then they have to be treated with respect, right? So that when you get the disabled kids in school, you're not saying, "Oh, honey, touch the tree. Isn't that cute? You can touch a tree." Instead, you're saying, "Okay, my friend, this is an oak tree. How do you identify the oak tree? This is a maple tree. Learn to tell the difference. Here's your test. Get the answers right." So having high expectations. And so for me, it was that foundation that was really important. And so that's how I went from a small child in a little town. It wasn't just me being strong and brave and working by myself. It was everyone who was there to provide opportunities and education. And if you have, I'm happy to be in touch with folks individually if that's helpful also afterward.
Okay, thank you. And I want to say one thing. While I was researching about you, your story gave me a hope as well. And I continue with the question. Third question is, there is a possibility that we will encounter these advanced creatures in future. And for this, is it possible to make a separate research area and work on it?
I mean, I think people are sort of doing that. It's hard to study a topic when you don't have any of it to study. So we imagine what language might be like or what other kinds of thought might be like. And I think that's important work. But it's hard to do when you don't have any examples, right? It's hard to study life on Mars when you don't know if there's life on Mars. Once we find the life on Mars, we'll be able to study it. Once we find an alien language, we'll be able to study it. But all we can do right now is work on the problem, right? Is try to get prepared. So there are people around doing this work, but not very many. And maybe that's reasonable. I don't know. At some point, you sort of run out of things to say because, like, oh, yeah, we could make a language out of math. Okay, what else could we do? And it's important to keep those questions going. And there are scientists doing that, not very many, but you are right that we need to keep doing it.
Okay, thank you. And another question is, what would be the easiest coding for our language to be understood by another level of intelligence, or how do you choose the coding?
Oh, that's really hard. That's really hard. Coding is hard. It's a really hard question. So I don't think there's one right way. I think the best thing that we can do is to try to do everything in parallel, right? I have one good idea. Okay, I'll do that. You take the same message, you would code it your way. Someone else takes the same message, they encode it their way. Remember that we have 7,000 languages on Earth. So how are we going to even pick which one to use, right? There's no one best language. If we just pick it by numbers, the most widely spoken language on Earth is Chinese, and so we should do that. Or is that what we want to do? I don't know. Chinese is a good language. I don't speak it very well, but I could learn if I had to. We have a lot of questions about language because language is complicated. Math is much more simple.
Okay, thank you. I think this is our last question for you. If we encounter complex and advanced creature like ourselves, can we come to terms with symbols?
I'm sorry, I didn't understand the last part. Can we what?
If we encounter complex and advanced creatures like ourselves, can we come to terms with symbols?
With symbols? I think the only thing we can do is try and try again. If that's what if you're talking about encoding. But the other thing that I think is important to say is that we don't know what they're going to be like. We just really don't. And there are people who think that we should never send a message because maybe the aliens are scary and they will come and eat us and we'll all be dead. And that's a big risk. There is, as far as I can tell, really no motivation for aliens to come, to go to all the trouble and spend all the energy to come all the way over here to hurt us. We're a small planet. We don't have much stuff. If what they want is stuff, there's stuff in the universe all around. There's natural resources like crazy. So they don't really need our stuff. They don't need to take anything from us because we don't have much. And it's much easier if what you want is iron and uranium. We're not a good source for that, really. So I am an optimist, I guess. So I don't think that the aliens are out there to hurt each other. I could be wrong. And I hope I'm not wrong, but I could be wrong. So, but also we don't know what the best approach is. Like if we say nothing, if we never send a message, if we always hide, is that the wrong answer? Because maybe the aliens will come and help us. I don't think that that's necessarily the case either, right? I don't know that they'll hurt us or help us, but there might be things that we can learn from them. And it would sure be just a wonderful, joyful thing to know that the aliens are out there. And I think Jill Tarter, who works at the SETI Institute, said this the best. Just knowing that there's another civilization out there that's more advanced for us than us gives us hope that we can survive. Because right now, I don't know if we're going to survive. We are facing some pretty serious problems with global warming, with wars, with the natural disasters where we are not, we don't have the distribution systems we need to help one another. We are not kind to each other. We have a lot of problems. So will we survive as a species? I don't know. But if I meet another civilization that's done it, at least then I know it can be done. Like, oh, we can survive this. This is just a time when humans are struggling. But other species have gotten through it. Other species have survived. Maybe we will survive too. And that's one of the reasons that I do this work, is because of the hope that we'll meet someone who can tell us, yeah, my little friends, my little Earth friends, you can do it. Things will be okay. You can get through this because we got through it. And that's, I think, one of the most important reasons for doing this work.
I am agree with you, and our question is over. Thank you for your presentation, and it was a quite enjoyable.
Yeah, it was really enjoyable for me, actually.
You were amazing, and you guys have my email address. I'm happy to correspond with anyone who has questions about this,
Yeah.
or if you are, or you know someone who has a disability who you want to connect. I'm also happy to do that.
Okay, we will share your mail address on our chat so people also can contact with you.
Wonderful.
Okay. Thank you for your time.
Thank you, everyone.
Happy to have you here.
Thank you. Have a lovely evening, everybody.
Thank you.
Bye-bye.
See you. Bye-bye.
Bye.
Okay, guys, we will continue with our question and answer event, but it will be a few minutes later. We will give a small break, and then we will be here again. See you. Bye-bye.
Merhabalar arkadaşlar. Agenastro 3. Uluslararası Astrobiology Konferansımıza hoş geldiniz. Şu zamana kadar bütün oturumlarımıza katıldığınız için çok teşekkür ederiz. Bizlerle birlikte olmanız gerçekten bizi çok mutlu ediyor. Görüyoruz hepsini. Şimdi bu kadar çok sunum yaptığımız için sizinle böyle aramızda küçük bir soru cevap etkinliği yapmak istedik. Sorularımızı soracağız. Sorularımızı sorduktan hemen sonra cevaplarını da ardından tekrardan ekrana getireceğiz. Yani cevap vermeniz için yaklaşık bir 30 saniyeniz ya da 1 dakikamız falan olacak. Sözü Zeynep'e bırakıyorum şimdilik.
Evet, şöyle interaktif bir etkinlik yapmak istedik aslında. Sheri hocamızın interaktif sunumundan sonra biraz daha eğlenmeye devam edelim istedik. Berra soruyor olacak. Biraz böyle bilgi yarışması gibi. Sonra 1 dakika kadar bekleyeceğiz. Sizden gelen cevaplarda, yorumlarda üzerine konuşmaya devam edeceğiz. Sonra ben asıl cevabı söylüyor olacağım ve Berra da cevabı gösteriyor olacak. Şimdi etkinliğimizi ekrana alalım. Evet, Berna başlayabilirsin.
Tekrardan soru cevap etkinliğimize hoş geldiniz. O zaman ilk sorumuzu gösteriyorum.
Evet.
Aşağıdakilerden hangisi Mars'a gönderilen keşif araçlarının rover isimlerinden biri değildir? A. Opportunity, B. Perseverance, C. Spirit, D. Anxiety. Anxiety.
Anxious. Anxiety.
Aslında belli de biraz sanki.
Söyle bakalım. Anxiety. Anxiety.
Anxiety.
Evet.
Sizi böyle bir dakika kadar cevaplarınızı bekleyelim. Bir 49-50 geçe gibi.
Aslında bence şu an seyircilerimizin yarı yarıya joker hakkıyla elemiş olmaları gerek. İlk 2 tanesi zaten hocalarımız tarafından bahsedildi.
Evet.
Evet.
Değil mi? Dimitra Atri bahsetmişti.
Evet,
sanki.
dün de Opportunity'den bahsedilmişti. Spirit biraz eski ama seyircilerimiz doğru cevap verdi. Evet, Anxiety Berra'nın söyleyemedi. Öyle bir aracımız yok. Sadece Spirit ruh demek diye ben de bir endişe ismi olsun diye öyle bir cevap koydum. Bazı cevaplar zaten çok uydurma olacak. Göreceksiniz, eğlenelim diye yaptık.
Tamam, o zaman bir sonraki sorumuza geçiyorum ben. Aşağıdakilerden hangisi ekstremofiller ailesinden değildir? Asidofiller, alkafiller, çılgınofiller, alkalifiller, çılgınofiller, termofiller. Süremiz başlamıştır.
Bence bu gayet kolay, yani herkesin anlayabileceğini düşünüyorum.
Evet,
Bu esprilerimizden biriydi. Evet, doğru bir cevap geldi. Yani ya, doğru. Evet,
ama hocam cevabı söylersek olmaz.
Çılgınofiller tabii ki değil. Evet. Devam edelim Berra. Herkes şu an eğleniyor.
Herkes doğru cevapladı. Bu kadar zor soruyu nasıl doğru cevaplarsınız bilmiyorum. Neyse, bir sonraki sorumuza geçelim.
Zor sorularımız da var ama.
Bekleyin. İlk büyük yok oluş hangisidir? Devonian yok oluşu, B. Büyük oksidasyon olayı, C. Trias yok oluşu, D. Voldemort'un yok oluşu.
İlk üçünü bilemeyeceğini düşündüğüm için seyircilerimize kolay bir şey koymak istedim.
Öyle yapıyorsun ama insanlar belki bilmiyor.
Evet ama belki burada isimlerini duyunca merak edip araştırırlar. Trias
Evet,
yok
chatte
oluşu neymiş,
birisi
Devonian yok oluşu neymiş falan.
biri Devonian yok oluşu dedi ama bak
Biri
demek ki
Trias
bilmeyenler var.
dedi. En azından bir şıkkı eleyebiliyorlar. Voldemort'un yok oluşunu eleyebiliyorlar.
Neyse biraz daha bekleyelim cevapları.
Evet, herkes farklı cevap veriyor oldu. Voldemort'un yok oluşu diyen arkadaşımız var ama.
Evet.
Biraz daha bekleyelim bence.
Bekleyelim.
Herkes
Oo,
belki
A
kopya
demeye
çeker
başladılar.
arkadaşlarımız.
Arkadaşlar bu kadar... Herkes başka cevap vermeye başladı. Evet arkadaşlar doğru bildiniz.
Bayağı aktif bir şekilde ilerliyoruz.
Permiyen Trias.
Trias. C ve A arasında odaklanıyor herkes.
Evet,
İlginç.
bir harf şu an ortak bir karar veremedi. Şu an 3'e bölündük. Neyse o zaman biz doğru cevabı söyleyelim. Siz
Bence
bu kadar
de
çok
söyleyelim
arada kalmayın.
artık.
Evet, cevabımız
Büyük oksidasyon olayıydı. Kimse bilemedi.
bilemedim.
Evet.
Yapacak bir şey yok arkadaşlar. Bir sonraki soruya.
Yaklaştınız diyelim. En azından
Evet.
Voldemort'un yok oluşu bir kişiden geldi sadece.
Evet, demek ki onu herkes biliyormuş. Aşağıdakilerden hangisi yaşamın başlangıcı teorilerinden biri değildir? A. Panspermia, B. RNA dünyası, C. Elektrik kıvılcımı, D. Tsunami.
Bunu bilirsiniz artık. Bu arada özür diliyorum. Evet, yorumlarda görmedim. Gözel Azat bilmiş B demiş. Ama kopya çekip çekmediğine emin değilim. Çünkü çok süre verdik.
Valla ben kendim yapmaya çalışıyorum şu an. Sorulara bakmamıştım önceden ama.
Evet, bunu doğru biliyoruz en azından.
Vallahi bilmiyorum.
Bir doğru cevap
cevabı
geldi bu
arkadaşlar.
arada. Ben doğru
Tamam,
cevap gelince doğru cevap
çaktırma.
geldi diyorum. Gelmediği sürece sadece sizin cevaplarınızla eğleniyorum arkadaşlar. Haberiniz olsun. Orada soruları hazırlayan benim. Berra doğru söylüyor. Soruları ve cevaplarını görmedi. Ona da şu an sürpriz. Biraz.
Evet,
O
ben şu an
çalışmadığı
vallahi
yerden geliyor
bilmiyorum.
ona.
Bunu bilemedim. Ben de çalışmadım vallahi arkadaşlar.
Arkadaşlar bu önceki sorudan kolay bir soruydu. Bunda kolay bir şık bıraktım. Tahmin edersiniz diye ama galiba kafa karıştırıcı oldu o şık. Şöyle
Olabilir.
doğru cevap bununla tsunami'ydi. Panspermia zaten yaşamın başlangıcı ile ilgili bir teori. RNA dünyasında da yaşamın DNA'nın RNA'dan oluştuğu ile ilgili bir düşünce var. Elektrik zaten deneyleri de yapıldı bunun ilk başta. Yani elektrikler, daha doğrusu şimşekler sebebiyle yaşamın başladığına inanılıyor ama tsunami ile ilgili bir şey yok.
Tamam, bir sonraki sorumuza geçelim artık o zaman.
Evet.
Aşağıdakilerden hangisi astrobiyoloji alanında çalışma yapmış ünlü bilim insanlarından biri değildir?
Bu da çok kolay.
Yani evet. A. Charles S. Cockle, B. Albert Einstein, C. Carl Sagan, D. Betül Kaçar. Yani buraya gelen herkesin bilmesi gereken bir soru. Sanırım bir soru geldi Zeynep. Chat'e bakmak
Yok,
istersen.
elektrik kıvılcımı şıkkını açıklayan deneyi söylemişler, Miller-Urey'i. Evet.
Sanırım bu sefer herkes bilecek gibi.
Bunu bilirler artık.
Yani buraya geliyorsunuz tabii ki bunu bilmeniz lazım biraz sanki. Neyse biz biraz daha bekleyelim.
Zaten doğru cevap verildi. Bence doğru cevap verilince beklemeyelim ama çünkü herkes birbirinden görerek zaten söyleyebilir. Ama doğru cevap yoksa bekleyelim. Eğleniriz. Evet.
Tamam.
Doğru cevap ve Albert
Tamam, o zaman
Einstein.
doğru bildiniz arkadaşlar. Evet, bir sonraki sorumuza geçelim o zaman. Aralık 2021 tarihinde fırlatılan ve Ocak 2022'de yörüngesine yerleşen teleskop hangisidir? A. Hubble Uzay Teleskobu, B. Sovyet Orion 1, C. James Webb Teleskobu, D. OAO 2. Onu ilk defa duydum.
Eski bir teleskop. Tarihten dolayı zaten kimse bilmediği için onu işaretlemez diye düşündüm. Ama o da var bu arada.
Sovyet'i de biliyorum da o D'yi ben de bilmiyorum.
Zaten asıl önemli olan tarihti burada. Yani herkesin kolayca anlayabileceği. Ben öyle düşünüyorum.
Doğru cevap
Evet.
geldi aslında. İsterseniz
Evet,
cevabınızı
beklemeye
verelim.
gerek yok. Çünkü tarihten dolayı en güncel olan James Webb tabii ki 2022 olduğu için.
Evet,
Devam
bir sonraki
edelim.
sorumuza geçelim.
Evet.
Dünyadaki yaşamın başlangıcı hangi jeolojik dönemde gerçekleştirmiştir? A. Ben bile soruyu okuyamıyorum. Prekambriyen dönem, B. Paleozoik dönem, C.
Paleozoik. Mezozoik.
Paleozoik dönem, C. Mezozoik dönem, D. Milattan önce 1200.
D'yi seçmezsiniz diye umuyorum.
Ya Zeynep sen daha soruyu açtık 10 saniye içinde cevabı verdin ya.
Vermedim.
Olmuyor böyle. İzleyicilerimiz çok şanslılar yani. Evet, şu an herhalde daha cevap gelmiyor. Evet, ilk cevabımız geldi.
Biri verdi cevabı. Bakalım başka kimler ne cevap verecek? B diyen oldu, A diyen oldu. Evet,
Evet.
A mı B mi arkadaşlar?
Evet,
A'lar
bir karar
artıyor,
verin.
A'lara oy artıyor. D'yi ben sizin için eledim zaten. 3'te 1 şansınız var. Evet,
Hadi
güzel. Doğru
bakalım.
cevaplar geldi.
Dini kaynaklara göre D olabilir belki.
Ama
5000
dini
yıllık
bir şey
insanlık
sormuyoruz.
tarihi.
Jeolojik dönem soruyoruz yaşamın başlangıcı ile ilgili. Hani evrimsel bir başlangıç var ya. Bence gösterelim artık Berra.
Doğru cevap geldiğine göre gösteriyoruz.
Evet. Prekambriyen dönemdeydi arkadaşlar. Zaten Mezozoik dönem bayağı sonra. Yani o kadar geç başlamadık yaşama.
Bir sonraki sorumuza geçelim o zaman.
Evet.
Aşağıdakilerden hangisi yaşamın başlangıcı ile ilgili yapılan ilk deneyleri uygulayanlardan biri değildir? A. Francesco Redi, B. Miller-Urey, C.
Urey.
Louis Pasteur, D. Operin Haldane.
Operin Haldane. Az
Haldane.
önce Miller-Urey'nin ismini bilerek vermek istememiştim ama chatten bir kopya geldiği için B şıkkını şu an elemiş olduk. Miller-Urey elektrikle ilgili yaptığı deneylerle ilk deneylerden birini yapmış oldu. Dolayısıyla 3 tane şıkkınız var.
Valla ben iki şık hakkın arasına gidip geliyorum şu an.
Bu zor bir soru bu arada. Bilerek aldattığım bir şık var. Yani düşeceğinizi düşündüğüm şıkka düşüyorsunuz şu an.
O şıkkı ben eledim ya. Louis Pasteur aşıyı yapan değil miydi?
Evet, yaşamın başlangıcıyla ilgili de bir deneyi var. Zaten aslında arkadaşlar sunum hazırlanırken o şıkkın rengi de bir farklı kalmış. O yüzden aslında size şu an cevap gösteriyor. Ben size kopya vereyim buradan. Yani bir farklı ton var orada. Helyum, neon, lazer gibi mi? Oparin ve Haldane gerçekten bilim insanları bu arada. Neon lazer değiller. Gerçek isimler. Ama şöyle açıklayayım. Bu zor bir soruydu. Oparin ve Haldane cevabımız. Oparin ve Haldane yaşamın başlangıcıyla ilgili karma bir çorba görüşünü savunuyorlar. Ama bunu deney olarak yapamıyorlar, gerçekleştiremiyorlar. Sonrasında Francesco Reddy ve sonraki bilim adamları bunu deneyerek ispatlıyor. Miller-Urey de aynı şekilde bu karışık çorbanın içine elektrik verildiğinde olanları anlatmış oluyor ileriki deneylerde. Louis Pasteur'ün de bu arada yaşamın başlangıcıyla ilgili deneyi var. İsimleri çok uyduruktur.
Bayağı bilgilendirici oldu bizim için.
Hayır, uyduruk değiller. Gerçekten varlar arkadaşlar. Araştırmanızı tavsiye ederim. Bir yandan bu soru cevabı yapmamızın sebebi sizin aklınızda böyle isimlerinin kalması ve biraz da olsun fikir edinmeniz. Oparin ve Haldane'i Google'dan araştırarak öğrenebilirsiniz. Bu arada Reddy'nin, Pasteur'ün ve Miller-Urey'in deneylerine de bakabilirsiniz. YouTube'da bunlar için küçük böyle çocuklara eğitici videolar gibi kısa videolar var. Oralardan hızlıca izleyebilirsiniz.
Evet, güzel bilgilendirmen için teşekkürler Zeynep.
Rica ederim.
Evet, bir sonraki sorumuza geçelim.
Bu kolay bir soru.
Aşağıdakilerden hangisi Mars'ta yaşam olmasını zorlaştıran faktörlerden biridir? A. İnce atmosfer tabakasına sahip olması. B. Matbaanın geç gelmesi. C. Artan kur fiyatları. D. Yerli üretimin az olması.
Bunu Türkiye şartlarına uyarladım ama inşallah banlanmayız bu. Bu yayını banlamazlar inşallah. Öyle yani bence gayet açık ve net bir cevap ama siz bilirsiniz.
Bir sonraki şık Türkiye'de yaşamak olacaktı herhalde.
Yo, rengi değişik değil. Ben aynı görüyorum. Siz farklı mı görüyorsunuz? Ekranda mı? B rengi değişik
Evet,
diyor.
rengi değişik bu arada. Evet, rengi değişik.
Peki. Evet, cevabımız A'ydı. İnce atmosfer tabakasına sahip olması.
Çok zor bir soruydu gerçekten.
Yani zor sorulardan sonra kolay sormaya çalıştım.
Last Universal Common Ancestor, Luca, kaç ortak gen bulundurur? A. 100, B. 82, C. 65, D. 126.
Bu zor bir soru arkadaşlar. Lütfen Google'a bakmayın.
Lütfen Google'a bakmayın.
Google'da yazıyor çünkü.
Ama ben de bilmiyorum bu arada bunun cevabını. Ama bir tahminim var.
Aslında bu soruyu şeyde de sormuştuk. Kahoot yapmıştık ya, etkinliği orada da sormuştuk.
Hı.
İlk sorularımızdan biriydi.
Evet, sanki oradan mı hatırlıyorum acaba?
Evet.
Emin değilim yani. Ben de cevabımı yazacağım. Dur.
Farklı renklere takılmayın, ben onu öylesine söylemiştim. Yani çok küçük renk tonu farklılıkları olabilir. Bu sadece tema için yapıldı arkadaşlar.
Arkadaşlar ben MBG Türkiye'den yazdım. Ben de cevap yazmak istedim buna.
Evet. Çok farklı cevaplar geliyor. Biz cevabı söyleyelim arkadaşlar. A100.
Evet, doğru bilmişim bak.
Evet, ben doğru bildim.
Sevindim kendime. Bir sonraki sorumuza geçelim. Var mı soru bilmiyorum ama.
Var.
Evrende en çok bulunan element hangisidir? A. Helyum, B. Hidrojen, C. Karbon, D. Tahta.
Bu soruda da sizin için bir şık eledim. 2 şık arasında kalacağınızı düşünüyorum.
Ben de cevabımı yazayım ya. Ben de cevap yazmak istiyorum.
Tahta diyenler var.
Tahta.
Evet, bizim ekibimiz de tahta diyor. Herkes tahtada hemfikir galiba. Doğru cevabı veren arkadaşlarımıza teşekkür ediyoruz. B. Hidrojen arkadaşlar.
Aa, cidden mi? Ben karbon yapmıştım ya. Niye
İşte
karbon
arasında
diyebiliyorum bilmiyorum.
kalacağınızı düşündüğüm şıklardan biri aslında karbondu ama bu arada evrende en çok bulunan element hidrojen ama gezegensel olarak değişimler oluyor. Yani helyumun çok bulunduğu yerde var. Güneşte de helyum mesela çok vesaire. Hani biz direkt evrende bakılan haliyle sorduk. O yüzden hidrojen.
Yorumlar çok iyi, şu an okuyorum ama. Tamam, geçelim bu soruyu. Dünya atmosferinde en çok bulunan gaz hangisidir? A. Oksijen, B. Helyum, C. Azot, D. Hidrojen. Evet, bu da bence çekişmeli bir soru.
Yo, bence
Sorunun
bunu
cevabını
bilirler ya.
biliyorum.
Bu kim 500 milyon ister mi, 1000 ister mi? Onda bile çıktı. Hatta yüzdelerini sordular. Bu bayağı
Yüzdelerini
bilinir
de
diye
biliyorum.
düşünüyorum. Evet, bak biliyorlar arkadaşlarımız.
Tabii bilimsever herkes bilir.
Hala tahta diyen var galiba. Arkadaşlar tahta yok burada şıklarda.
Hayır.
Tahta
olacak
gaz
direkt.
değil. Üzgünüm, onu koyamadım. Gaz olsa onu koyacaktım. Evet, doğru cevap azot. %78'le olması lazım yanlış hatırlamıyorsam.
Evet. %70'li bir şeydi. Ben de öyle hatırlıyorum.
Yani 78 veya 72 idi galiba yanlış hatırlamıyorsam.
Oksijende %20 olması lazım.
%20'ye yakın galiba. %18 falan o da. Tam hatırlamıyorum ama.
Evet, azalmış oksijenimiz
Galiba
arkadaşlar. Nefes
öyle bir
alamıyoruz
şey.
artık.
Azot 81 mi? O kadar yüksek diye bilmiyorum. Ben 70'lerde hatırlıyorum ama.
Bazı arkadaşlarımız çok bilgili.
Biri ben sözelciyim bilmiyorum demiş. Ama
Evet Şeyma, evet.
21'miş oksijen. Peki.
81'e 21 olmuyor arkadaşlar yani. Biriniz yanlış söylüyorsunuz bence ama.
Bence oksijen 21 olabilir. Diğeri de azot da 78 falan olabilir. Kalan %1-2'lik
Şeyma.
kısmı işte küçükler.
Aynen. O da
Diğerleri
o
olabilir.
diğer gazlar.
Tam hatırlamıyorum. Azot 70'li bir şeydi ama ya.
Azot 7 olmasın.
Diğer soruya geçelim.
Tamam. Mars'ta
Evet,
uçuş
Nur doğrusunu
gerçekleştiren
yazmış bu arada. 78, 21, 1 diye. 78'i doğru hatırlıyormuşum.
evet. Şeyma Hanım yanlış bildiniz maalesef. Sözelci bile olsanız. Yapacak bir şey yok. Mars'ta uçuş gerçekleştiren ilk helikopterin adı nedir? A. Ingenuity, B. Ingenuity, B. Curiosity, B. Ability, D. Dexterity.
Lütfen renk farklarına takılmayın arkadaşlar. Bir de Dexterity'yi yanlış yazmışlar burada. İyi var orada fazla.
Olsun.
Ben herkesin bilebileceğine inanıyorum bunu. Zaten şıklardan birinin adına ne rover var ne helikopter var. Onu ben uydurdum.
Tamam. Ben de cevabımı yazdım.
Berra yanlış bildin. Curiosity rover'ın adı ve o rover'la onun alakası yok. Cevap Ingenity'ydi. Ingenuity Perseverance'la taşındı. İlk uçuşlarını o şekilde gerçekleşti. Curiosity Perseverance'dan önceki rover'dı. Onda helikopter yoktu.
İşte oradan bir anımsayınca direkt şey olmuşum. Ona cevap vermek istedim. Arkadaşlar hala renkten mi gidiyorsunuz? Sınavda değiliz ya.
D yazım yanlışından elenebilir. Evet, çünkü sunumu hazırlayan arkadaşımız oraya fazladan bir i koymuş ama bu demek değil ki doğru cevap değil. Zaten bir tanesinin ismini ben uydurdum. Hepsi Ingenuity Curiosity diye bitiyor diye, Ability diye ben ekledim.
Yani o zaten çok belli, biraz bariz olmuş. Tamam, bir sonraki soruya geçiyorum o zaman.
Evet.
Aşağıdakilerden hangisi dünya dışı uygarlıkların var olma olasılığı ile ilgili paradokstur? A. Ne o? Belin mi yazıyor?
Evet,
Belinin uzay gemisi paradoksu. B. String paradoksu. C. Fermi paradoksu. D. Zoidak paradoksu. Zoidak arkadaşlar. Evet.
Buradan da astroloji bir bilim değildir diye tekrar bir kamu spotu geçelim.
Astroloji geçiyoruz.
Bu soruyu da aslında eğer geçen sene bizim konferanslarımızı takip ettiyseniz biliyor olabilirsiniz. Umut Yıldız evet bu konuyu anlatmıştı. Evet, Fermi paradoksu doğru. Onur yanlış bildin, A değil.
Bildiğim tek paradoks Fermi bence C. Evet.
Evet, C doğru.
Bundan
sonraki sorumuz son sorumuz bu arada.
Evet, o zaman arkadaşlar son sorumuzu soruyorum. Uzaya ilk çıkan astronot kimdir? A. Yuri Gagarin, B. Neil Armstrong, C. Edwin Buzz Aldrin, D. Alan Shepard.
Alan Shepard. Bunu bilirsiniz
Yani.
diye düşünüyorum. Hatta bilerek
Daha
Edwin
geçen
Aldrin yazınca tanımazsınız diye Edwin Buzz Aldrin, hani Buzz Aldrin'den tanırsınız diye böyle isimlerini bilerek
daha
şey
geçenlerde zaten günü vardı arkadaşlar, biliyorsanız.
Evet. Genelde her sene de kutlanıyor.
Hı hı. Yani kozmonotla astronot aynı şey
Aynı
zaten.
şey. Evet.
Evet.
Aslında
O
doğru
sadece-
cevabı verip yanlış cevabı verdi.
Türkler için ne isim konmuştu, hatırlıyor musun Zeynep?
Gökmen.
Gökmen.
Evet.
Aynen.
Niye
Tamam.
men
O zaman-
bilmiyorum ama o İngilizce'deki adamdan mı geliyor, Superman'deki gibi, onu anlamadım çok. Gök adamı.
Gök adamı. Hayır, gök insanı.
Evet, cevabımız Yuri
Evet,
Gagarin.
cevabımız Yuri Gagarin.
Çok teşekkür ederiz bizimle bu etkinliğe katıldığınız için. Biz çok eğlendik. Umarım siz de çok eğlenmişsinizdir.
Evet, ben bayağı
Teşekkürler
eğlendim
Berra.
açıkçası.
Sana da
Ben de teşekkür
soruları
ederim
yönelttiğin
Zeynep.
için.
Soru cevap etkinliğimize katıldığınız için çok teşekkür ederiz. Sıradaki hocamız, onun da duyurusunu yapayım bir saniye. Sıradaki hocamız saat 4.30'da Shiladitya de Samara bizlerle beraber olacak. Yayınımızdan ayrılmayı unutmayın.
Görüşmek üzere.
Hi everyone, I'm Sude and I will be hosting the fourth session of today. Prof.Dr. Shiladitya Sarma will be joining us, but first I'd like to tell you about him shortly. Dr. Sarma is a pioneering microbiologist, well known for his contributions to the genomics, molecular biology and biotechnology of archaea, and the field of astrobiology. Prior to joining the Institute of Marine and Environmental Technology, University of Maryland School of Medicine, he was a professor in the University of Massachusetts Amherst and the University of Maryland Biotechnology Institute. He has published over 150 scientific papers over his career and mentored many students. He founded the UMB Pills Genomics track and is the UMB institutional representative for the system-wide NIS graduate program. Extremophiles define the limits to life on Earth and serve as the model organisms in the search for life elsewhere in the universe. Now, we will be having Prof. Dr. Shiladitya Sarma on the topic of ancient microbes as models for astrobiology, polyextremophilic capabilities, and early evolution of holophilic archaea. Hi, Shiladitya. How are you?
Good. How are you, Sheri?
I'm well. Thank you for coming. Would you like to add anything to your intro, your bio? Did I miss anything?
Well, sure. I can add a couple of things. I actually have a couple of slides in my presentation that gives you a background, a picture of where I come from, what my education was like. So, I was trained at MIT with a fellow by the name of Hargobind Khurana. And he was a Nobel laureate for his part in cracking the genetic code.
Wow.
So I worked with him long after he had won the Nobel Prize and cracked the genetic code. But that's sort of my history, the roots of my intellectual development was from him. And so, I think that says a lot about the way in which I think about astrobiology and about science in general.
That's great. He must be so inspirational.
He surely was. And he had a very large group. He had about 30 people in his group. And he worked over 6 decades. And actually, we just celebrated his 100th anniversary of his birth. He was born in 1922. So last year, there was a celebration of his 100th year centenary of his birth, and I gave a lecture, and that lecture is available on YouTube. So I can show you a link to that as well.
Yeah, that would be great. We can share that on chat, the link to that.
That would be great. Yeah, I can. Do you want me to put that in the chat?
No, we can handle that, and you can start your presentation, of course.
Okay. Well, thank you so much, Shudi. This is a wonderful opportunity, and I also want to thank Zainab and everyone there. It's terrific that you guys are putting this conference together, and it looks like a wonderful event. So I will go ahead and present. Should I just click on present, and that should?
You should click on present and then share my screen.
Okay. Okay.
And then entire screen. Yes, this is perfect.
Okay.
And you can begin.
Super. So thank you again, Sudhi, and all the organizers for inviting me to speak to you today. And it's entirely my pleasure to be here. And I would like to spend most of my time introducing you to halophilic archaea or haloarchaea. I've spent about 40 years working on these organisms, and I find them to be very fascinating, particularly because they are really remarkable in their extremophilic capacity. They're able to tolerate a lot of different extremes. And they're also evolutionarily very interesting organisms. So with that, I would like to start by, talking in general about astrobiology. I know we have many lectures on astrobiology, but from my perspective, this is what I think of when I think about astrobiology. And the first is it a philosophy or is it a science? Some of the questions in astrobiology are really philosophical, like what is life? Or are we alone? Could we find life elsewhere if it exists? But there are some questions in astrobiology that are more on the science side. And how did life evolve on Earth? They're very challenging questions scientifically, but one perhaps that we could solve. And another is, what are the limits to life? And these are the types of questions that I have spent a lot of my career thinking about. And I'd like to share some of those findings with you today. So as I was saying earlier, I was trained at MIT in the laboratory of Hargobind Khurana, A.G. Khurana. And Khurana is a pioneering figure in molecular biology because he helped to crack the genetic code. And you can see the genetic code on the right. And, there are 64 letters, which specify 20 amino acids. And it's been called standard or universal. Essentially, every organism on Earth uses the standard genetic code. And this is probably the best evidence that all life on Earth evolved from a common universal ancestor, LUCA, people call it. And because essentially this is a frozen accident in the evolutionary development of life on Earth. And so Dr. Khurana's expertise was in chemistry. He was able to synthesize nucleotides, and that's why he contributed to the cracking of the genetic code. He went on to do a lot of other work, including gene synthesis. He synthesized the first gene. And you could, I think, argue that he is really the father of synthetic biology. And we celebrated his centenary of his birth last year. And I was asked to give some lectures, and these lectures, a few of them are available on YouTube. And you could go to our website, which is halo-ed.org or /HGK, and you can hear this lecture if you like. Whoops. So when I worked with Dr. Khurana, his research had moved on to studying membrane biology. And in particular, his laboratory was focused on one protein called vectoridopsin. And vectoridopsin is a protein that's produced in the purple membrane of Halobacterium. And Halobacterium, despite its name, is an archaeon. It's not a bacterium. And one of the first things that Dr. Khurana did was to hand me a flask of this purple organism and said, this is going to be your project. And it's a pretty fascinating organism because it produces this protein that's a light-driven transmembrane proton pump or hydrogen ion translocator. And so if you shine light on cells, it pumps protons across the membrane or hydrogen ion ions, and it creates a proton motive force, which is a universal phenomenon in biology. And in fact, just a few years before I joined Khurana's lab, two other people named Racker and Stokenius had done an simple experiment to prove that proton motive force was very important in synthesis of ATP. This is called the chemiosmotic coupling hypothesis, and it had been proposed a few years before that by someone named Peter Mitchell. And this protein was very important in proving that cells carry out proton motive gradients to synthesize ATP. Well, in any case, the Bacterodopsin protein was something that Khurana himself had sequenced. He sequenced the protein himself. He was the first author on that paper. And his lab had already also shown that the chromophore, which you can see inside in purple, is retinal, is attached to the protein by a shift base. So in addition to Khurana, another scientist had a rather profound effect in my thinking, and his name is Carl Woese. And he was not a direct mentor to me, but he was working at the same time on ribosomes, and it's particularly ribosomal RNA. And of course, ribosomes are where the proteins are synthesized and where the genetic code is translated. But he was looking at it from an evolutionary perspective, and he showed that used by analysis of the small ribosomal RNA, that all organisms could be classified according to 3 separate, what he called domains. So he came up with this 3-domain tree of life. And this was around 1977, just before I became a graduate student. So I knew this when I entered Khurana's lab. Sorry. Okay, so when I joined Khurana's lab, one of the first archaeal genes had just been cloned and sequenced, and this was the Bacterodopsin gene, or BOP gene. And that sequence showed for the first time that archaea used the same genetic code as all the other organisms. So you can see on the bottom the translation. But in red, you can see that we were looking for a promoter and we couldn't find a promoter. So in bacteria, promoters have a particular sequence, which is called a Pribnow box, TATAAT, and there was no such promoter. So my project was to find the promoter, and I used a method called capping. And capping is something that is done with eukaryotic messenger RNAs, and I could show using some classical nucleic acid biochemistry that one could cap this RNA, and you can see the red arrow showing the GC, AUG, UUG. That's the start of transcription. So there must be a promoter there, but it wasn't like anything that we had seen before. So that in itself was additional evidence that archaea were different from bacteria. And then I also did some work on Halobacterium genetics because the particular strain that I was using was purple. I could find mutants that had lost the ability to produce purple membrane, and they were orange mutants and white mutants. And I could analyze these, and it led to the discovery of transposable elements in archaea. And you can see on the right that the Bacterodopsin gene or BOP gene is frequently interrupted by transposable elements. So this, at an early stage in my career, opened up my interest in the genetics and the genomics of Halobacteria. So jump forward about 10 years, in 1995, I had already started my laboratory at the University of Massachusetts at Amherst in 1986. And during this time, sequencing methods had been advancing. And in 1996, the first complete genome of a free-living organism, Haemophilus influenza, was published by a group at the Institute for Genome Research. And this started, of course, the genomics revolution. And we started immediately sequencing the Halobacterium genome. And it took us at that time 5 years to sequence the first genome, and it was published in Proceedings of the National Academy of Sciences in October of 2000. And one of the findings from the genome was that there are about 2,500 genes which code for a very large number of proteins. And the proteins function in a lot of different cellular processes, including nutrient uptake, energy production, signal transduction, protein translocation, transport of cations and anions, etc. And this work was, this picture was also published in textbooks. So, for instance, the microbiology textbook by Slonczewski and Foster published this. So let's think about the environment in which Halobacterium and these extremely halophilic archaea grow. So they grow under conditions that are essentially considered the limits to life. So on the left, you can see that as you evaporate a brine, you slowly decrease the water activity, and you have a sequential precipitation of different salts. So gypsum or calcium sulfate, halite, and ultimately potash. At the point at which halite or sodium chloride precipitates out, that's considered the highest salinity or the lowest water activity at which life can exist. And under these conditions where you're having evaporation to saturating conditions, you also have other extremes. You have very low oxygen usually, and generally these are occurring in solar, highly illuminated environments, such as, and so they're exposed to high ultraviolet radiation. And when the precipitation occurs, you're actually getting desiccating conditions. And those desiccating conditions result in breakage of DNA, double-stranded breaks, which is the same damage that ionizing radiation exposes cells to. And then frequently, well, not so frequently, but occasionally you'll also have environments which are cold. So these are all additional extremes that haloarchaea are exposed to. So here on the left, you can see the growth of haloarchaea and other organisms at different sodium chloride concentrations. So you can see a series of organisms which are halophiles, but they're slight, moderate, or extreme halophiles. And you can see on the right, the haloarchaea are the most halophilic or salt tolerant. They have an optimum of around between 4 and 5 molar. They really do not grow at 2 molar. They generally tend to lyse. However, they can grow at saturating salinity, which is about 5.3 molar. And so these are really remarkable extremophilic properties. And the other thing is that they are archaea, so they're also evolutionarily very old. You can see the cartoon on the right showing the evolutionary tree from Lucca, or near the, which likely existed near the formation of the Earth within the first billion years or so. Up to the present time, the Earth's age is about 4.5 billion years. And the archaea are thought to have evolved prior to the Great Oxidation event in the first half of the history of the Earth. And there are lots of unknowns, and these unknowns are of interest for astrobiologists. And that is, how did all of these different processes evolve from Lucca to, say, photosynthesis or respiration, phototrophy, even the genetic code? We know what the code is, but how did it evolve? And chemiosmotic coupling, as I mentioned earlier, and even the formation of cells. So all of these are unknowns, great unknowns that astrobiologists pose. And Some of the questions that we have posed over the years is, for instance, when and how did halophilic archaea evolve? And how do haloarchaeal proteins function in their extremely low water activity and hypersaline conditions? And how do haloarchaea survive multiple extremes, low oxygen, ultraviolet and ionizing radiation, perchlorate ions, etc.? And could haloarchaea survive and be detected on Mars or even on exoplanets? So I wanted to provide you with one piece of evidence that these archaea appeared very early, and that comes from their lipids. Their lipids are very unusual. They have a fatty chain, but it's branched. It's a phytanol chain, and it's linked to the head group, the glycerol, via ether linkages. So this is very distinct from bacterial and eukaryotic lipids. And these are extremely stable and can be detected using Raman spectroscopy. And so there are reports that sediments that are 2.5 to 3.8 billion years old contain these types of chemicals. So that is evidence that these archaea evolved very, very early in the history of the Earth. And if you look at it from a phylogenetic standpoint, you can see on the right-hand side is a small ribosomal RNA tree, similar to what Carl Woese would have published. This was published a bit later by a group in Germany. But you can see that there are three distinct groups: the bacteria, the eukarya, and the archaea. And the haloarchaea are clearly, distinctly within the within the archaeal group. You can see it in the purple. However, on the left is a whole genome tree. So once we had the first haloarchaeal genome, the Halobacterium species NRC1, we could do whole genome analyses. You could see that with a whole genome, where you take an average of all the genes, haloarchaea actually come out as the root, at the root of the archaeal group. So does that mean that haloarchaea actually evolved early, or did they evolve late? So that's a question that we still don't have a complete answer to. However, one observation that we made was that depending on which bacteria you use to draw your whole genome tree, you get different results. So for instance, on the left, if you use Seneca cystis, Dinococcus, or Aeoleuticus, you see that Halobacterium is branching as an early branch of the archaea. But if you use Bacillus, Pseudomonas, and E. coli, Halobacterium actually moves over into the bacterial group. So the reason for this is that there are a lot of bacterial genes in halobacteria. So if you take an average and do a whole genome tree, it actually moves around. So if you classify genes according to their bacterial or archaeal character, and you can do that for a whole set of different organisms, the ones on the left are showing bacterial genes in archaea, and the ones on the right are archaeal genes in bacteria. For instance, Thermatoga maritima is one bacterium that was famous for having a large number of bacterial genes. You can see that, but you can see with haloarchaea, it contains even more bacterial genes. Hal is the one in the center here, and you can see that it has more bacterial genes than any other archaeon. So this became evidence that there are a large number of horizontally transferred genes, bacterial genes, in this archaeon. So that's currently the dogma. We've done quite a lot of work on analyzing these, and there's a paper by one of my former graduate students, Sean Kennedy, who's now at the Pasteur Institute, and you can read this paper in Genome Research. to get more details, but the upshot of it is, for instance, the respiration genes, aerobic respiration genes in Halobacterium are very similar to the genes in E. coli. So it's fairly likely that Haloarchaea learned how to respire with oxygen. Presumably they evolved before the great oxidation event. So they must have been anaerobic at one point, then they became aerobic by essentially stealing the aerobic respiration genes from E. coli or a bacterium like E. coli. So if you think about early evolution of life on Earth, on the left, it was the conventional view, as you saw in the tree that I showed with Carl Wose's picture. But as time went on, it became that clear that evolution is not that simple, and there's been a lot of genetic exchanges along the way. So, okay, so we have started looking at diverse Haloarchaea after studying Halobacterium species NRC1 as our model for many, many years. Recently, we've isolated organisms from the Great Salt Lake, some solar salterns, this giant salt lake or salar called Salar de Uyuni in the high Andes of Bolivia, also Tarija mine. This is a very old Permian mine in Bolivia. And also we're studying an organism isolated by the Australians in a deep lake, which is in East Antarctica. And these environments are Mars analogs. So on the right, you can see some photographs of the surface of Mars. The blue is a false color, but the others are the real color. So you can see that they're actually evaporites on the surface of Mars. They're mapped about, NASA has mapped about 600 of these. And they're probably pretty similar to the Salar de Uyuni as shown on the left. And as you can see, if you dig down a little bit into the salar, there's a lot of color and indicative of living microorganisms just beneath the surface. So it's tantalizing to think that maybe something similar is also true on Mars. The other resource that we have as we do the genome sequences is our database. And I'm sorry, I didn't update the URL, but it's called HaloWeb. So if you Google HaloWeb, you'll see it. It's haloweb.org. And so there are genome sequences from Haloarchaea from all over the world, including Antarctica. And most recently, sorry about that. Most recently, we have isolated new organisms from Great Salt Lake, from the east coast of the Dead Sea in Jordan, and also in the high Andes of Bolivia. And all of these genomes are available. So one of the things that we've done with these genomes is do a comparative bioinformatic analysis, and this is through this process that was pioneered by Roman Tadusov in NCBI, in NIH. And the idea here is to take a single protein and blast against the whole genome of another organism and to a third organism and then back to the first and second organism. And then you can find what are called best reciprocal hits. It's a lot of computational work, but ultimately you end up with clusters, and they're called clusters of orthologous groups. And if you have just 3 genomes, you're doing 6 genome blasts. In this case, we did 9 genomes, and we did 72 genome blasts. So it becomes progressively geometrically more complicated. So it does get computationally very intensive. But one can obtain clusters of orthologous groups, or COGs. In the case of Haloarchaea, we call them HOGs, for haloarchaeal orthologous groups. And what we found is a distribution like this. So if you take the these hogs, and you plot out how many hogs are present in how many organisms, you see that there's a bimodal distribution, and the ones that are present in all of them, we call them conserved hogs or chogs, and there are about 800 of those. And all of the others are present in a subset, and you can see that there are many genes that are only found in a few haloarchaea. And so this is sort of the pangenome. So it's the core versus the pangenome that's being displayed here. And interestingly enough, there are 77 chogs or conserved proteins which are only found in haloarchaea. So we find those to be particularly interesting because they are signatures of haloarchaea. So as we dug deeper into analyzing these, we found that the proteins in haloarchaea are incredibly acidic. So this is a plot of the NRC1 proteins with respect to their isoelectric points, or PIs. And anything below 7 is acidic, anything above 7 is basic. And you can see with the red line that essentially everything is acidic. And that's in contrast to everything else, which has both acidic and basic proteins and some neutral ones, and with essentially a neutral isoelectric point, neutral proteins. And one of the consequences of this is that the proteins are all negatively charged at a pH of 7, and so therefore they repel one another, and we think that this is an important mechanism in keeping them in solution. And this is a universal property of all haloarchaea. You can see they're plotted here, and they all have incredibly acidic proteins. The other impact of having very negatively charged proteins is that they can hold on tightly to water, which is the problem with saturated salinity, is that there's so much salt that the proteins would otherwise become dehydrated because they can't compete with the ions for binding of water. And you can see on the left, the red shows the halophilic proteins binding to water. So they do have a hydration shell around the proteins. And if you look at a specific protein, in this case, we're looking at the Halorubrum lacus profundi beta-galactosidase protein. Beta-galactosidases have been very good as model proteins. You can see on the left is the haloarchaeal protein. On the right is a thermophilic bacterial protein, and you can see there are more negative charges in red on the left, and you can see that there are fewer blue or positive charges. So the net charge of the haloarchaeal protein is -65, whereas it's only -4 for the thermophilic protein. And we've done considerable work on this protein, and I don't have time to really go into the details, but you can see there are 5 papers here that have been published in the last few years to study this protein. And to make a long story short, we mutated residues in this protein. There were ultimately there were 10 which deviated from conserved amino acids in mesophilic homologs of this protein, because this protein is produced by the Antarctic haloarchaeon, Halorubrum lacus profundi, and we could show that these amino acids were important for the cold activity of the protein. And many of these residues are very far away from the active site. The active site is in this TIM barrel, the dark blue. These are the active site glutamic acids. And you can see that there are residues that are quite far from the active site, which are having an impact on its ability to function in the cold. So with that, I would now like to turn to the other extremes that I mentioned: the low oxygen, high solar irradiance resulting in UV damage, and also desiccation, which results in DNA breakage and also results in ionizing radiation tolerance. So Haloarchaea have tolerance to all of these different conditions. So the approach we've taken in general has been this combination of computational and experimental, or bioinformatic and experimental. So we have genomes which we are using for comparative genomic studies. We are also doing transcriptomic analysis, and then the results of that are being used for experimental work, biochemical studies, and identification of regulatory proteins, for instance. And then we can isolate genetic mutants by doing knockouts. And then after we do knockouts, then we can do physiological studies. And then we could take the genetic mutants and do sequencing and transcriptomics and do further bioinformatic analysis. So this is a circular approach to our research. And the glue that holds it all together is our genomic database, HaloWeb, which I've already mentioned. Jumping here. So Haloarchaea are very versatile metabolically in terms of their metabolic capabilities. They can grow by photophosphorylation. They can grow by oxidative phosphorylation, either aerobically or anaerobically through use of alternate electron acceptors like DMSO or sometimes nitrate, and even perchlorate. And they also have fermentation capabilities, such as using arginine. So they have a lot of different capabilities. So we approach this through analysis of transcriptomic data, and I just want to show you some of the data. So this is transcriptomic analysis of anaerobic versus aerobic growth. And so you can see each of those dots is a gene expression, for a particular gene. So those that are induced anaerobically are going to be above the diagonal, and those that are induced aerobically are below the diagonal. And you can see here the BOP gene, which codes for the purple membrane bacterodopsin, is one of the most highly induced under anaerobic conditions. So when the cells are anaerobic, they're trying to produce, or they do produce, purple membrane, which can then use light energy for growth. So it allows a period of phototrophic growth. They also turn on genes for the DMSO respiration. So the DMS A, B, C, D, E are involved in utilization of DMSO as the terminal electron acceptor. Here's another experiment where we took cells that were grown anaerobically with arginine and compared them to cells that were grown aerobically. And in this case, again, BOP is one of the more highly induced under the anaerobic condition. And the DMSO genes are actually even more highly induced. This is a more anaerobic condition. And then there's this third set of genes, the ARC genes, that are involved in arginine utilization. Those are also induced. And then finally, we compared growth under two different anaerobic conditions, for instance, TMAO and arginine. In this case, with arginine, one obtains induction of the DMSO genes. So that is counterintuitive. The ARC genes are also induced. The BOP gene is actually induced under the TMAO conditions. And another set of genes which are involved in production of buoyant nanoparticles called gas vesicles, which allow cells to float, are also induced under TMAO. So to put it all together, it's a lot of data, but there's a hierarchy of transcriptional responses by the redox conditions. So you can see in the triangle at the on the right-hand side, there's aerobic respiration is at the top. That's the preferred method of growing, or metabolism for growth. But if you reduce the amount of oxygen, the first things that you induce are BOP and the gas vesicle nanoparticles. And then you induce an alternate cytochrome oxidase and the DMSO, anaerobic respiration. And then ultimately, at the most anaerobic conditions, one induces, Halobacter induce the ARC genes. So they're pretty well evolved to tolerate a whole range of different oxygen conditions, and this would have been important during the evolution of these organisms, since they evolved from a pre-GOE time to the present oxidative time. And there are a large number of regulators and transcription factors, and I won't have a chance to go into this, but our lab is interested in how all of these regulators are working together. So in the last part of the presentation, I want to turn to these other extremes that haloarchaea are able to tolerate. And they have a large number of DNA repair systems, both bacterial and eukaryotic. And those are listed here. They everything from direct photo repair using photolyase to nucleotide excision repair using EVR ABC, mismatch repair, and other types of DNA repair, including recombinational repair. So just as an outline, these are the mechanisms for UV light repair. So you can see that UV will generally produce CPDs or thymine dimers. And in the presence of visible light, you can carry out, or haloarchaea can carry out light repair, which uses a protein called photolyase. In the case of dark at night, they can do dark repair, and this is using what is called an endonuclease, which excises out a fragment of the DNA, and you can see that in the lower panels. And there's actually a video for this. If you go to the MolGen tutor, and unfortunately I don't have the updated URL there, but I can give you that, or you can just Google MolGen tutor and you will find it. So haloarchaea are highly tolerant of UV radiation, and you can see that in the survival curves on the left, compared to E. coli or yeast, certainly human. The survival is much higher, and it's a little bit less than Deinococcus radiodurans. But in the presence of light, it's fairly close. And we've done a fair number of biochemical and genetic studies with this. And I just want to show you one where we mutated the UVR A, B, and C genes, or A and C together, and we found that those are no longer able to survive as well as the wild type on the left-hand panel. And we also studied which genes are being turned on using transcriptomic analysis, and it's actually a fairly small number of genes that are being turned on. So we recently studied the UV sensitivity of other Haloarchaea, not just NRC1. And you can see in the 9 panels on the left, these are organisms that we've isolated or obtained. Most of them are our own isolates. Halorubrum lacus profundi was isolated by the Australians. And you can see the red curves show the survival. So the higher up it is, that means that it has a higher survival in the presence of light. So they have very good, the top 3 in particular, which are Halobacterium species, all have very good light repair systems. In contrast, the ones at the bottom, ball 5.1, 6.1, and 5.4, these are all isolated from subsurface Permian mines. They have very low light repair systems. And so we've studied this in some detail. We published a paper recently in Microorganisms on this. And you can see on the left the genetic arrangement of the photolyase gene in red. And one of the mine organisms, for instance, is missing the gene entirely, the photolyase gene. And several of the other ones, like 5-1 and 6-1, have the photolyase gene, but it seems to have a number of amino acid changes that likely make the protein less functional. And that's shown in the table on the right. I don't have time to go through the details of this, but you can find this paper in the MDPI journal Microorganisms. The first author is Sigorka Nag. And you can see, for instance, compared to NRC1 here, ball 5.1 has many different amino acids, as does ball 6-1. There are also some differences with ball 3-1 and HLA, but not so much with JOR1, which has actually an excellent UV light repair system. And the paper also goes into the structural analysis and shows what the impact is of the mutations in these mine organisms on specific residues for the photolyase protein. So we've also studied ionizing radiation in Haloarchaea, and in this case, NRC1. And NRC1 has a remarkably good ability to survive high doses of ionizing radiation. In this case, this is an experiment we did with Linda DeVoe with linear accelerator, electron beam radiation. And you can see in the gel on the left, when you irradiate with high enough dose, you break the chromosome or the genome into small pieces. These are about 50,000 bases. This is about 2 megabases. And then after a few generations, it stitched it back together. So what we did with the DeVoe lab was to carry out a set of sequential killing experiments with the linear accelerator. So we exposed it to about 20 kilograms of radiation, and then we allowed it to recover. We did this several times, and we isolated mutants, LH7A and LH5, for instance, and we tested its ability to survive different doses of ionizing radiation. And you can see here's the normal wild type NRC1. This is Deinococcus radiodurans, which is just a little bit more resistant. But you can see that these mutants are even more ionizing radiation resistant than Deinococcus radiodurans. And we carried out transcriptomic experiments, and we showed that there's a single operon that's upregulated in these mutants, which is the RFA operon. The RFA operon codes for a single-stranded DNA binding protein, which is similar to the RPA protein of eukaryotes. we were also able to overexpress the RPA protein in wild type. And here you can see that the engineered strains are more ionizing radiation tolerant than the wild type. So the model for this type of DNA repair is taken from yeast. This is a model for yeast. So the idea is that ionizing radiation or desiccation would result in breaking the DNA into having double-stranded breaks, breaking into many different pieces. And the RPA protein would bind to the 3' ends that would be created after the breakage. And then through the process of use of red 51, which in the case of archaea is red A, one would then repair these double-stranded gaps using double-stranded gap repair mechanisms. So this is the mechanism that we think is operating in Halarchaea. So now I want to bring it all together and talk about the possibility of Halarchaea surviving on Mars. So in order for this to happen, Halarchaea would have to be surviving a lot of different extremes. And we've talked about, ionizing radiation, ultraviolet radiation, cold temperatures. All of these are present on the surface of Mars. And so we wanted to find an analog on Earth to determine whether Halarchaea could indeed survive all of those extremes. And so the analog we chose was the stratosphere. And the stratosphere is very cold, similar to Mars. There's very high UV flux because it's above the ozone layer. It's also, of course, exposed to cosmic rays and electrons and protons, and it's very low pressure. It's similar to the pressure on the surface of Mars, and it's incredibly dry, not too dissimilar, a little bit less dry than on the surface of Mars, but fairly similar. So we did a set of experiments with a group of students in California, where we sent them organisms to launch into space using helium weather balloons, and they reached a height of around 33 to 34 kilometers, and they stayed at this height for about 2.5 hours, and then they burst and they came down, and then the students mailed the experiments back to us for testing in our lab, and we tested 2 different organisms, Halobacterium NRC1 and Halorubrum lacus profundi, and this is what we obtained. So we found that so we had controls that were just stayed on the ground or went back and forth by airplane, but didn't go up on the balloon, and then there were the experimental ones. And you can see in the third panels here with Halorubrum lacus profundi, there was better survival than with NRC1. So you can see that also here, that you have this is the airplane is in red, and the balloon is in blue. This is NRC1. This is Halorubrum lacus profundi. So there's a little bit of killing, about 2 orders of killing with NRC1, but in Halorubrum lacus profundi, they were actually able to almost survive fully in the stratosphere. So our hypothesis is that Halorubrum lacus profundi is able to tolerate the cold temperatures better than NRC1, and these are just growth curves at 4 degrees. If you just compare the 4 degrees, the red is Halorubrum lacus profundi, and blue is NRC1. So they're able to tolerate are able to grow in much colder temperatures. And they're also able to survive freeze thaw, which happens when the samples are sent up to the stratosphere and then back down. And so we've done some transcriptomic comparisons of these organisms. And again, I'm sorry, I don't have time to go into the details of the experiment, but the upshot of it is that Helarubrum lacus profundi, I hope you can see this, has a large number of genes that are regulated by temperature compared to NRC1. So there are 5 times as many genes that are up or down regulated. So they have a much more sophisticated biological regulatory system for dealing with cold temperatures. And that makes sense because, of course, Helarubrum lacus profundi was isolated from an Antarctic lake. So, and then finally, can we use Haloarchaea for detection of life elsewhere? Well, on Earth, they form these brilliant colored ponds, and they have a number of different pigments, including the bacteria rubrans, beta carotene, and of course, retinal in the purple membrane. And retinal, we noted, was one of the simplest pigments in the wide diversity of pigments that are present in nature today. Compared to, for instance, chlorophyll, it's a much simpler pigment. And another observation that we made was that purple membrane has a absorption spectrum that's complementary to chlorophyll pigment. So you can see that in the center, purple membrane has a absorption maximum in the green-yellow region, about 568 nanometers, whereas the chlorophylls have very little or no absorption in that region. So they are essentially avoiding that region. And instead, they're absorbing in the blue and the red. So we hypothesized that these two types of pigments might have co-evolved in nature. And if one looks at stratified communities of organisms, and this hypothesis you can see in the PBS EONs and CNN color scope videos that are out there. So the retinal is also produced prior through pathways prior to the TCA cycle, which is not true for chlorophyll. So it would appear that retinal might have evolved earlier before there was a oxidative TCA cycle. But this could have happened in these stromatolites, which are these microbial mat communities, which one still observes. For instance, this is in Shark Bay in Western Australia. These are mounds of microbial mats when one can observe in low tide. And there are fossilized versions of these, as you can see here on the bottom right. And some of these fossils are over 1 billion years old. So this type of process has been going on for a long time. And you have these stratified layers of communities of different phototrophs. And so it's possible that the Bacterodopsin may have dominated the Earth prior to the development of chlorophyll-based photosynthesis, and this has been dubbed the purple Earth hypothesis. And so in terms of being able to actually identify or use this as a remote signature, and I think you'll hear another lecture perhaps about this in future, but I just wanted to leave you with this kind of a picture. So these are actually aerial imaging that's been done by NASA scientists of these solar salterns where Haloarchaea are present in very high quantities, numbers here. And you can see that they absorb here in this around 568 is the maximum. So if you're looking at a reflection, you would actually see a green edge. And my collaborator, Eddie Schwieterman, who I think you'll hear from, has done some modeling and shown that that compared to the forest, where you would see a red edge, you would see this green edge. And in fact, he predicts that the region in which you would see the green edge, around 680 nanometers, is actually a very good part of the spectrum to be looking for life elsewhere, as opposed to the 570 nanometers, where you would have a lot of spectral interference from water. So that's a lot of stuff. I hope I haven't overwhelmed you or anything by this presentation, but we've been working for a long time. I wanted to give you a sense of all of the different things that we've done over the years. So in conclusion, I wanted to say that these modern haloarchaea are polyextremophilic, and they're probably derived from ancient microorganisms that evolved prior to the Great Oxidation event. There's been a lot of horizontal gene transfers, so this a combination of vertical and horizontal inheritance has played an important role in their evolution. Proteins have evolved surface negative charges in order to function in high salinity and low water activity. Bacteriodopsin, gas vesicle nanoparticles, alternate electron acceptors, and fermentative substrates allow growth in a lot of low oxygen conditions. And then survival mechanisms to both ionizing radiation UV include both bacterial and eukaryotic repair systems. And they survive in the cold stratosphere, and suggest that some haloarchaea may have the potential to inhabit Mars. And finally, that haloarchaeal pigments may serve as biosignatures and have the potential to answer questions about the possibility of life elsewhere in the universe. And so I just wanted to acknowledge there are a lot of people who've contributed to this work over the years. I've listed some of them, not all of them. I've worked for the last 25 years with Priya Desarma, who has contributed to all of these different projects. Victoria Lay, Sean Kennedy, Victor Ng, Melinda Capes, Jung Hyun Kim, have all been PhD students in the lab. Sagorka Nag recently was an intern, and Leonardo as well, and who's now a graduate student with me. And the collaborators, I just wanted to mention Mark Krebs, who was at Wisconsin, is now in the Jackson lab, Eddie Schwieterman, Joan Slonczewski, who wrote the textbook on microbiology as well, Vince Foltz, who's a biophysicist at Temple, David Crawley at Assumption University, Rich Roberts and Brian Anton at New England Biolabs, Shirley McGreedy at Oxford Brookes, and Linda DeVoe at Idaho State. And of course, funding, and our most recent funding has been, a lot of this work has been funded by NASA, although NIH and NSF have contributed to it also over the years. So I'm going to stop now, and let's see. I hope you guys are still with me. I haven't lost anyone. Oh, good.
No, we're all here, and thank you so much for this presentation. It was so good. Really, it was enlightening because you talked on a lot of topics, a lot of different topics, but concluded all of them in one. So it was really nice to be able to watch this presentation, really.
Thank you so much. You're very kind. It is kind of special to be able to spend a lot of time on one system. So I took a decision early on in my career to focus on the haloarchaeal system, because there was so much to learn. And with NASA expecting to return samples from Mars in the 2030s, younger scientists among us can take the view that maybe we can study something that is from Mars. But when I started my lab in 1986, no one was talking about returning samples from Mars. So this is as close to Mars as we could get here on Earth.
Yeah. Also, it's like very clear that it's our future, and we have to know as the new biologist, new geneticist, and yeah, I think it's really eye-opening to hear all this. And now we have some questions. So the first one is, where and how macromolecules and building blocks were formed before the first cell formation?
Well, that's a wonderful question to pose. And as I mentioned, the last universal common ancestor probably already had a genetic code, and it was probably pretty similar to what is used in essentially all the organisms today. And if our fossil records are correct, this was in the first billion years of the planet's history. So what we're talking about when we're talking about prebiotic evolution would have been in that time frame. So that is, of course, the big mystery. In order for cells to have evolved, you had to have a membrane. And in fact, the Bacteroidopsin story said that the membrane gives an immediate mechanism for energy transduction. If you can move ions across the membrane, you can create a potential, you can create a gradient, and then you can generate ATP from that. But in order to get to that cell, let's say the first cell only had Bacteroidopsin and ATP synthase, and it would generate ATP, and then ATP is the energy currency that's present in everything. And so the energy currency could then be used for production of everything else. But you have to have a situation where you form a membrane first. And that has to be in the prebiotic evolutionary stage. So how did that happen? And the best answer I know is from the work of David Deamer at the University of California, Irvine, I think. And actually, I think it's in Santa Cruz, excuse me. So what he thinks is that there's a process of wetting and drying through, evaporation and rain, that process has resulted in formation of these early building blocks. I like that idea, and even over a billion, it's hard to imagine, but can you imagine how many times there would have been wetting and drying over 100 million years? So it's hard to predict what might have happened over the course of that time.
Yes, that's interesting. Also, could I ask you to close your share screen because it echoes sometimes? Thank you. Now, another question we have. Okay, how are bacterial genes and archaeal genes can be determined?
Exactly. So that's a trick, right? Because if you look at Haloarchaea, and 30% of the genes are bacterial, and the 70% are archaeal, it's who's to say that the 30% isn't what the origin was, and the 70% invaded the 30%. But I think most people are just going by the 16S as the molecular chronometer. If you have an archaeal 16S, then you're an archaeon. If you have a bacterial 16S, then you're a bacterium. And so if the gene is more highly prevalent in the bacterial organisms, then it becomes a bacterial. But completely, it's a semantic argument. there isn't, that's a really good question, I have to say, and not one that people usually ask.
Great. And another one. Do we have any cloning experiments to create a more durable extremophile, like a superbug, like cloning TACPO2D radiodurans to create a bacteria that can survive both heat and radiation?
That's a wonderful idea, and people have, of course, done experiments to show increased tolerance to specific stressors. Like, for instance, in the case of ionizing radiation, when we isolated through multiple rounds of killing doses more highly ionizing radiation mutants, then we went back and we overexpressed the RPA genes and then tested and found that those were also more highly radiation tolerant. So that's just looking at one. But it depends on what you want to achieve. So maybe you want to make an organism that can be used to grow food on Mars. Then you would have to think of something that can grow in the cold, can tolerate ultraviolet, can grow anaerobically, can metabolize or use perchlorate as a terminal electron acceptor. So you'd have to, it would be a very interesting exercise for your generation to come up with this superbug that would allow us to colonize Mars, for instance.
Actually, if we were to ever grow plants on Mars and we were be able to do that, we could use some nitrification bacteria too, which would be, I think, logical. So
if you could grow plants, you would want to grow legumes that have some ability to provide nitrogen or whatever else that the plants would need, because you would want to have high protein content. Right?
Yeah, true. Let's say there is a life at any point in space, even at the microbial level, and somehow bits of this microbial life came out to our world preserved. Assuming that they continue their life activities in the living conditions of our world, can we say that people can live without any protection on planet that they came from?
If I understand the question,
so if there were to any microbial level activity in another planet, and if we were to go to that planet, could we live with less protection or no protection there, hypothetically?
right. Yeah, so there's a hypothesis called the Gaia hypothesis, which says that the Earth itself is a living planet, and that that all of the organisms produce. They're sort of working in concert to produce the environment in which we all live. And in fact, the climate change is one of the wrinkles in the Gaia hypothesis, because if you increase greenhouse gases too far, you won't be able to buffer the system for all life to flourish. So I think this question kind of gets at that kind of, how do you get to a planet where you have a diversity of life, and there has to be some cycling of the different elements and things that allow conditions for a variety of living systems to thrive. So those are, ecological questions that are really worth thinking about. And, I think Mars is actually a pretty good analog to Earth, because in the first billion years or so, there's probably a lot of water, and it unlike Earth, it didn't hold on to it. So things can happen in the history of a planet where it can be living for a while, and then something happens so that it's no longer able to support life. So as we look at these exoplanets, and as the astronomers are able to tell more and more details about, the conditions on those planets, who knows? I mean, I think these are really relevant questions that we may be able to answer through actual experimental analysis of other planetary bodies.
Thank you. Also, in a hypothetical planet where we can grow archaea, but its life is tested to its limit by another outer effect such as radiation, could it evolve, or can we use genetics to grow them in other limits?
Yeah, I love that. I love that question, and I would again go back to the radiation experiments that we did to show that indeed you can isolate more resistant organisms. Interestingly enough, it's not always true, though. So, for instance, when we published the organisms that are more radiation tolerant than Deinococcus radiodurans, it was pointed out that people had tried that with Deinococcus and had not been able to achieve it. So it depends on the organism. It depends on the extreme that you're looking at. There are going to be limits, I think.
Mhm.
So, there probably, at least in terms of life as we know it, there are probably limits that we cannot surpass. And if you think of it as humans, we can very easily think about conditions that we cannot really tolerate. And again, going back to the climate change, if the temperatures are above 90 degrees with a certain amount of humidity, we just won't be able to tolerate that. Now, could you say, well, could you find mutants that who would be able to tolerate that? There may very well be people who can tolerate higher conditions, but it would have to, you would have to think about changing the basic biochemistry. It's like with the Haloarchaea, they have as much salt inside the cell as outside the cell, and all their proteins are negatively charged. So you'd have to do something really radical like that, I think, to be able to achieve, certain growth and conditions that would extend our ability to grow in certain extremes.
Mhm. What are the proposed hereditary models for a hypothetical non-carbon-based life form?
That's a really interesting question. So I was trained as a chemist and a biochemist, and I find that my thinking is constrained by my knowledge of biochemistry. Um, so and chemistry, and if you look at the periodic table, and you see carbon, you see the atoms, the elements that are found they're used in life, right? uh, you know, Carbon, hydrogen, oxygen, sulfur. It's just a small number really that are really critical. Those have some special properties because they're at the upper part of um, the periodic table, and they don't have, they're only filling their first two orbitals. They're not filling their f orbitals and things like that. But if you so the atoms that have similar elements that have the similar properties are in the same columns, right? So below carbon, there's silicon. So you could imagine a silicon-based life. But silicon on Earth is sand, right? It doesn't have the same sort of chemical properties because of the fact that it's a different element with more protons and electrons and more orbital shells. So it's possible that you could have life that's based on silicon, and we just don't have that here because the carbon-based life is just so prevalent. And didn't give the chance for something else to grow. But if the conditions are different and they're right, I'm skeptical, but I have an open mind that there may be life forms that are non-carbon based.
Mhm.
But I'm skeptical.
This is actually really like the subject itself is really engaging, but I'm like taking notes at this point. Like, remember this, search this, keep in mind. Let's see. Another question is, on other planets, is it possible to create a living creature suitable for the conditions of that planet, or is it possible for existing living things to evolve according to the conditions of the planet?
Right. I think if it's endogenous life, then it would probably have evolved to tolerate or utilize the conditions that are prevalent there. And if it's something that came from elsewhere, then it may not have be optimally evolved to grow in that environment. And people talk about like seeding of planets like panspermia, and even for the Earth, it's possible that there are different asteroids or comets that have amino acids and things. That there are ideas that these things may have come to the Earth and then evolved. We know that some of the Martian meteorites actually have halite on them, sodium chloride crystals. So since haloarchaea can survive embedded in crystals, it's possible that they might have been transmitted from one planet to another, between Earth and Mars, for instance.
Mhm.
But we don't have any actual evidence to show that occurred. But now as we go to colonize Mars, I may imagine that this is something that humans will want to do in the next century. The question that's being posed is really highly relevant for that.
Mhm.
What's going to happen? We need to understand that before we actually plan these
Yeah, definitely. And thus chlorophyll is the only pigment that can do photophosphorylation, or the other pigments that can produce ATP also count as photophosphorylation different than green color.
Yeah, that's exactly right. So the purple Earth hypothesis says that the retinal-based pigments predated the chlorophyll pigments, and so the original phototrophy on Earth is not chlorophyll-based. However, this is just a hypothesis; it's not proven, and this is for your generation again to address. How did chlorophyll become so dominant? I don't imagine that it was always so dominant.
Mhm. What is a different mutant example for a very strong life-limiting element other than NRC1 enduring radiation? But I believe this question was asked to question for another limiting element other than radiation.
Right. So if you're talking about element as a stressor, is that what you mean?
Yes,
Okay.
I think so.
Yeah. The other um, extreme is just dryness, right?
Mhm.
Uh, and Mars is very dry. It's even drier than the stratosphere, but there is water there, right? There's the ice caps are uh, the polar caps have ice in them, and there's even at lower latitudes, you can find subsurface, just beneath the surface, there's frozen ice. So those are two extremes, right? First is that it's cold, because anywhere the temperature is high enough, the water is escaped.
Mhm.
So in order for life to survive there, you would need to have enough uh, capability to hold on to water and to be able to survive or to grow under freezing conditions. So those are a couple of extremes. So you'd have to ice, and even though we see this with Halorubrum lacus profundi, if you grow it, it actually its optimum growth temperature is 30 degrees. But so if you take it when it's growing at 30 degrees and you throw it in at 4 degrees, it doesn't grow for a while. But if you wait, it adapts, and ultimately it starts growing. So it grows. We have cultures growing in our cold room at 4 degrees. And then you can take those cultures and you can put them at lower and lower temperatures progressively, and they will adapt and grow. And we haven't really studied the basis for that. And I think it'd be very interesting. Why do you have a lag at the lower temperatures? Do you have to produce a particular set of proteins, or are you actually isolating mutations? And we went down as far as -2. And that experiment took 6 months. We could see growth at -2. And it's not frozen because of the salt, right? So the salt, actually, you could go down as far as -20, and it would still be fluid. But the generation time increases, right? So you may have a generation time of 6 months at -2. Then the question becomes, if you go down further, and the generation time comes 100 years or 1,000,000 years, is it growing? Is that life? If something replicates once in 1,000,000 years, it becomes philosophical at that point, right? It's a philosophical question.
Yeah, it's like there was a tree that I learned, 100 years tree. It only flowers once in 100 years. I really like that one. Also, could you repeat the name of the archaebacteria that you just told, like the name of it?
It's called Halorubrum lacus profundi. It comes from Deep Lake, Antarctica, and it's we did the genome. Actually, that's a paper that we published together with Carl Woese. So if you look up Woese and Desarma, that paper will come up. So that organism, Lacus profundi, it comes from the root, I think from the Latin root, is Lacus profundi is deep lake. Lacus is lake and profundi is deep. So that's why. And it's a Halorubrum genus.
Wow. Another question is there a study that we try to gene editing on other species, such as plants, fungi, etc., DNA or RNA, in order to add these archaeogenes that might increase its durability in space?
Yeah, I don't believe any. I don't know of any, but of course, people are trying so many different systems. I think the idea of having communities is a very idea, because going back to the Gaia hypothesis, that we actually don't really exist by ourselves, right? If you think about it, we grow all sorts of things, many plants and things in order to provide food, and now we're thinking about trees for sequestering carbon and things. We are all interdependent. And so this is another area of community analysis that's very important for the future. How will we plan on having a trip to Mars, which will take 2 years? Would you would you put people in a deep sleep and then they would wake up in 2 years, or would you expect them to sit in a spacecraft for 2 years and just look out the window? Uh, if you had some plants, it might make it nice. It's nice in an apartment. I know my daughter has a lot of nice plants in her apartment, so it pleases us. And so, there are psychological as well as physiological and environmental reasons why you would want to be thinking along these lines. But to be honest with you, my generation has not really thought about these issues because we were, I was raised in the Apollo moon generation. I remember watching the Apollo when I was in school,
Wow.
the missions, and it was really inspirational. And the picture of Earthrise, I don't know if you've seen that, but the Earth rising over the moon that was taken by the Apollo mission, it just changed the whole idea of planet Earth. And but that was, there were limits to what we could do, and that was before the computer revolution. I mean, there were computers then, but they were large. They were not microcomputers, and so things have evolved, have advanced, and I don't really think that someone of my generation can do justice to the kinds of questions that you're posing here. I think you have to think about these. This will be your legacy that you will leave to the future generations. What is the future of humankind? What is mankind's future? So the Mars is a beacon in that sense, even more than the moon, I think.
Mhm. Also, with the SpaceX and NASA launch, like every other month we have a launch and we can watch it online. So I think it's impacting us in a way where it's like very usual to us. So I think we can, as a generation and like the generation that is next to us, is gonna do great things. And now we have run out of time, unfortunately, but it was so great to have you here. It was such an honor, and truly we had so many topics that I was interested in, our viewers were interested in. We had so many questions, and this was just great. So thank you so much for coming.
Thank you. That was really wonderful, and I really appreciated the opportunity.
Thank you. I hope we see you again in the future, and have a nice day.
You too. Bye.
Bye. Now we're gonna have 5 minutes break, and then we're gonna come back with Mike Simmons. See you again.
Hello everyone. Now we will continue the topic of the importance of astronomy with Mike Simmons. Mike Simmons has been an amateur astronomer and outreach leader for more than 40 years, including leading and creating outreach organizations. He is now an affiliate research scientist at Blue Marble Space Institute of Science, where he is creating programs addressing issues of diversity and inclusion using astronomy and space. Astronomy for Equity. Hello, welcome to our conference.
Hello, Ezra. Thank you for having me.
Thank you. We're so glad to see you.
It's good to be here.
How are you?
Oh, very good. Thank you. It's morning here in California.
Yes. Sorry about that. If you're ready, you can share your screen and start your presentation.
Okay. Well, today I'm going to talk about something that's a little bit different than talks such as the last one. Yeah, all of you are studying astrobiology or any other aspect of astronomy. I know you get questions from your family and your friends. Why are you studying that stuff up there? What importance is it? How are you going to make a living? So I'm going to talk about the importance of astronomy as I've seen it over the years. So starting the screen share, let's see. We will have window and entire screen. There we go. All right. So you should have my screen there.
No, I can't see.
I see it down below. There we are.
Yes, I can see now.
Okay.
The stage is yours. I'm going now.
Okay. Thank you.
Thank you.
So, you know, we're all fascinated by astronomy. We know why we want to do this. We know why we want to think about life on other planets and so on. But is it just because we feel like it? Is astronomy really important in some way? Anyway, well, you know, there are ways in which it really is important. I'm going to talk a fair amount about what to expect from astronomy around the world. You're used to seeing it in Turkey. Others who are here from other places are used to it in their countries. But it's really kind of an isolated science, something that doesn't seem like part of the mainstream until there's some great discovery or a rover lands on Mars or something, then everybody wants to know about it. So a few things about astronomy. First of all, astronomy is really universal. I mean, what's kind of an oxymoron. The universe is universal, but it's in every culture throughout history. So in Turkey, in every place else, every culture, we find ancient artifacts about astronomy. And it's part of everything that we do. I mean, even if you're giving a rating for a movie, we use 5-star reviews or something like that. If you think about it, the great deal of what we have in our culture has to do with astronomy and the stars. Everyone is fascinated by astronomy. This is something that makes it really different than everything else. People are always interested in finding out or learning about whether or not there is life on other planets and so on. But the chemistry, the biology, and so on, not everybody is as much into that, but there isn't any place that you go that people aren't as interested in astronomy. It's practiced in every single country. So I've worked with people around the world, and in the most unlikely places, you find people who are doing astronomy. If they can't be professional astronomers because of the situation in their countries, there are amateur astronomers. And I've even been to places where there are amateur astronomers who are sharing astronomy with the public, but don't even have a telescope. I try to help them too, and I've gotten telescopes for many of them. I'll show some examples here as well. And astronomy is the same worldwide. So a geologist can say, well, we have rocks everywhere, but they aren't the same rocks. There's something different about something where everything is exactly the same. So if you are at the same latitude anywhere around the world, you will see the same sky. It's true if you go south, you see a little bit, you'll see different stars and so on. But astronomy really is the only thing that is planet-wide exactly the same. And it makes sense because it's our environment. Everywhere we go, the environment changes, but Earth has the same environment. It doesn't matter if I travel from California to Turkey, the space around us is the same. So here are just some examples, and I have a lot of demonstrations of things like this. Here's a picture of the moon rising over the Taj Mahal. Also one rising over the Acropolis in Greece, and rising over a building in Yazd in south central Iran in the desert, rising up behind the skyline of Boston in the United States, rising above the coast of Brittany in France, where they're trying to get it into a little different position for a better picture, I guess. But the moon looks exactly the same. We see the same thing when we look up and look at the moon. We can be looking at the same place. It's something that we don't really think about very often. But imagine you are on a bus, everybody looking out the window seeing the same thing. And maybe the people on the other side are looking at a different window. They see something different. But when you turn around, you see the same thing. Everything around you is really the same. We're just looking out different windows, but what we see up there is exactly the same. Well, here are some pictures of the sky from different places. And the thing that's striking, as with the moons, is that these could be anywhere. They happen to have chosen foregrounds that show where they are. And I recognize this as Yosemite Valley in California. And we recognize the Moai on Easter Island, showing our galaxy, the Milky Way, and a couple of other galaxies. A very similar view, the other side of South America at Iguazu Falls on the border of Brazil, Uruguay, and Argentina. And this scene could be in California. We have some dunes like this. This exact same picture could have been taken here. In fact, it's taken in the central desert of Iran. And so the differences that we see between us and the different places around the world are local. Earth is just one little place. It's a locality. But the universe we're a part of is, much bigger, and it's the same for all of us. Okay, now I'm going to show some pictures just to give you an idea how universal your interest in astronomy really is. One of the reasons for this is because, you may feel like, well, you have a small club or you have a small group and you're all interested, and other people outside, they're not interested. So I can tell you that you are far from being alone in the interest for astronomy. In this case, these pictures are coming from at first here from an event I ran for the International Year of Astronomy in 2009 called 100 Hours of Astronomy. We had tens of thousands of telescopes out around the world in one night, maybe 1 million people looking through telescopes in one night, which is amazing. And it was all one night. The people, as darkness went around the world, it went from one to the next and the next. So this was a star party that lasted for 24 hours. And one of the things you remember too that's interesting and very different about astronomy is that very few people have ever looked through a telescope, and they don't know anything about it. So if you're a botanist, you don't have to explain to people what grass is or what a tree is and why they're different. If they see a tree, they know it's not grass, it's a tree. But people don't know what a plant is. I mean, of course, they know what a plant is. They don't know what a star is. They don't know what a planet is. They really don't understand even the sun that gives us life and the moon that's up there. They're not sure exactly what these things are, and they don't know what they can see. So here we have somebody who's offering his views during that event in New Zealand. Well, here is an array of very small telescopes. They had 100 telescopes for 100 hours. This was in China, of course, where they make these things. This is the biggest one I know of. This was in the United Kingdom, where they had a smaller number of people who got very big looks through the telescope. To Pakistan, where people were viewing this, again, the same event. This was in Baghdad. I had been to Baghdad a while before that, just before the war. And this was during the war. They had 500 people there. And this was at a time when suicide bombers would target crowds. And they said, we're not going to skip this. We want to be a part of this. The whole world is taking part of this. And they felt very alone, but they were a part of this planet-wide event, and they came out for it. People in Bangladesh, they made their own shirts and everything else. This is in a Muslim country in Southeast Asia, I think, and I always forget where it is, but I love the stars on the robe there. And a girl looking through a telescope in Kathmandu in Nepal, also looking through a telescope in India and in Iran. And in northern Iraq, in Kurdistan. This is a telescope I actually took there for the amateur astronomers there when I visited. And he's in traditional clothing. Here is exactly the same picture. Same kind of telescope, pointed the opposite direction. Traditional clothing, it happens to be in the Andes where they're wearing their traditional clothing as well. But the scene is exactly the same scene. And different parts of the world almost opposite each other. But they're all using the same telescope, looking at the same things, doing the same thing. Here's a single sidewalk astronomer in California during the solar part of it. And I'm sorry, where am I here? Yeah, there. Showing the sun during the daytime. Here's a big group together in Argentina at a star party, bringing out lots of people. For the solar part, here is a group in Oman. Now you can see some pictures of countries where you may not know about, or you'd be surprised that they're doing astronomy. It doesn't surprise me anymore. They just do everywhere. I've forgotten which North African country this is in, but I recognize that it's one of the countries in North Africa, down towards the south a little on the edge of the Sahara Desert. Again, back in Pakistan, another city there. So what do you do if you really want to be a part of this big event? You don't have a telescope handy. Well, like I said, a lot of people do outreach in astronomy. They don't have a telescope. And in this case, though, they did have a camel. So what do you do if you don't have a telescope, but you've got a camel? Well, you make a camel cart and you take displays. And look at the kids crowded around. I mean, and they're not looking at the camel. Maybe they're used to camels. I'd be looking at the camel. But they're looking at the things about astronomy that are being explained to them there. Well, solar observing, again, translated 100 hours of astronomy. There on the side of the telescope with a child looking through and another looking through. And this, I love this picture. This could be taken anywhere in the world. If you do astronomy outreach, this is why you do it. This is the payoff. You don't get money from it. You get something like this where children go, wow. They see something they've never seen before, and it expands their universe. You suddenly now are not experiencing just what's here on Earth, but you are seeing, in this case, the sun in H alpha. You're looking at the planets that you can look up and see with your own eyes. People don't realize that. So suddenly, it isn't just everything you see down here. You're part of something much bigger. And everybody loves to share the views through a telescope, including this young girl in Brazil who wanted to make sure her doll got a chance to take a look as well. Well, moving on from that, there are I have a few pictures I think are demonstrative from other places. This was a telescope that was set out in Bhaktapur, Nepal. It's not Kathmandu. It's not a huge city. I'm not sure how big it is, but this is what happens. You put out a telescope. In this case, maybe it was just looking at the moon, and the line forms behind it. Everyone wants to take a look. They don't know what to expect, but nobody walks away disappointed. You know, how often do you produce something that you can give to everybody for free and everybody's happy about it? So this is an experience that few people have had. Astronomy is everywhere. It's endangered in some places. Now, these are schoolgirls looking at the sun through solar viewing glasses made for looking at eclipses or at the sun and sunspots and so on. But I am in contact with people in Afghanistan, and now that the Taliban is in charge, they are not able to do what they were doing before, because some of the things that we know about the universe, they may conflict with what some fundamentalists feel is taught by the Quran. It's a matter of interpretation largely. And they don't really like it. And they don't like educating girls. And they don't like a lot of things. And so astronomy is not something that they can practice freely. But this is kind of rare. I've found in the Muslim countries I've been to, and certainly in Turkey, but also in more stricter ones like Iran and Iraq and some others, that astronomy is considered to be really a gift from God, and that it is something that we must celebrate, the universe as a whole and being a part of it. Well, this one too, you have to watch out sometimes when you get into a place like this. This is in southeastern Iran, and I do go to Iran a lot, so I have a lot of pictures from this. I wasn't at this one, but this one is another beautiful picture of the universe with something in front. It's not a monument or a hallmark of some sort in this case, but an armed guard, because this happens to be along the smuggling route from Pakistan for drugs, and so there can be trouble there. So they wanted to be out and enjoy the night sky, but the government gave them a guard just to make sure everybody was okay. So instead of a telescope with the Milky Way, we have this, a bit different. You know, astronomy in most of the world, and this is different than here in the US. Here, it's mostly older guys like me who got into it when we were younger, and we've gotten old and white-haired. Women are joining now, but it's still mostly men. And it's not as many people of color. That's changing as well, fortunately. But the young people here aren't as interested in taking part as amateur astronomers. But in the rest of the world, it's just recently discovered, and it's all young people. In this case, in the Philippines, and you'll notice in these that it's mostly women as well in many countries. So the Philippines here, this is in Vietnam. Here's a picture I took in an educational observatory in northern Tehran. And I didn't realize until later when I looked at this that there's only one boy in this. And otherwise it's all women. And these are the things I've learned by connecting with people and going to these places around the world through astronomy, is that Iran is completely different than I expected. Maybe some of you have been there because, but for Americans, they don't know anything about it, and it's completely different than I thought. And in this case, the women dominate the universities and colleges, especially in the sciences, which is, of course, different than here. Well, they're all types. I've met this guy. He's in a different city now in Isfahan in central Iraq. I recognize by the mosque in the background. But I usually see him at the tomb of Hafez in Shiraz in southern Iran, the poet and astronomer. So it's just an example of all the people that are interested in this sort of thing. Of course, In the Muslim countries in particular, sighting the crescent moon is still very popular, as many of you know here. Even if you're not using the first sighting of the moon to start the month, as is traditional, it's still part of the culture. And that's an important part of astronomy too. This is part of our culture. There are so many things that are sciences that, you know, they have a history of a few hundred years or something since really the scientific revolution. But astronomy is and always has been a part of our culture. So a crescent moon above a mosque has a particular meaning. I'm sorry, I don't know exactly where this mosque is. I don't recognize it. And here, some amateur astronomers out waiting for the sun to get low enough that it will be dim enough they might see the very, very thin crescent moon. Well, astronomy is also accessible, and I think I've alluded to that. Everyone has the astronomy laboratory. So if I go out of my house, I'm in the hills in Southern California. The sky's better than in the cities, but the cities are too close, and I don't see that great a sky. I used to see the Milky Way quite easily, but either the sky's gotten brighter or my eyes have gotten worse, probably both. And so I don't see the Milky Way at all really anymore. But if you're in a developing country or in a rural area that we think of as not being having resources, you have a better sky up there than the rest of us do. So a school someplace, I'll show some examples, may have no resources of any kind, but this is an unused resource here. You go walk outside of the classroom at night and you see something that most of the people in developed countries will never see, which is a sky like what this observer is using right now. There's no equipment needed for this special laboratory. Having binoculars like there is nice. Having a telescope is nice. But, you know, astronomy was a science for centuries without any optics of any kind. And it's very easy to get some inexpensive optics like what we have here, some binoculars or something. But there is a lot going on with the planets and the moon moving. I mean, people figured out a lot of things from looking at the sky, including the nature of the Earth itself. That it is a curved surface, that it is round, as well as the nature of the solar system and relative distances to a certain extent. So here's a classroom in Rwanda. They don't have any labs of any kind. The teacher there is holding what looks like it might be Uranus or Neptune. These are things that they can talk about. And if they're lucky enough to get a telescope, they could see one of those planets. Or if it's really dark, you can actually see Uranus. I don't know if they'll do that, but this is something that fascinates the kids there too. And this is done in places where you think, well, I think they really need other things more than they need astronomy. Well, not necessarily. I've been asked that when I've raised money for places in Africa to get telescopes. I think they need food more than they need telescopes. Well, that's true. But here, for example, this is a United States Peace Corps class in Tanzania in East Africa. And they are studying science. And I was contacted by the young person doing this. They wanted to include astronomy because they want to learn science, because they want to be these different things. One wants to be a doctor, another a teacher, another a laboratory technician. What chances do they have to learn science, to be introduced to science? They're not, you know, if you want to be a molecular biologist, you're not going to just start studying it in high school, getting into college and stuff. And even there, it can be difficult. So you start introducing people to science. Not only the people like this who really want to study science and have an opportunity through astronomy. Oh, and there's another important connection too. This is an astrobiology conference. So astronomy is connected to every other science. including biology and chemistry and all the things the other speakers are teaching about here. Not everybody's going to be able to become a biologist right away. Many people, and I've seen this happen many times, are interested in astronomy. They get inspired by it, and they go into the sciences, not because they wanted to end up being an astronomer, but because they were exploring through the telescope, and they learn what it's like to ask questions. And this is not something that exists in every place around the world. In Tanzania, here it is in Nigeria. This is a STEM camp for girls. And there is astronomy done here. And the reason for doing this, and here's another one where they have telescopes they're putting together. The reason that it's done there is because these girls, it's not that like in some countries they are discouraged from going into science. They don't realize they can go into science. They don't know that they can be a scientist. They don't see anybody who is. In this case, this fantastic organization was started by a young woman who's the outreach coordinator for the Nigerian Space Agency. So there are women involved there who serve as the role models. But look, this is a case of growing up not even looking at the sciences, and then realizing, well, wait a minute, I can do this. And they're inspired by this. There are sparks that go off when this when they get a chance to do these things for the first time. Well, here's a container. Doesn't look like much from the outside, but you can see it's got some windows in it. This is a container that contains a STEM lab based on astronomy in a refugee camp in northern Nigeria. This is internally displaced people. Boko Haram came to their villages. They've had to escape. The children there are living under conditions that you can imagine are not ideal. But this is a picture of them while they're doing astronomy in this place. And I love this picture because it shows that the wonder is still there. Look at the smiling faces. I mean, it's not always like that during their regular day. They have some telescopes there as well. And this is an opportunity, and it's not just a chance to escape. It is something different, but it's a chance to experience something more and to feel a part of something bigger. There are other ways of taking astronomy for education to other places. This is in Ethiopia, where they have an astro bus. Now, the thing is that most of what we do at the universities, we do in the cities, and so on. We don't reach most of the people that way. But astronomy is something that allows people to understand science better, STEM, science, technology, engineering, and mathematics. And but very few people have exposure to it. In this case, they are taking telescopes and other things out to rural areas in Ethiopia to give them a chance to experience this as well. We have planetariums in cities. Sometimes people use mobile planetariums and take those out to rural areas as well, which is a great way to do it. Which seems funny. They can see the sky, so why take a planetarium? Well, it gives you a chance to point things out. But to me, the telescopes are the best, because then you get a chance to see what those things up there really are. I mean, when you point the telescope at Jupiter or Saturn and they step back and they look up and say, is that it? From then on, that the sky doesn't look the same to them anymore. So I think that's the best. This is also from the Astrobus. They can go into classrooms and do things that they wouldn't otherwise have a chance to do. So this is a picture taken in Uganda, again with the eclipse glasses. You know, how many people have actually looked at the sun? You know, it's something you avoid looking at during the daytime. But how have you ever actually just looked at it, look for sunspots, see what it actually looks like? I don't suggest doing it without proper filters, such as these eclipse glasses here. These were sent for a total for solar eclipse that was going to happen, but they were used anytime. And just simply looking at the sun is something that people can consider doing science. It's pretty simple, but this group here was a classroom who heard that we had glasses in Tanzania for an eclipse coming up, and they got a bus and all came to where the person was who had the glasses. And the reason was, they said, we want to be scientists too. So to them, they were doing science. Now, what's the purpose? What have they learned? They've learned they can be scientists. They've taken a first step. It's a lot more than nothing. That first step is always the biggest. You know, solar eclipses, I mentioned, that's something that's what really started my international participation in connecting people around the world through astronomy. And because, you know, you have to go to where the moon's shadow is going to touch the Earth, and it takes you to a lot of places. Now, here's an eclipse in Africa. I think if you look at the shorts on somebody there and the short t-shirt, you can tell which one is the local. He's sharing the views of the partial eclipse with the people there, but we always take extra glasses so we can give them to the people and they can enjoy the eclipse as well. I can't imagine not doing this. We're coming from, it's like being aliens from space. We drop in by the thousands, and so you share these inexpensive eclipse glasses with other people so they have an opportunity to experience it, and they can keep those. And, you know, who knows what will happen? I mean, I've gotten hundreds of thousands of these out, and there are millions of them around the world. Well, here's one a lot of you will recognize. This is actually in Cappadocia. I co-led an eclipse trip there. And this is actually mother and daughter. The mother is wearing the traditional clothing and the daughter more modern clothing. Same eclipse. It traveled across Africa. These are students in Egypt. And they were viewing the eclipse along the path there as well. This is one I took in China near the Great Wall. Yeah, the dog wasn't thrilled with this. He wasn't interested, but the people were. Well, then of course there are other situations. This is a friend of mine who was in Antarctica in 2003. First time anybody had ever observed a total solar eclipse from the continent of Antarctica, but he got a lot of interest from the locals there as well. So astronomy also is opportunity. And I mentioned that it's connected to every STEM field because there really isn't anything it isn't. In astronomy, the professional astronomers often go into slightly different fields, but a lot of the people doing astronomical research do not start in astronomy. They're engineers, they're physicists, they're different things, and they find that their interest is really in something that has to do with astronomy. And because astronomy isn't really connected, it isn't really there. It's really part of everything that we do. So I mentioned astrobiology, of course, and chemistry, and all the things that go into that, the geology, but the technology also, CCDs and telescopes, telescope design, optics, software, hugely important, mathematics. Well, you can't do anything without math. And so engineering, of course. So it really is connected to everything. And so there's a lot of cross-pollination, people going back and forth. And as I said, it's a way to introduce STEM. It's more accessible. Everybody likes it. People want to know more about it, and they know very little, but they're curious. I can tell you put out a telescope and you will find out. When people know that you're an astronomer, they want to ask questions. They don't know much. This is interesting, is that when I've been doing outreach like at an observatory, and I recognize this all the time, there's a mother and father and then a young boy, and they're approaching me, and the mother and father look like unsure. But the kid comes up and starts asking questions, some of which are, he's got details about exoplanets that I never heard of and things like that. And the parents are standing back because they don't want to look like they don't know anything, despite the fact that they don't about astronomy. There's no reason why they would. But eventually they start coming in and asking questions everybody's interested in. So how can we use astronomy for good in this case? Well, I like this way of showing that the difference between equality and equity. So on the left there, we're showing equality. You give everybody the same thing. It's not quite the same as equity, where you give everybody the same opportunity. So you can give everybody a grant to go to college. It's enough for some people, it's not enough for others. You need to raise up the people who have greater difficulties and give them the opportunity. So I meet people around the world through astronomy who are really brilliant, but they don't have the opportunities that we do in the United States, in Turkey, in many of the other places. And so that is really what Astronomy for Equity is about. And let me show some examples. This is in Puerto Rico, a school in Puerto Rico after the hurricanes that hit several years ago. And they had problems in, most of them were standing, but still big problems. So they had to return to school and try to do the best they could with that. So I heard from a mother in Puerto Rico who wanted to buy a telescope that we had available and know if it could ship to Puerto Rico because it's US only. Well, Puerto Rico is part of the US. Not all American companies treat it that way, but it is an American territory. And we could, and I thought, well, why just this one? She wanted something for Christmas for the child. So I arranged for, with scientists there, many of whom are in the US, but still stay there and involved, and an astronomical society and a school, nonprofit that runs schools around the island. And we raised money for 20 telescopes and we took them there. So that was an opportunity for them to have something different. What the mother had asked for, what she was looking for, was this opportunity for her child. And we gave that opportunity to a lot of other students. So I like doing things in schools because you've got a lot more people there to help. And these were among the poorest schools on the island and on other islands as well. But the thing is that they had great kids, they had great teachers. I loved the schools that I visited. They were running under generator power because it was a year later and they still didn't have their power back, and they may not still. They had everything going against them, but the people were fantastic. The children were happy and they made good use of these. So this is back to Tanzania. Now, he was part of a program called Telescopes to Tanzania. It's now an educational observatory in northern Tanzania, where teachers can bring their students for educational opportunities they wouldn't otherwise have. So that's probably a typical classroom. It's good that they have a floor. The only thing you've got on the walls there is a poster, and I'm pretty sure that was brought by the American who started this stuff. And this is a small telescope that they had the opportunity to look through here just during the daytime. And also teaching the older students something about astronomy on the laptop. Now, this is the best of all because these are teachers. We raised $50 for each teacher. It's what it costs them to take a bus across the country to this place where they would be taught by others to teach astronomy. Something they could do in their schools, something they wanted to do. It's a great program. There are a lot of things like this to teach the teachers to teach astronomy, and then they can teach others. these are, I have to say too, some teachers, they couldn't get the $50 for the transportation because they hadn't been paid in several months, because there just wasn't money for them. But somehow they managed and they kept working. This is now the observatory, the location there. I hope to be taking a small group of people to this observatory later this year. It's on the edge of a wildlife refuge, so they have to worry about elephants walking through at nighttime. I haven't heard about lions yet, but they're probably there. So this is how things grow, and I've got these in here twice, so I'll skip those. This is an astronomy club in Libya. This is a middle school in Libya. These are, as you can see, this is not supposed to be just girls, but it is. There might be separate schools, but I think they're maybe co-ed. And they have an astronomy organization that's fantastic nationwide. They form these astronomy clubs. They have the Ministry of Education supporting them. They have all the passion, and the teachers and everybody else, they couldn't get telescopes. There just was no way to get them. So we ran a successful, and there's somebody from the Ministry of Education there interviewing this young girl who wants to be an astronaut, as young people do, raise money for those telescopes. We also connected them with astronaut Nicole Stott, a wonderful woman who's flown several times on the International Space Station. This was a big deal. This was the first time they had talked to an astronaut since Yuri Gagarin visited. That would be in the 1960s. So it was a big thing. This is after the event with ministry people. And the effect of these things here is good for everything, including astrobiology or other education, because these little things, they inspire the students, they inspire the teachers. But the other thing is that the governments notice. So, and you might find this in Turkey, that if you do something that really has an impact, some political figures will say, oh, this is really good, I want to support this, whether because they think it's a good thing to do or they think it will advance their career. They're politicians, I don't know. But if you can get it done, I don't care. That's fine. Well, this looks like any other picture of somebody craning their neck to look at something through binoculars, except that this person is actually blind. So we would say blind, visually impaired, low vision, legally blind, but they can see something still. So astronomy can be done. And remember now that for many of the people, we're really lucky here. We have access to the internet. We can take part in something like this. We can talk to people around the world. We have books, teachers, all kinds of things. But for a lot of people, they're just excluded. Astronomy can include them. And there is interest. Blind people know about astronomy. They don't know the concepts. I've recently learned that when they feel a dome above them, where they can feel the stars, they realize, wait a minute, the sky is curved. They didn't realize it isn't flat. So, it doesn't take too much to include them. Here's one way to do that. This is a 3D model of the moon that they're able to feel and find out what the moon is like for the first time. This is a planetarium program. So this is something that you can hold in your lap, and there's a narration. It could be done in a planetarium where the sighted people can see the stars or not, and they're able to take part in that for the first time. So if this is inspiration for you, astronomy is, or astrobiology, it should be accessible to everybody, not just those of us who are fortunate enough to be able to take part. Well, finally, astronomy is inspiration. This is probably the main reason that all of us get into doing astronomy in the first place. We feel connected when we do this, especially in the things that I do where I deal with people around the world. We are all part of something that is greater. And in astrobiology, really, this is this isn't just about curiosity. I wonder what's happening on that planet. You're wanting to answer the question, are we alone? That's not a trivial thing, but that isn't about what's out there. That's about us. We want to know where we fit in. Are we really unique? Or is there other life out there and we're just a part of that? This is no different than if you're in your village, someplace isolated from everywhere else, and you know that there is more earth out there on the other side of the hill, and you just want to go over there and see what's there. And imagine if you didn't know if there were other people or if you're the only ones on the planet, and you go over there and you find there are lots of other people and you learn about what you are a part of. So this is why we are interested in the first place. We are all traveling together, in fact, on Spaceship Earth, as Buckminster Fuller called it. And as I mentioned, we're looking out different windows into the sky, but we're looking out at the same thing everywhere we are. This is an important aspect, and there is a group called Astronomers for Planet Earth who are working on climate change through the lens of astronomy, getting astronomers involved to explain what is going on. Something where astrobiology, of course, has a role because, if astrobiology largely is studied here on Earth. We study the life that we know and the conditions here that we know life can exist. We can't extrapolate to other places, but we do our best to try to create those situations that would be different. So we are traveling together. We are in space. This person in the background here is seeing that right now. And when you go out at night and you look up, you can see you're traveling through space. And if you watch the stars, you can see how they move, and that shows how we move. So right now, for example, what I'm going to be doing very soon is raising money for telescopes for schools in Ukraine. Now, you know the situation in Ukraine. The astronomy students there, they have teachers who are teaching astronomy. They have a lot of astronomy. They have amateur astronomers there who will help. They are studying astronomy because it makes them feel part of something larger. They feel very much alone and forgotten in places where they've either lost their homes or they have to run for bomb shelters 3 or 4 times a day during their classes. Interrupts their studies, but they can't get telescopes. So I'm getting them some telescopes. It's such a small thing. And the reason this request for telescopes came from the students. And the reason was this: they have blackouts all the time. The teachers are very discouraged because they can't go on with their classes. The students said, but look at the sky. It's dark. We can see the stars now. We need telescopes. So that's why we're doing it. So what's really important too about the bigger view is in caring about each other. This is a famous blue marble image taken by Apollo 17 on the way to the moon in the 1960s. But without that overview, you don't recognize that the people that you don't see are really part of what's going on. People say we're all in this together all the time. I don't know about in Turkey, but in the United States, as soon as the pandemic hit, we're all in this together. Everybody says it. Nobody acts like it. They don't, because they don't really experience that. A great way to understand that, based on astronauts I've talked to, is called the overview effect. And this is a cupola on the International Space Station with an astronaut looking out there. The overview effect is the change that happens when you get outside of outside of Earth, your own local area, and look back at the planet. Not just looking at the planet itself, but seeing it surrounded by stars. And this changes things, like being in that little village, not knowing if there is anything else around. But climbing up on that hill and seeing there are lots of other things. Our village is not everything there is. So in Buckminster Fuller wrote, "We're all astronauts on a little spaceship called Earth." And he even published an operating manual for Spaceship Earth. That was quite a long time ago. Now we have Marshall McLuhan added later, there are no passengers on Spaceship Earth. We are all crew. We all need to take part. So this is Earthrise from the Moon on Apollo 8, which started a global movement of awareness that led to Earth Day. And this was the first time humans had traveled this far out. Bill Anders, who took the photo, said, "We came all this way to explore the moon. And the most important thing is that we discovered the Earth because we saw it in a new way." And of course, this is the Artemis mission that went out well past the moon and took a picture of both the moon and Earth. Now, the overview effect is that paradigm shift I mentioned, experienced by many people who get out into space. If you saw William Shatner's response to several minutes above the Earth's atmosphere, very close to Earth still, but far enough up to see it as a whole, you'll understand, because he expressed it as something that completely unexpected. So we understand these things intellectually, but it's not really part of our existence. We don't really get it. The Overview Effect by Frank White is the book that described this for the first time. It's sort of like the Copernican perspective of the solar system. It's something we know is true, and we can prove it and we can understand it, but we only see how the solar system works in simulations. We're not out there outside of the solar system watching. But in this case, you can see the Earth as a whole. Or we can see the Earth and Moon. As we get farther out, this is taken by Voyager, the first image of its kind in 1977, on its way to the outer reaches of the solar system and beyond. And also the Earth and Moon taken by the Near spacecraft in 98. And Chang'e 5 taking a picture of our system as well, more recently. And here we have, well, I don't know if it'll show up on there, but there's a little dot on the right side of that bigger one, and that's the moon. The big one's the Earth. So this is getting farther out. This was taken by OSIRIS-REx by the NavCam. And then, of course, there's this one taken from the surface of Mars by the Spirit rover, and the arrow is pointing to where the Earth is. And you are here. Everybody is here. Everybody who ever lived is here. Just like in the pale blue dot, as Carl Sagan described it. This taken in 1990 by Voyager 1, 6 billion kilometers from Earth. And he said the Earth is a very small stage in a vast cosmic arena. So this is a perspective that you get. What we see at the top on Earth and what it looks like if you get out far enough away. It just really doesn't make any sense anymore from that perspective. And that's the shift that happens with astronauts who get out there. And Sagan said it underscores the responsibility to deal more kindly with one another. Fewer than 1,000 people have been to space so far, fewer still to the moon. Private space flights are going to help, and virtual reality, but not many people can access those things. For the rest of us, though, there is one way to experience the overview effect. That's astronomy. So when we look out there, when you look out and wonder, is there life there? You know that you're not the only one on Earth thinking that. You're not thinking about from a Turkish perspective or a Romanian perspective or a Nigerian perspective or an American perspective. You're thinking from an Earth perspective. Are we, not me, are we as a species the only ones? And when we look out into the sky and we study the sky, just watch it, if nothing else, like the Greeks did thousands of years ago, and others have done for thousands of years, we see that overview effect. We see that we are on spaceship Earth, and we are all there together, and we are just one species, not a bunch of us versus them. And this is the kind of thing that we get. This is our galaxy. I mean, a lot of people look out at the Milky Way and they say, well, it's beautiful, and they may understand what it is. This is a spiral galaxy. We're looking at it up close. We're inside of it. We're out towards the edge, 2/3 of the way out. But look at that. What a view. So I spend a lot of time looking through big telescopes at galaxies like this, tens of millions of light years away. But look at this. This is right there. You just need to go to a dark place. In this case, it's the top of Mauna Kea in Hawaii. So this is how we can get an overview effect. I just don't see how people can look at something like that and say, this is the galaxy we're in, but I'm more important than the person over there on this little dot. It doesn't work that way. So the overview effect for the rest of us, I think, that's astronomy. And this is why I think it is so important. And I wish we could get everybody into space, which we can't. John Dobson used to say with a million telescopes, we can give everybody a view through a telescope. I don't know if that's enough, but you know, those of us who do this kind of work, we're doing the best we can to make that happen. And so I just ended the slideshow, but not the share. Okay, there we go.
Thank you very much for this presentation. It was a very informative. If you're ready, we can take the questions.
I'd be glad to.
Okay. First question is, how has astronomy played a role in shaping our cultural and philosophical beliefs throughout history?
Oh, well, I can't answer that completely because it's too big an answer. Imagine we were never able to see the sky and we never knew the stars were up there. We would not have any navigation by the stars. We would not know about, we use star. The word star, you'll find that in all kinds of things. It represents something. It represents, you know, we reach for the stars. Somebody who's doing very well is a star. If you think about it, look at our language and you'll see all the different ways that it is represented. And because I've been to some ancient places too, including Turkey, there are an awful lot of things in history that show the stars as part of the environment. They weren't separated like we are because the night sky was not lit up like it is now. So it's really absolutely essential. If you look around, you'll see it. We don't even realize it. We have cars called Saturn, and there are just so many things. But I think the main thing is you'll find the word star in a whole bunch of things. I even went to, I met a film director who did something about people doing things at night, including astronomy. And it was a film festival and it wasn't far, so I drove over there. And I was talking to him about this. And I said, look, you even have stars in the introduction in the background of your film. And he said, I do. I mean, he didn't even realize it. So it's too big a question to answer. It's everywhere. And it's an extremely important thing. We would not be the people we are in any of our cultures without astronomy.
Okay, thank you. The next question is, what are some of the current challenges in astronomy, and why is it important to continue to fund and support research in this field?
Well, you know, my area is not in research, but I've done research in other areas. But it is critical for a number of reasons. Now, of course, we hear in the news mostly about gravitational wave astronomy and things like that. One of the things that I think that people don't realize is that these big projects and these billion-dollar telescopes are not all there is. There are telescopes all over the world, and they are just as important. Some people will say, well, you know, you don't need to build a telescope on Earth because you can put it in space. Well, I can't put a telescope in space. I don't know anybody who can. So we need all those down here too, because the same work continues all the time. That to me is one of the challenges, is just keeping astronomy going and keeping it funded. And it's one of the reasons why I like to talk about the importance of it and why it's important for different things. There are many, many challenges. I think you're going to have others who are in this conference who are going to be able to address specifics better than I can there. But, you know, the big challenges like what is dark matter, what is dark energy, cosmology seems to present the biggest ones. But the biggest question of all that we've always had, of course, is, are we alone? That's why we're all here, right?
Thank you. What can we learn about the universe from studying astronomical phenomena like black holes, pulsars, and supernova?
You know, the best answer to that question is we don't know what we're going to learn. This is why you explore. This is why you go up to the top of that hill and take a look out there. It's because you don't know for sure. Now, it is true that studying black holes and pulsars, supernova, things that don't happen here on Earth and we can't study here. We learn a great deal about physics, and all of those things come back to help us. You know, if we can verify things in general relativity or in quantum mechanics that are applied here, and people don't realize that you know, if it wasn't for relativity theory, we wouldn't be able to talk on our cell phones with mobile phones with satellites and so on. All the things are necessary. The advancements that we get, though, sometimes are entirely from the fact that we are looking at something we've never seen before or never seen up close. I do some work with the sun, and I know the history of it. I use a telescope that's over 100 years old. They didn't know what the source of the energy of the sun was then. They had no idea. They couldn't figure it out. They didn't know about atomic fusion. That came about in the 30s, I think, when somebody suggested it. Helium was discovered on the sun during an eclipse in the corona before it was discovered here. So, you know, I'm not the best one to list off the different things about what the main challenges are or what we'll learn from these things, except that these are natural laboratories that we don't have on Earth, and we will learn things. Some we'll be able to answer some of the questions we can, like testing theories that we have on Earth that we can't do, and we'll discover other things.
Okay, thank you. What advances in astronomy are possible thanks to artificial intelligence?
Well, artificial intelligence is very big in the news right now. My understanding from people I know that work in this area is that artificial intelligence doesn't understand anything. It's not intelligence in the way we talk about it. What we're seeing mainly is large language models that are trained on large data sets. What they're really good at doing is looking at parts of enormous data sets and putting them together in what seems the most likely way. That's how they come up with responses to questions. They look and say, what's the most likely next word to be put into this sentence? And they string them together and they make sense. And then sometimes they're right, and sometimes they're completely wrong, and sometimes they make things up, which in artificial intelligence circles is called hallucinations. But there's no question that AI is a tremendous tool as we gather bigger and bigger data sets. It's more and more of a challenge to find things within it. So really data analysis, I think, is the great thing here. We're not going to have AI that's going to tell us what to do with the telescopes, but it's going to tell us what we can find in the data that we've collected we might not otherwise find.
Thank you. What do you think about amateur telescope making? Is it safe that using handmade mirrored telescopes?
Yes, not only safe, it's a great idea. I mean, when I was younger, that's how people got telescopes. They couldn't buy them. They made them. It's a fantastic thing to do. There are many, many ways. You need to look in the older books about how to do this because, well, there are new ones now about Dobsonian telescopes and so on, but people have been doing this forever. The hard part is making the optics because it has to be done just right. And you need to make a mechanism for testing it. It was a very common hobby. My society, Los Angeles Astronomical Society, that I was a part of, started as amateur telescope makers of Los Angeles. So it's always better to make one. Then you understand it. You know exactly what you're doing. But it's very easy to get the ones coming out of China now cheaply. But yes, if you're thinking about it, give it a try. Yeah.
Thank you. The next question. What is the importance of studying astronomy in understanding the origins of the universe?
Well, you can't understand the origins of the universe without studying astronomy. I'm not a cosmologist, so I can't respond directly to that, but I can't think of another way of doing that. Now, with James West, which is an infrared telescope, so it can look farther back in time at the radiation that's being released by younger objects in the earlier universe. With gravitational wave telescopes and with other things, we can get farther and farther back to the beginning. But for the questions like how did it start and what was there before the Big Bang? Yeah, I think I'm going to leave that one for cosmologists because those ones I can't even imagine.
Thank you. The next question. In what ways has astronomy impacted the field of astrophysics and the study of fundamental physics?
Oh, well, that's huge because, as I said, take 100 years ago when people didn't know what the stellar spectra really meant. And they created laboratories where they could put gases under different pressures, different temperatures, different ionization states, and they shine light through it and see what happened. And so these are things that wouldn't have come up in the first place. Studying the sun first is what led us to understand a whole lot of things about it, about how things work. There aren't that many places where it's easy to study quantum mechanics outside of solar atmospheres. And so it is the laboratory that without which we would kind of be stuck with a lot of theory, but much, much less understanding. And there are things that we can see happening that otherwise just we wouldn't know about, or we could only guess at. So there are discoveries, but also I think to me, the main thing is it's the laboratory where we can test our theories and find out what's right and what's not right.
Thank you. How has this study of astronomy contributed to our understanding of the evolution of life on Earth?
Yeah, that's a really interesting question too. And you have other people, astrobiologists. I know some of them like Sanjoy Som and Jacob yesterday who spoke to you are astrobiologists. But I know that, first of all, the Earth is here because of the light from the sun. The sun has evolved. The radiation that we're getting from the sun has changed over time. There wouldn't be anything here if it wasn't for what we consider astronomy, which is our environment with the Earth. The moon creating tides also has played a huge part in the evolution of life here. Now, as far as understanding, I guess I can't answer, what did we learn from looking at the stars that it tells us something about here? The one thing I can say, though, is that if we'd only ever had a chance to look at the sun, we'd never know what its life cycle was like. When I was young, the sun was thought to be a really small star. That turned out to be a sampling bias, an artifact of the observations we were making then. But now we understand the main sequence and how stars evolve. and that so we can look back and say this is what the sun was like before. I guess that's the main thing I can think of for that.
Thanks. The next question is, does optical telescopes' importance is decreased after invention of radio telescopes? Do we need to invent more strong optical telescopes, or we go for with JWST type of new telescopes?
Yeah, so these are not different things. I mean, the same thing. James West is not a substitute for Hubble. They're looking at different wavelengths. Radio telescopes look at something entirely different. And so we just see different things. Now, imagine, for example, if you took a red filter, you put a red filter over your eyes and all you could see was red. Then you look through a blue filter and all you can see is blue. You're not going to see the same things. It's going to depend on the color. So the wavelengths are giving us different things. The importance of things like radio telescopes is very low energy by comparison, longer wavelengths that are coming from things we wouldn't otherwise see. For example, the H2 clouds in the galaxy, we see 21 centimeters wavelength. As opposed to a few thousand nanometers like our eyes do. The infrared radiation shows us what we consider here, because this is what's predominant here, to what we think of as temperature. But there are things we see in the ultraviolet. There are some animals that can see into ultraviolet or farther into the infrared, and they see things differently than we do. They can see better at night if you can see infrared. So there isn't one that's more important. They are all important. And that's why we go into space too. We have X-ray telescopes now and other telescopes that get beyond the protection of our Earth's atmosphere. Now, Hubble and J. West, it's good to get beyond the atmosphere anyway for many reasons, even optical. But there are other things that don't get to us, and it's a good thing they don't, because if we had X-rays and ultraviolet radiation coming in all the time, we wouldn't be here. So we need them all. We really do.
Thank you. There is one more question, but if you're in a hurry, we can finish the questions.
One more is good. It'll be fine.
Okay. The last question is, what challenges await those who want to work in the field of astrobiology?
Well, I'm not an astrobiologist, so of all the people in this conference, I might be the least able to answer that question. But I can tell you that in astronomy in general, the biggest challenge is really moving on after the university. And I think that's going to be the case for astrobiology as well, that people get their PhDs in astronomy and then they might get a postdoc here, a postdoc there. The situation has changed quite a bit. Where do you get a job? You can't just find a tenured position at a university. There are companies that will do these kinds of things, but the real challenge is post-educational. And that is a really big challenge, and it's really hard. And some people may say, well, if it's going to be that hard to find a job and make a living, don't do it. I feel exactly the opposite way. I've always sort of made my own jobs, and you can too. So I say to follow what it is you want to do, but look into what the prospects are afterwards as well, and be prepared for that. That's really the tough part.
Well, thank you very much for coming and taking the time for us. Your presentation and your answer was very informative. Also, my team and I would like to thank you for helping us through this process. Sorry for that.
Yes. Well, it was a pleasure to be here. I love talking to passionate people like this. So it was very good.
Thank you. So take care.
Thank you. Mm-hmm. Bye.
Bye. Now we will continue with Angelica Angles at 19:30. See you.
Hello everyone, I am Berra from the Agenastro team. I am currently studying molecular biology at Üsküdar University. I plan to be an astrobiologist in the future. I will hosting the last session of the day. Dr. Angelica Angles will join us. But first I want to talk about her briefly. Dr. Angles is a pioneering astrobiologist known for her work. She completed the PhD in astrobiology planet exploration from the University of Hong Kong. Geological features of the Kainan Basin in Tibet. Through her research in Tibet, she became part of NASA's landing stage selection team for the Mars 2020 the planetary mission. Last year, she was one of 5 analog astronauts for the first analog space exploration mission in the UK. She is also the principal and investigator of the Mars Analog Expedition, where she collaborates with the Icelandic Space Agency, NASA, and Massachusetts Space Research Institute. Now, she talked today Mars on Earth using experiment placed on Earth to find life on Mars. Hi, Angelica.
Hi, hello.
Hello.
So should I start my presentation then?
Yes.
Okay.
We are happy to welcome here. Your teammate who connect to you confused your time zone, so we had to pick you up an hour late or for broadcast. We apologize for that. Thank you for spending your precious time with us. How are you today?
It's great. It's not a problem. It's Saturday morning for me. I am in Canada at the moment, so it was fine to wait 1 more hour. No problems. Yeah.
Okay, I am very pleased. Thank you.
Yeah.
I tried to introduce you as much as I could. Is there anything you want to add?
No, I think that was great. I think after my presentation, people will have a more clear idea of the type of work I've been doing. And I left a little bit of time at the end for some questions. So I'm happy to answer anything at the end.
Okay. 1 second. If you're ready, you share your screen.
Okay, I'll share my screen.
Click the present button below and share the screen and entire screen.
That's what I'm trying to do. Okay, I think it's this. It says I don't have
the presentation now.
Can you see it?
No.
Maybe it's because of your Chrome settings. I'm sorry, I'm just coming here and interrupting you. I'm Zeynep, by the way. Maybe it's because of your Chrome settings. You can check your permissions because sometimes it's not allowing to share screen.
Okay, let's see. Conferences, 1 second.
Also, if you want, if it is a PDF or PowerPoint, you can click slides part with that present button. You can click slides and then you can upload it from your computer.
Yeah, that's what I'm doing, but it says please choose a smaller file.
Oh, maybe because of the size. Okay, then you can just say share screen and then entire screen and you can show us.
Share screen.
Yeah, share screen and then entire screen. And if you have any audio in your presentation, you can also allow the share system audio. You can click that button and then you can share.
I'm doing that. Entire screen.
Yeah, entire screen.
And then share.
Yeah.
It says Chrome has lost permission to capture.
Yeah, that one. Chrome needs permission. You need to allow that permission, actually.
Okay. So I will allow the permission screen. Okay.
Yeah, from your top part of your screen, you can see what what permission you are giving to Chrome. For example, here I can see. Okay, she will
leave.
Yeah, but she will come. It's happened once again today, and also yesterday. For that permission, they need to reload the page, actually. That's the issue. That's why she is gone. Yeah, she can. Okay, you can try now.
I am back. I think it needed to restart something. So I'll do it again. Share screen.
Okay.
Entire screen. And then share.
Yeah, we can
yes,
see.
I can see it.
Yeah, okay.
So you can see?
Yeah.
Yes.
Great.
Okay.
Okay.
Stage is yours.
Thank you very much. It took a little bit of time.
Thank
you. Okay. Thank you, Vera, so much for your introduction. I am very excited to present the work I've been doing about Mars analogs, and I hope you will find my talk interesting. So I'll start with this. So planetary missions to Mars greatly depend on rovers. However, the landing site for rovers is selected using only remote sensing data, which unfortunately lacks essential information for us to fully understand the habitability conditions. Additionally, in a sample return mission, the rover must choose very carefully the samples due to the very limited catching capability and the limited instruments on board. And this is especially relevant when life detection is the main goal. We really need to understand not only which samples to take, but also the geological, the environmental, and the microclimate parameters. So to better understand Mars and to know if it ever harbored life, we cannot rely only on rovers and satellite imagery. So for the past years, I have been studying Mars analog environments in order to analyze the survival strategies of the organisms we find in these locations, and then compare these locations to Mars and to find out where we could potentially find habitable environments on Mars. There are many Mars analog environments on Earth, depending on what exactly you want to study or you want to look for. But these are the Mars analog environments that I have been studying in the past years. Many of these analogs look visually like Mars, but some of them have other similarities to Mars, such as similar geological history, climatic conditions, or even isolation and remoteness. For people like me that study analogs, we tend to say that our analog is the best, but the truth is that each Mars analog provides different aspects of Mars, and it is the combination of all Mars analogs on Earth that makes us better understand Mars. So I am going to show you two of the Mars analog environments I have been studying the most: the Chaidan Basin in North Tibet. This is the analog I've been studying the most. This is where I did my PhD, and Iceland. And then I will talk about my analog astronaut training and mission in a very different analog site in Scotland. So I'll start with the first one. Okay, so for the past 8 years, I've been studying one of the best analogs, in my opinion, the Chaidan Basin in the mountains of North Tibet, which is a relatively unexplored area in the world. It is also a very remote place. It takes 2 days driving to get to our study site from the closest city, Xining. So the Chaidan Basin is the highest desert on Earth. It's about 4,000 meters high. And in this drone footage, you see that the area is very big. It's about 800 kilometers across. So we choose a small area to study, but still choosing a small area, we had to drive about 10 hours per day. So it's very tiring. It is also one of the driest and more hyper-arid areas on Earth, making it one of the most similar environments to Mars. It is a very remote area, so once you are there, you can see there is absolutely nothing. There is no vegetation, no visible life forms, not even insects live there. So the site is also a military-controlled area, so foreigners are not allowed, so not an easy place to go. But every time I managed to get there, we would try to do the science, and in every trip, we would collect about 50 kilos of rock samples for further analysis in the laboratory. And you can really see that it totally looks like we were on Mars, especially that bottom right picture, which is one of my favorites. So back in the home laboratory, these are the methods we mostly use to analyze our samples, especially the first two, the scanning electron microscope and the X-ray diffraction. So Chaidam in Tibetan means salt flat, a description in agreement with a huge amount of salt deposits in the basin. The entire basin floor is covered by hundreds of meter-thick evaporative salty crust, where sulfate deposits dominate, with gypsum together with halite as the main minerals. So on the basis of the investigations on our samples, I'm going to show you a wide variety of geomorphological features and their counterparts on Mars, especially during the period when the water on Mars disappeared. So on the left side, you're going to see the Chaidam Basin, and on the right side, you're going to see Mars. So catastrophic debris flows appear in the Chaidam Basin, where the direction of a massive flow is severely interrupted by another flow advancing downslope. So this event might indicate the possible thawing of ice from the upper parts of the mountains in a short time, due probably to a sudden warming. These flows are about 15 kilometers long and about 2 kilometers wide, so they're very, very big. And mass flows events of such magnitude are kind of rare on Earth. This process would have different effect on Mars due to the lower atmospheric pressure and the amount of water required to form such flows. However, Mars, as you can see, exhibits multiple indications of catastrophic mass flows. A discharge of saline groundwater or warmer climatic conditions or melting of water snowpacks are some of the hypotheses to explain the formation of these flows. Polygons. So polygonal desiccation terrains are common in the valleys of the Chaidam Basin. We interpret them to be related to periods of intense evaporation and sustained by very limited quantities of brine. So random flooding and minimal melting indicate that there are means to create these polygons in extreme conditions, and gives critical clues to understand the Martian polygons. So on Mars, we think that similar processes could cause this network of polygons by annual sequences of hydration and dehydration of clays and salts. We also found that mountain crests record a variety of unique geomorphic structures characterized by relic pit-like forms and hollows, ranging in size from just a few meters to a few kilometers across. We believe that they are formed by the accumulation of ice that led to the formation of these irregular depressions. So for this to happen, the only probable source of water had to be originated in the upper mountain areas. So we suggest that these morphologies correspond to the late stage water or ice activity. So consistent with this interpretation are the series of hollows observed in the upper mountain crests, about 5,000 meters high, in the center of Gale crater on Mars. These morphologies provide information of the last time when ice was present and was enough to modify the lithology, although we believe that wind activity may also play a role. So some of the playas display these alternate layers of salts and clays that can reach several hundred meters wide in steeper areas. We think that the formation was influenced by multiple factors. For example, brine concentration and evaporation over long periods of time, aeolian effects, local steepness, and deposition under different climatic conditions over long time scales. So one example of Mars is the layers of evaporites and clays in the deposits of Becquerel crater that you see there, where the low albedo layers have been associated with high levels of hydrated minerals, such as sulfates and halides. So the presence of layers is consistent with successions related to climate change and brine cycling produced by the effect of water. We also found these unique structures that are characterized by the dark streaks, their preference in equatorial slopes, and their appearance mainly during spring and summer. These are called recurring slope lineae, or RSL, and they are active features on Mars today, but their origin still remains an open question. The McMurdo dry valleys in Antarctica has been previously proposed to be the closest analog for RSL on Earth. However, here we have evidence of seasonal brines in the Chiltern Basin as well. Gullies appear in the mountains areas in the Chiltern Basin. The ridges, however, the top part of the mountains, are not able to sustain high amounts of groundwater due to the limited area and the strong evaporation that characterizes the Chiltern Basin. So our suggestion is that an ice cap was stable for some time and episodically melted, providing the very limited amount of water that is flowing at a very strong evaporite condition, so very salty water. And new gullies are rarely seen flowing the line of former gullies. On Mars, the main difference between the gullies and RSL is that the gullies have been found to take place mainly during winter, and they don't have an albedo contrast. So despite the main period of outflow channel formation ended on Mars long time ago, and the current low temperatures, gullies can be detected in many locations. So we think that in the presence of salts, small amounts of liquid water might be stable under the current Martian conditions, the same that is happening in the Chiltern Basin. We also found galligons, which is polygons at the end of the gullies, strongly indicating that some temporal relationships within the polygons and the gullies might exist. Similar galligons appear on Mars over a wide range of zonal climatic conditions, and so we believe that they provide key information to interpret the permafrost development on Martian soils. Alluvial fans in the Chiltern Basin are unique because they are very long and they can be up to tens of kilometers long. Because these valleys are so long, we believe that they were formed by a cataclysmic release of water or meltwater that formed the valleys. They also, in the top pictures, the V-shaped valleys represent a rapid downcutting by runoff along a steep gradient. So these long valleys represent the end of an extended history of aqueous activity and deposition. I really like the last two bottom pictures. Even that little rock seems to be on the same place. We also found yardangs, which are these small hills formed by strong winds and surface runoff in one direction. Also, the high altitude and atmospheric pressure in the Chiltern Basin, which is about 1/3 lower than normal pressure, makes the wind even more remarkable. So yardangs are abundant on Mars, and we could see them in many locations in the Chiltern Basin. These yardangs in the Chiltern Basin are the closest analogs you can get to the yardangs on Mars, as far as we believe. And they are formed in very similar conditions of strong winds and very limited precipitation. I also really like the two bottom pictures. I took it from the car in the Chiltern Basin, and on Mars it was taken by the Curiosity rover. So we also found these wind streaks, which are due to preferential removal of fine and small particles. So they are very common on Mars, and they come in a variety of sizes, shapes, and topographic locations, but all of them are largely stable features formed by very strong winds. So on Mars, they can be up to 60 kilometers, which is kind of amazing, and they are formed by very constant, unidirectional, and near-surface strong winds. So these wind streaks are very unexplored on Earth, mainly because the presence of liquid water and vegetation on Earth. So it's really hard to assess here on Earth. There are very few studies about these wind streaks on Earth, and the poorly studied ones really raise doubts about the formation. Consequently, there is no, to date, a geomorphological definition of them, and those already in the literature rely almost entirely on orbital observations. So again, here in the Chaidan Basin, we have a natural laboratory for testing the physics of wind processes in an environment that is rare to Earth, but very unique and common to Mars. We also observed large gravel on top of small hills. This indicates strong evidence of past fluvial activity. When the underground water thaws, the smaller particles settle in the voids below, and the large gravel remain on top. So even though there are, of course, some differences in gravity and flow conditions and even the type of fluid, these gravels are an indicator of an ancient, wetter environment, and the Chaidan Basin offers us an open window to study Mars when it was wet and warm. On Earth, most dunes are composed of quartz sand, which is non-existent on Mars, but these dunes in the Chaidan Basin are composed of sand together with clayish materials, gypsum and halite. So on Mars, the dunes are interpreted to be sulfate, muds and clays in between other possibilities. So what this means is that this type of dunes are most common on Mars than on Earth. So the particular mineralogy of the dunes in the Chaidan Basin are a very good comparison to Mars. Also, in the bottom two pictures, linear dunes in the Chaidan Basin undergo lateral migration at rates of 3 meters per year, which is the largest reported value for linear dune migration on Earth. And we know that thanks to the satellite imagery on Mars, we know that many dunes and sand ripples on Mars move as much as a few meters per year, proving that the sand on Mars is migrating under current climatic conditions. We also found these swirling textures, we call, which are impressions made by mountain runoff water ice blocks grounding into initially soft mud. So these patterns suggest that at least pressure, precipitation, surface runoff, temperature, everything was in equilibrium at some point to allow water to be stabilized. So on Mars, we believe that these features are formed by the interaction of the same runoff with waterlogged sediments and ice, and both scenarios are consistent with the possible failure to transport large amount of saturated sediments. And this is the last one. So this is also one of my favorite features because tectonism on Mars is one of the most controversial issues. Evidence of young tectonic activity has been identified on Mars. However, the identification of tectonics has been focused on the Tharsis region, which is near the equator, and no evidence has been presented suggesting tectonic activity in the polar regions. So this is what we found. We found enclosed layered deposits that form a mound, such as a contour structure with an elevated hill in the center. And you can see that it has a fine symmetrical stratification with alternating layers of darker clay, which is gypsum, and the brighter salt-rich, which is mainly halite. We named these enclosed structures made of layered deposits that form a mound ring structures. So the uniqueness of these ring structures is the formation mechanism, which is caused by tectonic forces from surrounding thrust belts in all directions. So our theory proposes that, one, initially the deposits were originally mixed with salts. Two, the regional pressurization causes localization of concentrated salts. The increased salt concentration applies pressure to the overburden. Number three, the concentration and increased buoyancy of the salts within the clay cause the salt to rise until the crust is arched as the salt is brought to the surface, and then a salt-rich layer is formed. So salt-rich and clay-rich layers continue to form as long as there is tectonic pressurization. So this is what we call salt tectonism. So the compression forces result in squeeze layers in a direction perpendicular to the compression. So stronger deformation can lead to a normal fault, where the displaced walls result in the disjunction of adjacent ring structures. So these structures offer a very unique analogy to the layered deposits that are in the northern polar region of Mars. They only appear in the North Polar region, where the disappearance of water bodies left behind huge amounts of salts. So the origins of these layered deposits are widely debated. However, we propose that the enclosed nature of this structure can be considered as a result of tectonism. So we see here that the tectonic compressions break the ring structures, and shear forces can cause the initial ring structure to be perpendicular to the direction of the main compressional forces. So other than the ring structures in the Titan Basin, no other examples are known on Earth. So we believe that the similarity of both planets' ring structures is, in my opinion, a confident proof that tectonism in the Martian northern polar region has been active in recent geological times. So thanks to my research in the Titan Basin, I was invited to take part in the landing site selection workshops for the NASA Mars 2020 mission, and I used the Titan Basin as an analog site to help me choose the landing site for Perseverance rover. So Holden Crater on Mars, which is the landing site I chose, was amongst the top 10 landing sites considered by NASA. And what you see in the picture is the landing ellipse and the traverse in blue that I created for the rover, with 7 stops for the rover to take samples. And I chose these 7 stops by comparison to the samples that I was analyzing from the Titan Basin. I also want to show you a little bit of my last expedition to another Mars analog environment, Iceland. So a few months ago, I was the principal investigator on another expedition, life detection strategies in Iceland's Mars analog sites. And Icelandic lava fields are always one of the best options for studying potential habitats on Mars. This is due to the interaction between glaciers, volcanoes, a broad range of different ages, and the relative isolation of Iceland. So the purpose of this expedition was to explore how biodiversity and habitability vary in different Mars analog environments in Iceland. I still don't have all the results from this expedition, but I anticipate the results from the different strategies we use to collect samples and the different methods we're using to analyze all the samples will improve the chances of success of future life detection missions. So during 3 weeks, we perform research in a diversity of lava fields, volcanic sites, glacier, and other geological units that we consider exceptional terrestrial analogs of some Mars area, mainly because the presence of extreme conditions, low nutrient activity, desiccation, temperature extremes, and additionally the high iron content from the basalt derived from the hotspots. So Iceland is, the Icelandic geology is a very good Mars analog, and you're going to see. So here are some pictures of we took during our expedition. So Langjökull Glacier is the best known glacier in Iceland and with the easiest access, although we had to use this monster truck to travel on it, which happens to be the biggest ice truck in the world. I'm not sure you can see it in the picture, but the wheels were almost as tall as me. So around the glacier, we found most of the analog terrain. We collected some soil samples, but we mostly water samples for further analysis. And in the south of this glacier, there is another very important area called Rotarsandur. This is where NASA had previously tested their rover capabilities. In this location, there are a lot of lava fields, lava tubes, and a wide range of volcanoes and craters and tuff ridges, including the largest number of shield volcanoes found anywhere in the world. So after a lot of walking and a lot of driving, we collected a lot of samples for further analysis in the lab. This site is located in a geothermal area, as you can see, and we went there to sample sinter deposits. Initially, we thought about testing some of the equipment here, but unfortunately, the area is quite popular for tourists, which means the site is not free from anthropogenic contamination. And so we could not use it for our study, which is a pity because, as you can see, it's really a remarkable visual Mars analog. We studied many more areas, such as several lava tubes and lava fields. We investigated the geology, the cryology, the hydrology, potential underground habitats for microbial life, and we used some instrumentation in the field to create 3D models of the site. And our last day that we were in Iceland, we had a very nice surprise. The Fagradalsfjall volcano erupted. So after driving the whole night across Iceland and 4 hours hike, we arrived to the site just before going to the airport. And it was an unbelievable experience and such a nice ending to our trip. And only a few days ago, I just finished all my laboratory work at the Lunar and Planetary Laboratory of Macau, where I analyzed kilos and kilos of the rock samples from Iceland to study the geology, the mineralogy, and the biology of the Icelandic samples, which hopefully can give us more clues about possible life on Mars. And lastly, I want to talk very briefly about my experience being one of the 5 analog astronauts of the first UK space research analog mission. So the mission took place on a remote and uninhabited and secret island off the north coast of Scotland. I am not allowed to say the exact location of the island, but after we completed a pre-deployment training, we were taken by private boat to the island and then to the habitat where we had to live and survive for the next 5 days. So the goal was to simulate a space mission to explore another planet. So there are many risks to health in space. So this analog space mission was a simulation, a survival exercise for us, the analog astronauts, to take care of emergency medical scenarios without outside help, as if we were in space. So even though the geology of this analog is not, as you can see, in any way similar to Mars, there were many other aspects of this island that made it a good analog site. The situations we were put in were perfect for isolation, companionship, developing leadership skills, and to test physical endurance, something that the future astronauts that go to Mars will definitely need. So, as I said at the beginning, there is no perfect analog, but it is the combination of all the Mars analog sites that makes us better understand Mars. We still have a lot to learn about Mars, not just its geological past, but also how to get there. And thanks to the Mars analog environments, we are getting closer. So I want to thank the funding provided to do all these expeditions and research, which is the University of Science and Technology of Macau, Iceland Space Agency, NASA, the University of Hong Kong, and UCL. And those are my details in case you want to contact me. And thank you very much. Sorry, I cannot hear you.
So sorry.
Now I can.
Thank you for your presentation. It was really interesting. And thank you for sharing your knowledge and experience with us. Now we have questions for you if you want.
Yes, sure.
Then I will start with the first question. Okay. What kind of problem can the gravity of Mars Celeste in the human biological system?
Ooh. The gravity on Mars on the human biological system. So obviously there is less gravity. So the human body is not created to work in that gravity. So I'm sure there's going to be quite a lot of problems to get, not that much to get used, but to deal with it. It's not something that I'm working on directly, but basically gravity and many other aspects of Mars are not the same as here on Earth. So this is one more problem that the astronauts that go to Mars will have to take care of.
Okay. And then other question. The presence of water on Mars has been confirmed in the recent years. Do you think we can use this water when we land on the Mars in the future? If we use it, can we start a life there with that water?
Okay, so the presence of water on Mars has been confirmed, not liquid water on the surface. So the water molecule is there. So it can be as part of the minerals, like you find the water molecule there. But to separate that water, you would need a chemical plant to do all the process to separate. If you manage to have that on Mars, and you manage to separate the water molecule, yes, my opinion is that, of course, you can use that water to support humans. As far as I understand, the biggest problem is not to use it or not to use it, but it's actually to find enough quantities of water to support humans. Again, it might be in lava tubes, in caves, you might find great quantities of water. And of course, that could be used for humans on Mars.
Okay. Another question. Have you ever heard of Lake Salda? Once I read on a newspaper indicates the minerals and rock deposits at Lake Salda are the nearest match on the Earth to those around the Jezero crater, and what it is importance in terms of research.
I have not heard of that site, but I'm totally gonna check it out. The thing with analog sites is that it really depends what you want to study. So there are some analog sites that are really, really small. Like it can be a small lake or a small river that, like this one, for example, has certain minerals or something specific that you want to study. The beauty of the Chaidan Basin in Tibet is that it's very big, so that allows you to study a lot of different things, but it's not perfect. And maybe this lake that Onur is talking about is more accurate in terms of the mineralogy. So I have never heard of it, but I'll definitely check it out. What is important instead of research? So again, perhaps studying this place and many other analog sites that are similar to Jezero crater is when you get the most information, when you better understand Jezero crater. So the more information we have, the better we can study. So thank you for letting me know. I will totally check it.
And okay, it's my questions. I want to ask you a personal question myself. As an astrobiologist, what kind of the experiments can be done on samples taken from various geological parts of the world or from meteorites?
Okay, so it really depends what you want to study. Do you want to study the geology of your sample? In that case, you will study the elements, the minerals. You can study the age, right? So you can study not just the rock that you took, but also the geological history of the area. If it was me, I would not only study the geology, but I would also study the microbiology. Is there any life in the cracks of the rocks or under translucent rocks? In that case, you can extract the DNA, You can extract the proteins, the lipids, and study all the microbiology to know what type of organisms are there, how old are they, how long have been there. So the more information you have, the better. If you find something that was alive in a meteorite, that would be really great, right? But yeah, when we take samples, we try to study as much as we can: the age, the geology, the environment, the organisms that live there, how long they have been there. In Iceland, for example, it's not just about studying at what time, but it's the continuation. So we plan to go every year to see how are these organisms surviving after a catastrophic event like a volcanic eruption, right? Are they surviving? Are they dying and then starting again? Do they appear again? After how long? How long time do they need to reappear again? So it's a progress that you need to study to understand how these organisms are adapting. But yeah, basically geology, mineralogy, and biology of your samples. That's what you want to study to have the most information.
Another question. I read that you have an experience in the analog astronaut. So, what kind of the difficulties do you think we will have while doing an analog astronaut on other planets for astrobiologist candidates like us?
I think, in my experience, the most difficult thing was the extreme tiredness, and we were cold. It was raining all the time. We were wet, cold, tired. We could barely sleep. So it's a combination of things that really shows your true colors, not just of you, but of the whole team. So my experience is that we were a very nice team before we went to the island. But once we were there and we were all tired, you could start to see the true colors of people, like who was the leader, who was listening to who, right? Like when you are so tired, you start to make the wrong decisions. So I think the psychological aspect is probably, in my experience, the most difficult one for astronauts going to other planets. You can be very experienced in astrobiology or engineering or any other, or medicine, or any other aspect that you want to mention. But the psychological aspects, how to deal with extreme scenarios or with extreme cases or with extreme tiredness, that's something that still is being studied today, like how to deal with that, especially if you put people from different nationalities and different cultures and different customs. How you work as a team is the hardest thing, but it's a very exciting thing to do, and I would recommend it to anyone that wants to try. But it's hard. It's hard because they do it on purpose to make you very tired, to see how you react. So, but yeah.
It's very enjoy. Another question. Which geological shapes in the world do you think are similar to those on Mars?
Oh, this is a difficult question because, as I was showing in the Chilean Basin in Tibet, you saw the picture of Tibet and the picture of Mars. There's so many geological features that are very, very similar, but that doesn't mean it's the best place. There are many other analog sites in the world that have similar rocks to those on Mars. The Atacama Desert in Chile is one of the best analogs as well. Antarctica, for example, if you want to study the poles. Iceland is also very good Mars analog site. There is so many analog sites. It just really depends what you want to focus on. I would say that Iceland, the Chilean Basin, Atacama, the poles, probably the best in the world to study Mars. Rotorua in New Zealand, if you want to study hot springs. Yeah, that's so many. I'm sure there is something in Turkey. I cannot come up with anything right now, but I'm sure there is a Mars analog site in Turkey that is very close from you.
Okay. Another question. In your opinion, in which fields other than astronomy and biology should someone who wants to be astrobiologist have experience? And for example, if we need to explore on the other planets or in the world in the future, do we need to learn areas such as mountaineering?
Okay, so this is a very good question. Many people ask me, what do I have to study to be an astrobiologist? And the thing is that astrobiology is such a broad field. So I actually did not study biology or astronomy. I studied engineering and then planetary science. But you can study as well geology, biology, astrophysics. So basically, it's a little bit of everything. And what you will realize once you are an astrobiologist is that there's so many things that you're going to have to keep learning. So I keep learning things about geology and microbiology every day because everything is in one field connected. Do we need to learn areas such as mountaineering? If you want to do expeditions to extreme environments like I do, having some experience in being outdoors, in getting used to being outside with a backpack full of rocks, camping, setting up a tent, these kind of things, of course, help. But not every astrobiologist does this kind of work. You can very well be in your laboratory, in your office, and get samples or get other type of astrobiological study that does not require you going to the field. So it really depends on you. For me, I like it very much to go to places like Iceland, but it is physically demanding. It is hard because you are going to extreme places where there is no people. So by definition, it's hard to get there, and it's hard to collect samples, and you're going to have to carry them, and it's most probably going to be raining or snowing or windy or very dry. So but it's very rewarding later when you have the samples and you study them in the laboratory, and then you do your publication. So it's a whole study from collecting the sample until you publish the results. Of course, mountaineering will help, but it's not necessary.
Okay. Another question. This information helped to us to learn about evolutionary on Earth and maybe other planet, but it is how help us to start to live on Mars.
Okay, this is also a very good question because when we are studying Mars, we are also studying a lot of aspects of Earth. For example, by studying possible life on Mars, we're also studying how life started on Earth, the origin of life. So this is helping us as well about understanding our own planet. So if we understand our own planet, we can understand much better planet Mars. So planet Mars is a case scenario that can help us to take better care of Earth, not to end up like Mars. So it really is helping us a lot to start to live on Mars first, learning how to live on Earth. I don't know if it makes sense what I'm saying. If we study the origin of life all the way up until now, we can understand the geological processes and everything else that helps us to be able to live on a planet. So does that make sense? I hope so.
Okay. Another question. What are the future plans for research for life on Mars?
Well, I think there is quite a lot of people studying Mars analog sites. We need to keep learning about different environments, different extremophiles or organisms that live in these extreme environments. We need to keep studying them to see the strategies they use to survive. So Also, you can study the information that comes from the rovers on Mars. You can study the satellite imagery from the orbiters on Mars. There is a lot of different things that you can be studying to push the boundaries of life on Mars. In my case, I chose this one, Mars analog sites, because it's very exciting. But there are many others. I feel like we are almost getting there. There is a lot of plans and a lot of future missions. There is maybe a sample return mission that is going to come from the Mars 2020 mission. So if we could have physical samples from Mars here on Earth, that will help a lot as well, because of course now we are working with samples from Earth, which is not the same. So having samples from Mars will help a lot. So I think that's the most exciting future plan for searching for life on Mars. But yeah.
Okay, thank you. And another question: what indicators and signs are being sought to digit the presence of life on Mars?
What indicators are being sought to detect the presence of life on Mars? You mean from the rovers? So the same as we do in the laboratory to search if there is any life in our samples, you can study if there are biominerals, for example. So the biomineral is not life itself, but it's a mineral that was formed by the presence of life. So if you find a biomineral, that is an indicator that life was present at the time of their formation. Basically, if you find organic compounds, if you find liquid water, if you find biominerals. So you also have to be careful, because you can find the building blocks of life, which is a building block, but by itself is not life. So finding organic compounds is not life itself, but it's a building block. So that's what the rovers are doing. But again, if we could have those samples here on Earth and analyze them in the laboratory, we will know for sure if there was life there or not.
Okay. Another question: what are the other protective elements of water other than salts?
I'm not sure I understand the question. What are the other protective elements of water other than salts? Do you mean to have liquid water? Because you can have liquid water, like I was explaining before. If it's very salty water, the salt makes the water to be liquid, right? So it is possible. One of the theories is that you can have liquid water in the surface today if it's very salty. I'm not sure this is the question, but this is one of the hypotheses, that very salty water could be present in the surface of Mars today.
Might be asking if it contains other elements and minerals.
If it contains other elements and minerals, you mean the water on Mars, or
Mars in found in water in the elements?
So for water on Mars. Sorry, I'm confused. I'm not sure.
Okay. And ask a question. Wait a minute. Okay. Why are creating exploration sites selected for researching for life on Mars, and how are these cities chosen?
Again, do you mean exploration sites here on Earth to search for life on Mars, or you mean on Mars, like exploration sites? I'm assuming you mean on Mars. How are the sites chosen? So in my experience, when I was doing the landing site for Mars, there is a lot of requirements of of the landing site. So first of all, you want an area that is astrobiologically interesting. So an area that has had liquid water for a certain time, that it's been, there is geological interesting, that is more or less in the equator, so the temperatures are warmer. So you want to look at a little bit of everything as if you were on Earth, right? So if you are looking for life on Earth, you wouldn't go perhaps to Antarctica. You wouldn't go to extreme desert. You would try to go to a place where the temperature, the geology, there is liquid water, and there's been the conditions for life have been there for a certain time, for at least a few million years, for life probably to have developed. So these exploration sites, there is a lot of debate, there is a lot of meetings and workshops to choose landing sites and to see what is the best. You want also areas that are easy to land. You don't want the rover to go into a sand dunes where it's going to get stuck, or it has pointy rocks. So there's a lot of requirements. And unfortunately, when you send a rover, you can only send it to one place. So it's very difficult to choose. But yeah, just think about it. If you were going to choose a place to land on Earth, there's so many different places that you would not think. You could think, oh, there is no life on Earth, but actually it's because you are in the wrong place.
Okay. And last question, what kind of benefit will finding life on Mars do for humanity?
This is a good question too. I think it's in our DNA to know about our where we are, where are we coming from, are we alone in the universe? I'm sure everyone has asked themselves at some point, are we alone? Are we the only ones alive? So the same way in the past, the people had to explore different continents and they had to explore the poles and they had to explore the oceans. Now is the turn of exploring space. So I think it's part of who we are to know more about our surroundings. I'm sure so many people don't care whether there is life on Mars, but I'm sure it will have a lot of implications, not just in science, but also in the philosophy of who we are and where we come from. And if we know there is life on Mars that was independently growing separately from us, then perhaps that means that there is also life everywhere else in the universe. And that's pretty big news. It will be pretty exciting in a way, right? So, yeah.
Another question. Instead of salts, which other compounds can contain water? Maybe my friend Sude, it's a question for you.
Instead of salt, which other compounds can contain water? Well, sorry, I don't understand again the question. So, of course, water can contain a lot of different compounds, but if you mean for water to be liquid,
not liquid.
I think, as far as we've been talking, in order to find, if it's possible to find liquid water on Mars in the surface today, it has to be very salty. There are other compounds. There are other compounds on Mars. Yeah, there are other compounds, perhaps, but the most important one is that there are salts. It's very salty water. I really don't know of. I'm just thinking maybe methane, because many times you see liquid and you think, well, perhaps it's methane and not water, but I just cannot come up with any other compounds that would make water behave in that way unless it's salty water on Mars. And again, that's something that the future astronauts that go to Mars will have to find out, right?
Okay. Well, Thank you so much for everything. It was a big pleasure. We answered all questions we had. If you have an opportunity to see the Solda Lake, I think there is a great wealth of astrobiology.
I will have a look at it. Yes.
Yes.
Thank
I
you.
recommend you to also. We are really sorry about that confliction. We misunderstood each other. My teammate emailed you the time a bit different, but we are really sorry about it.
Oh, that's fine.
And
That's fine.
we are really happy to have you here. Really, it was
Yes.
a good presentation. And also, actually, we have also an analog astronaut missions, Mars on Earth. We have Turkish, yeah. And also, I was the second analog astronaut actually. And but I cannot do the missions like you. You are going and walking and trekking and taking some samples and working on them. I cannot do that yet, but still also our teammates are working on it. So if they actually have a field now, so if they can do that area to reachable for us, so we can do that also.
Yeah, I hope so. It's a very
I hope. Yeah.
Yes.
Yeah, because I really admire your job. I'm always following you on Instagram. Every day I'm just seeing, oh, again, you are at the lab and taking samples. I'm also at the lab, but not working on that.
It's very exciting. There is always problems. You also have to find funding for these expeditions because they end up being expensive depending on where they are. You have to fly there, and you have to maybe ship a box of 50 kilos of rocks. Is very physically demanding, but it's very exciting. And so if you're really up for it, I'm sure you will find a way to do that too.
Yeah, I hope so.
Yes.
Okay, thank you for joining us today.
Thank you to you. Thank you so much for inviting me.
Okay, see you.
Bye.
Bye.
This is your last session for today. Thank you for attending our conference and for watching until this hour. Today was very enjoyable for us. Tomorrow, Murat Tutkun will be with us at 11 a.m. See you tomorrow. Good evening.
See you guys. We are really thankful for your joining us also, not just our speakers.
Okay, goodbye.
Bye
bye. Emre, mutsun. Konuşuyorsun ama duymuyoruz.
Pardon, çok pardon, özür dilerim. Türkçe devam edeyim. Zaten yarınki sunumlarımız Türkçe. Murat Beyran'ın dediği gibi Murat Tutkun'la başlıyoruz. Prof.Dr. Ali Demirsoy var. Türkiye'de biyolojinin hani babası diyebileceğimiz yaşayan değerli isimlerinden birisi saat 1'de. Ve Duhan Toparlak da yarın bizlerle. Hepinizi dolayısıyla bekliyoruz. Şu vakte kadarki katılmanız için de tekrardan teşekkürler diyorum.
Onun dışında İngilizce sunumlarımız da olacak ama en azından 3 hocamızın Türkçe sunumu olacak. Yarın görüşmek üzere. Herkese iyi akşamlar.
Görüşürüz. Buradan mı fotoğraf alalım yoksa buradan fotoğraf çekelim mi?
Yayınımızı